First of all, let's see what is computer vision, because OpenCV is an open source computer vision library. So computer vision is the way of teaching intelligence to machines and making them see things just like humans. So what happens when a human sees an image? He will be able to recognize the faces which are there inside the images. So in its simplest form, computer vision is what allows computers to see and process visual data just like humans. Computer vision involves analyzing images to produce useful information. So to give you some examples, a self-driving car, it can detect the lanes using computer vision. Or you might have wondered how Facebook detects images when you upload the images of you with your friends. It becomes possible by Facebook's face and image recognition technology. So now let's see what is OpenCV. So OpenCV, which stands for Open Source Computer Vision, is a library of programming functions mainly aimed at real-time computer vision. It is originally developed by Intel, and then it was later supported by a developer called Willow Garage, and now it is supported and maintained by Itseez. Now OpenCV is available on Mac, Windows and various Linux operating systems. So we can say that OpenCV is a cross-platform library. Now you can work on OpenCV using C, C++ or Python, and we will be using Python to learn OpenCV. Now OpenCV is an open source and free library which is licensed under BSD license, and it's said that it is very easy to use and install. That we will see when we will install OpenCV on various operating systems. Now because OpenCV primarily deals with computer vision, that means dealing with mainly images or videos, so I wanted to show you how a digital image is seen by a computer. So digital images are typically stored in the form of matrix. Now if you have heard about PPI or pixel per inch, which refers display resolution, that means how many individual pixels are displayed in 1 inch of digital image. So when a computer sees a picture, it sees it in the form of pixel matrix. Now there are two types of digital images. One are called grayscale images and other are called colored images. So in grayscale images, each pixel represents the intensity of only one shade. That means how bright or dark the pixel is. In other words, it is said that it has only one channel. So on the right hand side you can see a grayscale image, and on the left hand side you can see a colored image. So in colored images we have three channels, that is RGB, which stands for red, green, blue. So grayscale images have one channel and colored images have three channels. Your standard digital camera have three channels, that means red, green, blue channels. So we will learn more about images and how we can process images using OpenCV in the later videos. Now there is one more thing which I want to show you is Numpy. So we are going to learn OpenCV using Python. So when you will install OpenCV library for Python on your operating system, Numpy will be automatically installed with this library. So first of all, what is Numpy? So Numpy is a highly optimized library for numerical operations. Now as I told you, digital images are 2D arrays of pixels, and Numpy library is a general purpose array processing package library. So it provides a high performance multi-dimensional array object and tools for working with these arrays, which makes the processing of images easier. Now all the OpenCV array structures are converted to and converted from Numpy arrays, and in addition you can use more convenient indexing system rather than using for loops. So when you want to learn OpenCV using Python, you need to have some knowledge about Numpy also. So if you have some knowledge of Numpy library, it's good, but don't worry, I will teach you step by step so you will not miss anything. So that was a brief introduction about computer vision and OpenCV. In this video, I'm going to show you how you can install OpenCV for Python on your Windows operating system. So obviously you need to install Python on your Windows operating system in order to install OpenCV for Python. So first of all, I'm going to show you how you can install Python on your Windows operating system, and then we will see how to install OpenCV using Python. Now, if you have already installed Python on your Windows operating system, you can skip about 5 minutes of this video and go directly to the point where I am going to show you how you can install OpenCV for Python. So let's get started. So first of all, open your favorite browser on your Windows 10 operating system and then search for Python. And the first link which will appear here will be from python.org. So we are going to click on that link. And once this python.org website is open, you just need to scroll down a little until you see this downloads section. And you can see at the time of making this video, Python 3.7.0 is the latest version of Python available. So we are going to click on this link which says Python 3.7.0, and you will be redirected to this page which says Python 3.7.0. And now I'm going to scroll down until I see the files here, and you will see there are various kinds of installer available here. We are going to install the Python using the executable installer. So we are going to choose this option which says Windows x86 -64 executable installer, and now I will wait for this executable to be downloaded. And once this executable is downloaded, you just need to click on this exe file, and I'm going to minimize the browser here. So you can see Python's 3.7.0 setup window has been started, and on the first window you will see two options here. One is install now and other is customize installation. So what we are going to choose is this option which says customize installation, because when you choose this install now option, Python will be installed at this path which I don't want to use. You can see it's a long path which I don't want to remember. So I will use this option which says customize installation, and I will also check this option which says add Python 3.7 to path. So now let's click on customize installation, and next you will see this optional feature window, and you can see there are some optional feature which this Python installer will install. For example, documentation, pip it will install, which is a Python package manager, idle IDE, Python test suite, and other feature it's going to install. So I'm going to leave everything as default, and then I'm going to click next. And now this next window will open which says advanced option. Here I'm going to check this option which says install for all users, and I'm going to leave other check boxes as checked. And then you will see this section here which says customize install location. So I want to install Python on my C directory. So what I'm going to do is I'm going to open the Windows Explorer, and I'm going to go to the C directory here. And once the C directory is open, I'm going to right click here and I'm going to create a new directory, and I'm going to name this directory as Python, and then I'm going to press enter. And this path I'm going to give here in the customize install location. So I'm going to just give this path which says C:/Python and then \Python 37. 3.7 here means that we are going to install 3.7 version of Python. So now Python will be installed at this location on my computer, and then I'm going to click on the install button here, and then you will see the installation will start and it will be finished in a few seconds. So just wait for the installation to complete, and after some time I can see this message which says setup was successful. So I'm going to click on this close button which is going to close this installer. So now in order to check whether Python is installed on our Windows operating system or not, we are going to search for Python here, and you will see few options here. One is this Python 3.7 terminal, other is idle IDE. So first of all, we are going to click on this option which says Python 3.7 64-bit, which is going to open this kind of terminal. So this is a Python terminal, and here we can for example print something. So I'm going to just write print, and in the parentheses and in between the double quotes I can just write hello world, and then press enter, which is going to in return print hello world. That means Python 3.7 terminal is working. So I'm going to close this terminal now. And once again, I'm going to search for Python here. And this time I'm going to select this option which says idle. Okay, so just select this option which says idle, and in the parenthesis Python 3.7 64-bit. So this idle is an IDE which comes with Python installation. At the time of installation, we have chosen this option to install idle. That's why we can see this option here. And also this is an interactive shell, so you can once again write print, and inside the parenthesis you can just write, for example, once again hello world, and then press enter, and it's going to give you this kind of output here. So now Python interactive shell is working and idle IDE is also working. So I'm going to close this idle IDE, and now I want to check whether Python is working using my command prompt or not. So I'm going to right click on this Windows button, and then I'm going to click on command prompt, and here I'm going to first of all write Python and then press enter. And you can see this Python option is working now even on your command prompt, right? So here also you can just write print, and inside the parentheses you can just print hello world, and then press enter, and it prints hello world in return. Now once Python is installed on your Windows 10 operating system, we are going to install OpenCV using pip. Now pip is automatically installed on your Windows operating system with the Python installation. So you don't need to separately install pip on your Windows operating system. It comes automatically with your Python installation. So to verify this, first of all, I'm going to check the Python version. So you can just give this command python --version, and then you can check the pip version. So you can just give this command pip --version. So just give this command, and it's going to give you the version of pip which is installed on your Windows operating system. So to install OpenCV using pip, you just need to give this command pip install OpenCV -Python, and I'm going to press enter. So you can see OpenCV related packages are downloading now. So now OpenCV Python package is installed using pip on my Windows operating system. Now you will observe one more thing here, and that is Numpy package will be automatically installed with your OpenCV Python package. So now once OpenCV Python package is installed, we can verify it by just opening our Python shell. So I'm going to just give a Python command to open the Python shell, and then here I'm going to just write import cv2. Okay, so once you give this command, it should not give you any error, and if this import gives you error, that means OpenCV is not correctly installed on your operating system. Now after importing, you can just check the version of OpenCV which you have installed using cv2 dot underscore underscore version underscore underscore, and then press enter, and it's going to give you the version of OpenCV which is installed on your operating system. And in our case, this is 4.0.0 at the time of making this video. Now you can check the same by writing your code inside a Python file also. So here I have opened my Visual Studio Code editor, and I have already created sample.py file, and here also I'm going to import the cv2 package first of all, and then I'm going to print the version of cv2 using this print statement. So I'm going to just write cv2 dot underscore underscore version underscore underscore, and then save this script. And to open the terminal inside Visual Studio Code, you can just press Ctrl+Shift+P and then type toggle integrated terminal. So just type toggle integrated terminal and then click on this first option which says toggle integrated terminal. This is going to open the terminal inside your Visual Studio Code editor. So here you can run your Python script using the Python command. So Python and then name of the script, which is sample.py in my case, and then press enter. and it's also going to give you the version of OpenCV which is installed on your operating system. So this is how you can install OpenCV for Python on your Windows operating system. In the last video, we have seen how we can install OpenCV for Python. Now from this video, we will actually start writing some code. Now moving forward, I will be using PyCharm IDE to demonstrate how OpenCV works, but you are free to use any IDE or any other editor in order to use OpenCV. Now on PyCharm IDE, you need to install OpenCV little bit differently. So if you are using OpenCV, you just need to create a project inside OpenCV, and then you just need to click on File and then go to the settings. Now once this settings window opens, you just need to go to the project, and then it'll say after colon your project name. So my project name is OpenCV examples. That's why it's written here OpenCV examples. So project colon your project name. So just click on this section and then click on project interpreter, and on the right hand side you will see all the packages which comes pre-installed when you create a project inside PyCharm IDE. Now we want OpenCV Python package. So to install OpenCV Python package on PyCharm, you just need to click on this plus button here, and then you just need to type OpenCV -Python. Now the first result you can see here is OpenCV -Python, and the version which is available right now is 4.0.0.21, which is the latest version. So to install this package for your PyCharm IDE, you just need to click on install package button, and then after some time you will see this message which says package OpenCV -Python installed successfully in the green bar. That means OpenCV package is installed successfully. So you can close this window, and now you will be able to see OpenCV -Python is added to your packages, and also Numpy is added to your packages, which comes with your OpenCV Python package. So I'm going to just click OK, and now you will be able to import this CV2 package in your Python script. Now in this video, I'm going to show you how you can read images and write images using CV2 package. Now let me show you where you can find some sample images for your project. So you can open the browser and then go to this URL github.com/OpenCV. So just go to this URL, and then under this OpenCV project in GitHub, you will be able to see these repositories. You just need to choose this repository which says OpenCV, and then you can scroll down, and all the images you will find inside the samples folder. So I'm going to go inside the sample folder, and then inside the sample folder you just need to go inside the data folder. So here you will find many sample images and videos and other files which you can use in your project for the learning purpose. So you can use these images in order to develop your example. So what I generally do is I just go to this repository which is under the URL github.com/OpenCV/OpenCV, and then I either download the zip file of this project or clone this GitHub repository on my operating system. And once you clone or download this repository, it will look like this. So it will be downloaded as this folder, which is OpenCV-master. And once again, you can go to the samples folder here, and inside the samples folder, you can go to the data folder, and you will find all those images which I have shown you on the GitHub repository. Now to start with, we will be using this image, which is lena.jpg. So I'm going to just copy this image for now, and then I'm going to go to my PyCharm IDE, and then I'm going to just paste this image inside my project. So this JPG image will be directly available inside my project folder. Now let's see how we can read images using the CV2 module. So you just need to use CV2, and there is a method called IMRead which enables you to read the images. So the first argument which you need to give here is the image name. So I'm going to give the image name, which is lena.jpg, and the second argument here is a flag. So there are three flags you can give here. You can either give 0 or 1 or -1 flag here. So this second argument is a flag which specifies the way images should be read. So let me show you all the flags here. So the first flag is cv2.imread_color, or you can give the integer value of it, which is 1. And whenever you give this flag as the second argument of IMRead function, it's going to load the colored image. If you give this flag, which is cv2.imread_grayscale, or if you give this integer value, which is 0, it's going to load your image in grayscale mode. And the third flag is IMRead_unchanged, or the value -1, which is going to load your image as it is, including the alpha channel. So for now, we are going to just give here 0 flag, which means we want to load our image in grayscale. So now let's run the code and let's see what happens until this point. So you can see our code runs fine without giving any error. Now let me give any random name here as the file name, and once again run this code, and once again you will see that there is no exception which is thrown here. So even if you give the wrong file path or file name here, this function is not going to give you any error. Now in case of wrong path or wrong file name, let's say I'm going to just assign this value to a new variable, which is img, and let's print the value of this img using the print method, and then let me run the code once again. And you can see whenever you will give the wrong file name here or wrong path here, as a result of this method you will get none. So you can check the value of image, and if it is equal to none, then you know that you have done something wrong, or you have given some wrong file name or wrong path here. Let's give the correct file name. So I'm going to give the correct file name and then run the code once again. And now this time you will see it's going to give you a matrix, which means that it has read all the pixels from this image and then assigned it to our img variable, and the result you can see in the form of this matrix. So until now we have just read the image. Now we want to display our image. So in order to display our image, what we can do is we can use a cv2.imshow method. So just write imshow here, which is going to show your image. So the first argument here will be the name of your window in which your image will open. So you can give any name here. For example, I'm going to give image name here to my window, and then the second argument is the image variable which you have read using the imread method. So I'm going to just pass img variable, which is this variable here. So now will it show the image? Let's check. So I'm going to run the code once again, and you can see the image is shown for a millisecond and then it disappears. So now we need to add something which will wait for the image to disappear. So I'm going to add one more method here, which is cv cv2.wait key. So this cv2.wait key is the keyboard binding function, and the argument which it takes is the number of milliseconds for which you want to show your image window. So let's give 5000 value here, which means we want to show the image for 5 seconds. And at last, what we are going to do is, after we have done seeing our image, we will destroy the window which we have created. So you can just give this method cv2 destroy all windows. So destroy all windows simply destroys all the windows which we have created. There is one more method which is destroy window, and this method you can use to destroy a particular window, which we will see little bit later, but for now we will just use this method which says destroy all windows. So now let's run our code and let's see what happens. So now this time you can see our image is loaded for 5 seconds and our image is loaded in grayscale mode. Now if you give here 0 as the argument of wait key method, then let's see what happens. So I'm going to run my code, and now you will observe that your window will not disappear after 5 seconds or any number of seconds. It's going to wait for the closing of this window, which we can close from this close button. And you can see it's loaded in the grayscale mode. I'm going to close this window, and here as an argument of IamRead image, the second argument I want to give here right now is 1, which means the colored image. And let's run the code, and you can see this image is loaded in the colored mode now. Let's also check the -1 argument, which is unchanged. So it's going to just load the image as it is with alpha channels. So let me just close this image once again. So now we have understood how we can read an image using IamRead function. So let's see how we can write an image to a file using a function called IamWrite. So we are going to just use cv2 once again, and then there is a method called IamWrite, which you can use to write an image in the form of a file. So the first argument here will be the image name, whatever you want to give here. So here, let's say we want to give the name to our image as lena_copy.png. So the image will be saved as the file name lena_copy.png file, and the second argument which it takes is the image you want to save. So let's save the same image which we have read using the IamRead function inside this img variable and pass it as the second variable here. And let's run the code and let's see what happens. So our image is loaded using this IamShow function, and now when I close this window here, you will observe one more file will be created here. So let me just close this window, and now you can see as soon as I close this window, this method is called, and after this IamWrite method will be called, and when this method is called, this image is created with the name lena_copy.png. We can also open this image, and you can see it has the same image which we have seen in the case of lena.jpg. So let me close these two images. So now we have understood how we can read the images and write the images using IamRead function and IamWrite function. So let's make our code little bit better. And what we want to do here now is, let's say if somebody presses an escape key, then only we want to destroy all the windows without saving it into a new file. Otherwise, if somebody presses the S key, then we are going to save this file with the new name, let's say lena_copy.png file. So I'm going to just capture the output of my wait key. So just create a new variable, let's say k. So now when we press any key, this key will be captured in this variable. Now, as you know, every key has its own value, so we are going to just use if condition, and we are going to just check whether the value of k is equal to 27, which means that we have pressed the escape key, and if somebody have pressed the escape key, we are going to simply destroy all the windows. Otherwise, let's give the second condition, which is L if k is equal to ord, and this is a built-in function, and it takes one argument, which is the key name which we want to press. So let's say somebody presses the S key, and if somebody presses the S key, we just want to save the image which we have read using the imread function to a second image which we call lena_copy.png, and then we will simply destroy all the windows which we have created using imshow method. So let's run the code and let's see what happens. So I'm going to run the code. So this image is loaded, and as soon as I press escape button, you can see this image disappears. That means this condition is met and this method is called, and all the windows will be destroyed without saving the image. Let's delete this image and let's see what will happen when we press the save key. So let me just delete this image, and now let's run the code once again, and this time I'm going to press the S key, and once again you can see the windows are destroyed, but this image is created once again using this function. That means this time this condition is fulfilled and this image is created, and after that all the windows are destroyed. So this code is working fine for me, but in the documentation it's also written that if you are using a 64-bit machine, it's better to use this notation with your wait key method, which is wait key and this mask here, and then once again when we run our code it works as it is. But in case if it doesn't work, you can try using this mask here. So this is how you can read and write images using OpenCV. In this video we will see how to read, display and save videos using cameras. So often we have to capture live stream from camera. So first of all, we will see how we can capture the live stream from the camera. The same method you can use to display the video from a video file. So let's get started and let's see how we can capture the live stream from your default camera. So I'm going to just create a variable called cap, and then inside your CV2 package there is a class called video capture. We are going to take this class and create an object of it, and as an argument here you can provide either the input file name. So for example, if you want to just read the video from a particular file, you can give the file name, for example my file.avi or mp4, or you need to provide the device index of your camera from which you want to read. So by default this index will be either 0 or in many devices it's also -1. So first of all we are going to try with 0 device index, which in most cases works. So if this device index 0 doesn't work, try with -1. Now if you have multiple cameras and if you want to use the other camera, then you can also try 1 for the second camera or 2 for the third camera and so on. So we are going to use the default camera, which is at device index 0. So this is the argument we need to provide here, and then we are going to create a while loop in order to capture the frame continuously. So let's create a while loop here, and this loop we are going to run indefinitely. So we are going to just say that while this loop is true, we want to capture the frames. So we are going to just define these variable ret and frame, and then using this cap instance we are going to call a method called read. Now this read method is going to return true if the frame is available, and this frame will be saved into this frame variable. So here the true or false will be saved. If the frame is available, this RET will be true, otherwise it will be false, and this frame variable will actually capture or save the frame. Now in order to show this captured frame, we can use IamShow. So I'm going to just use a cv2 dot IamShow, which is going to show this frame inside the window. First of all, you can give the name to your window, for example frame, and then second argument will be the frame which you are reading, which is this variable here. Now in the next step, we have seen in the last video also, we are going to use the cv2.wait key in order to wait for the user input, and if this input will be Q, we will quit the window and destroy all windows. So we are going to just say cv2.wait key, and the argument here will be 1. And I have told you, you need to provide this mask for 64-bit machines. So you can provide this mask, and then we are going to just see if this key which is pressed is Q or not. So we are going to use the ORD method for this, and we will just check if the Q key is pressed, and if this Q key is pressed, we are going to break from the loop and we will come out of the loop. And after we come out of the loop, the first thing we need to do is to actually release the capture variable. So this is important. After reading your video, you need to release the resources. So you need to just call this method cap.release, and then we will just destroy all windows. So let's run this script and let's see what is the output. So I'm going to run this script, and you can see in this window the input from my default webcam of my laptop. Right now I'm just showing some book in front of this camera, that's why you will see this book. And as soon as I press Q key, our window will be destroyed and we come out of this script. Now let's say you want to change the frames to gray. So we want to convert our video input from the colored image to the grayscale image. For that, what you can do is you can define a variable called gray or anything else, and then there is a method called cv2.cvt color, which is to convert color, and the first argument which it takes is the source. So in our case, the source is the frame which we are capturing from the cap.read method. The second argument is actually the conversion what we want to do. So we will just call cv2.color underscore, and by default the default colored image is captured as BGR image, that means blue, green, red channel images, and we want to convert it to a grayscale image. So we will just write BGR to gray. This means we want to capture the BGR image to the grayscale image, and now this is going to give us the grayscale image, and this input we can just transfer to the IamShow method as the second argument of this IamShow method. So let's run this script once again and let's see what is the output of the script. And now you can see the video captured is in grayscale image, and as soon as I press Q, it's going to release all the captured resources and then destroy all windows. Now, as I said, if you want to display the image from a video file, you just need to give the name of the video file, for example name, and then the extension, which is, let's say, AVI or MP4 or any other format. Now using this cap instance, you can read few properties about the video which is captured, and the first property is if the video is open or not. So in case whenever you provide the file name and the file path is wrong, then this is going to give you false. So there is a method called isOpened, and this means if the file name of the video which you want to provide here is correct, this is going to give us true. Otherwise, this isOpened is going to give us false in case the file path is wrong or the index which you give here for the device is wrong. So let's give any random index here and then let's see what happens. So I'm going to run this script and you will see nothing will happen because this isOpened is going to give you false. Let's print that also and let's verify with the print statement the same thing. So I'm going to just use this and then run the program once again, and you can see it prints false. That means you cannot capture the video using this index. So my device is at index 0 by default, so I need to give this index name. Otherwise, for example, I provide the wrong file name here also, it's going to give us the false value. There is a method called cap.open also. So if this cap is open gives you false, you can try opening your capture video using cap.open also. Now there are other properties which you can read using this cap instance, and the property you can read using a method called get. So you can just write cap.get, and as an argument of this get method you can provide the prop ID. So there are different prop IDs which you can read. So let's say we want to read the property which is called frame width and frame height, which is going to give you the height and width of your frame. So for this you just need to write cv2 dot cap underscore prop underscore frame underscore width. This is going to give you the width of your frame, and if you want to get the height of your frame you can use cap underscore prop underscore frame underscore height. And this whole list you can find on the official documentation of OpenCV. So I will provide you this link where you can see different values of the prop ID. So right now I have used this ID and this ID, but there are several number of IDs available here which you can use to read the property of your frame. So let's use print method to just print out what property we are reading, and let's once again run this script. And here you can see in the output you can see the value 640 and 480, which is the width and height of your frame by default. Now let's see how we can save the image which we have captured from our webcam or the default camera. So as we already know that we read frame by frame when we capture the videos from your default camera. So for creating the capture you have used video capture class, and for saving the video we are going to create the video writer class. So I'm going to first of all create a variable called out for output, and then I'm going to call a class called video writer. So let's call this class which is video writer, and now this class takes few arguments. The first argument is the name of your output file. So for example I can just give the name output.avi, the extension of the file. The second argument here is the 4cc code. Now 4cc is a 4-byte code which is used to specify the video codec. And if you want to know more about 4cc code, you can visit this website which is 4cc.org/codec.php, and here you can find several 4cc codes. So for now what we are going to do is we are going to just get the 4cc code using a class called video writer underscore 4cc. So I'm going to declare a variable 4cc, and then I'm going to use cv2 to call a class called video writer 4cc. So as an argument of this class you just need to provide the 4cc code. So for example I can give this kind of code. So you can provide this argument which is asterisk and then your courese code which is xvid in this case, or otherwise what you can do here is you can also give this code in this format. So for example x comma, then second argument is v, and then third argument is I, and the fourth argument is d. So you can either give this type of notation, or you can just use asterisk and then in single quotes you can just write xvid or any other code here, and then this courese code we are going to pass as the second argument. The third argument is the number of frames per second. So let's say we just want to use 20 frames per second, and the fourth argument is the size. So we already know that the size in which we are capturing is 640 by 480. So we are going to provide this in the form of tuple. So 640 comma 480. So this will be the size of the video which will be saved in this file. Now inside our loop, as we have seen, we are just reading the frame here in the frame variable, and this is the boolean variable. If the frame is available, it's true, otherwise it's false, right? So first of all we are going to check if its value is true or false. So we can just write if ret is equal to true, then only we are going to just save this file into the output file. So I'm going to just put everything inside this if condition, otherwise we are going to break out of this loop. So I'm going to just say else break. Now inside this if condition we can just write this frame into a file using a method called out.write. So out is the instance of video writer, so I'm going to just use out.write, and then we are going to just pass the frame which we have captured, which is inside the frame variable. And now at last we are going to release all the resources using the out instance, which is the instance of video writer. So I'm going to just write out dot release, and then let's run the script and let's see what happens. So one thing to note here is our video will be saved as it is, that is in the BGR mode, that is in the colored mode. So let's run the code and let's see what happens. So I'm going to just start my script once again, and now I'm going to just press Q. So you can see here our video is shown in the grayscale, and our video will be saved in the original format because we are saving every frame before the conversion. So it will be saved in the original format. So I'm going to just close this script, and as soon as I close the script you can see the output.avi file, and in order to verify this file I'm going to go to the project, and here I'm going to start this file using, let's say, VLC media player, and you can see it shows the output of the output.avi file. So this is how you can read videos, display and save videos using the default camera or the video file. In this video, we will learn how to draw different geometric shapes using OpenCV. So to start with, I have this code and I have already explained what this code does. So this IamRead is used to read an image, and then we are just showing this image into a window using this IamShow method, and then using the wait key we will wait for the closing event, and the destroy all window will destroy all the windows which we have created. So this we have already seen. Now let's say we want to draw some geometric shapes on this image. So to start with, let's learn how to draw a line on our image which we have read from this read function. So what we are going to do is we will overwrite this image. So we have already created this image variable. So what we are going to do is we will draw a line on the same image. So I'm going to just write img is equal to cv2 dot lines, and you can see in the suggestion this line method takes few arguments. So the first argument is the image itself, the second argument is the starting coordinates of point 1, the third argument is the ending coordinates of point 2, and then the fourth argument is the color, and fifth argument is the thickness. So let's use this line method and then give these arguments one by one. So we want to write to the image which we have read using this file. So the first argument is the image variable, and the second argument is the coordinates. So the coordinates should be given in the form of tuple. So let's say we start with 0, 0 coordinate, and the ending coordinates will be, let's say, 255, 255. Okay. The fourth argument will be the color, and the color you need to give in the BGR format. So if you want to give the blue color, then you can just write 255, 0, 0, because first is the blue color, second is the green color, and third is the red channel color. So if you specify here 255 in the first channel, that means the blue channel, then it's going to draw the blue line. If you give here 255 and then you make other channels 0, then it's going to draw the green line. And if this 255 comes at last and the other channels are 0, then it's going to draw the red line. So let's say we want to draw the red line, that's why I have given 255 here. And the next argument is the thickness. So the thickness you provide in the numbers. So starting from 1 is the lowest thickness. You can increase the thickness 2 or 3 or let's say 5 or 10. So it's going to increase the thickness based upon this number. So let's say we want to give the thickness to our line 5. So this is going to draw a red line on our image. So let's run the code and let's see what happens. So you can see our image is loaded in the grayscale. That's why you don't see any color on the line, but our line is created here. So let's load this image in the colored format by changing this argument to 1, and let's run the code once again, and you will see the image is loaded in the colored format and the line color is red. Now if you want to change the thickness of this line, you can just increase this number, and if you want to change the color of this line, you can change it using these color channels. So let's change the line color to green, let's say, and I'm going to run the code, and you can see the thickness of the line is increased, and now the color of the line is green. Now if you want to draw the line with any other color, you can just go to your favorite browser and search for RGB color picker, but always remember our image will be loaded in the BGR format, so in the reverse order. So blue, green, and then the red channel. So let's say we want this color here, and its RGB channels are this. So I'm going to just copy all these channels, and then I'm going to give these channels in the reverse order. So first of all 147, then 96, and then third channel is the 44, and then I'm going to run my code, and you can see you get the same color which you have chosen here. So this is how you can change the color of your lines. Now there is a function called arrowed line. Let's say we want to use this function which is called arrowed line, and this is going to draw the arrowed line as it says. So let's say we want to just draw this arrowed line in blue color. So I'm going to just give the color channels here and then run the code, and this arrowed line is overlapping on the previous line. That's why you don't see the previous line. So let's change the coordinate of this line. So let's draw this line in this coordinate, which is going to draw the straight line in my opinion. Let's see what happens when I run the code, and you can see it draws the straight line from left to right, which is the arrowed line, and this was our original line. Now let's see how to draw the rectangle. So to draw the rectangle, we will do the same. We will just overwrite on the same image. So we will just say image is equal to cv2 dot rectangle, which is a method, and you can see what are the argument it takes. So the first argument is the image itself. The second argument is the 0.1 and 0.2. This 0.1 and 0.2 coordinate I'm going to explain in a bit. The third argument is the color, which is same as line, and the fourth argument is the thickness. So let's use this rectangle function to draw the rectangle. So first of all, I'm going to just pass the image variable here. The second argument is the top left vertex coordinates. So let me just draw something here so you will be able to understand in a better way. So when you want to draw a rectangle using OpenCV, this here is a top left vertex coordinates, which is x1 and y1, and this is here the lower right vertex coordinates. So the top left vertex coordinates you give in the second argument. So let's give some coordinates here. So 384, 0, and the lower right coordinates I want to give here is, let's say, 510, 128. So let's say we want to give the red color. So I'm going to just write 0, 0, 255, and the thickness I want to give here is 5, and I'm going to just remove this because it will just create problems. And now let's run the code, and you can see the rectangle is drawn with the red color of thickness 5. You can change the thickness of this rectangle by changing the value of the thickness, and then you can run the code, and now the thickness of this rectangle line is increased. Now one more thing you can provide here is, instead of giving the thickness value, if you write here -1, then it's going to fill the rectangle with the color which you provide here. So when we give -1 here, let's see what happens. So now we get the filled rectangle because we have provided -1 option here. So if you provide -1, then your rectangle or whatever shape you are creating will be filled with the color which you specify here. So let me just change the thickness to 10 once again, and now let's see how we can draw the circle. So to draw the circle, we once again use cv2 dot circle function, and once again you can see what are the argument which it takes. So the first argument is the image, the second argument is the center of the circle, the third argument is the radius of the circle, and the fourth and fifth argument is the color and the thickness once again. So once again we will provide the image. The second argument is the center of the circle. So let's give the center of the circle, which is the coordinate on which you want to give the center. So I'm going to provide, let's say, 447, 63 here, and the third argument is the radius. So radius we want to provide here is, let's say, 63, and the fourth argument is the color. So let's use 0, 255, 0, which is going to draw the green color, and then let's give -1 here. So our circle will be filled with green color, and let's run the code and let's see what happens. So you can see this circle is drawn here, and this circle is filled with the green color. Now let's see how we can put some text into the image. So to put the text on our image, we will once again use the image variable and overwrite on it, and then we will use a method called put text. So this is the method which we are going to use. The first argument is the image. The second argument here is the text which we want to put. So let's say we want to just print OpenCV on our image. So we can just write OpenCV as the second argument. The third argument is the starting point of your text. So you need to give the coordinates where you want to start your text from. So the coordinates I want to give here is, let's say 10, 500, and then the next argument is the font face. So the font face you need to give here using a variable. So I'm going to create a variable, let's say font, and then there are many font faces available using CV2. So you can just write CV2 dot font in capital, and you can see what are the options available here. I'm going to choose the first one itself, which is font Hershey simplex font, and then we are going to pass this font as the fourth argument. The fifth argument here will be the font size. So let's say I want to give the font size 4 here. The sixth argument here is the color of your font. So let's say I want to just draw 255, 255, 255, which is going to give us a whitish kind of color. The next argument we will give here is the thickness. So let's say I want to provide the thickness 10 here. And the next argument you can give here is the line type. So let's say I want to give the line type CV2 dot capital line underscore AA. And now let's run our script and let's see what happens. So you can see here OpenCV is printed in the white color of thickness 10. And if you want to change this color, you can change it from here. So I'm going to just put the first channel as 0, and now this color is changed to yellow color. Now one more thing I want to show here is how you can create an image using Numpy zeros method. So either you can use an image which you read from imRead method, or what you can do here is I'm going to just comment this code and we can create an image using the Numpy zeros method. So I'm going to create this img variable, and then I'm going to use the Numpy module. So just import this Numpy as np, and then we are going to use this mp to call the zeros method. Now in order to create a black image using this zeros method, you need to give the first argument in the form of list, and inside this list the first element will be the height, second will be the width, and third will be 3. So let's say we want to provide the height 512, we want to provide the width also 512, and the third argument will be 3. And the next argument you give here is the d type or data type. So you can just write np dot u int 8 here. So this method is going to give you a black image of the size 512 by 512. So let's run our code and let's see what happens. So you can see now you can see the black image, and on our black image the line is drawn, the arrowed line is drawn, and the text and the circle and the rectangle are drawn here. So this is how you can draw different geometric shapes on your image. There are several other methods you can use, for example cv2 dot polyline method or cv2 dot eclipse method to draw eclipse and polygon on your image. So just try those method to draw different shapes on your image. So in this video we will see how to set some properties to our captured images. So in the video capture lesson we have seen that when we create a cap variable using the video capture class, we can get many properties using the cap.get method. So we were able to get the width of the frame and the height of the frame. Similarly, we can use the cap.set function to set some values. So you can just write cap.set and then you can set the values of the property. Generally, all the properties which you can read like this, you can also able to set those property using the set method. Now this notation you can also give in the form of numbers. So every property here has a defined number. So for example, instead of using cv2.cap_prop underscore frame width, you can just write 3 here, and that will work also. So every property has a number associated with it. So using that number, either you can just, let's say we want to set the width and height, either you can write this as the first argument and the second argument is the actual width you want in the video, right? Or you can just give the number of that property and then give its value. So let's say we want to change the width of this video to, let's say 1208, and then let's just set the height. So cap.set, and the associated number for the height parameter will be 4. So 3 for width and 4 for the height, and let's say we want to just move it to 720, and then we will once again print the value of the width and height, and this time we are going to just give their associated numbers, which is 3 and 4. So let's run this program. You might already know this program, what this program is doing. So it's just capturing the video from your default device at index 0, and then it's just showing all the frames using this IMShow method in a window. So now I'm going to run this script and let's see what happens. So when I run this script, you can see the size of this frame is changed. So let's see in the terminal also. You can see before, the original size of the video we are capturing is 640 and 480. So width was 640 and the height is 480. Now once we have changed the width and height, you can see the width is changed to 1280 and the height is changed to 720. So even if I have given here 1208, the default camera will automatically set its value according to its resolution. So let's just close this video, and let's say we want to just change this value to some random number. So let's say 700 by 700. Will it work or not? So let's run the script once again and let's see what happens. So the script is running, and you can see that even though we have provided the 700 and 700, the camera will automatically take the resolution which is available for your default camera. So the resolution remains the same even though we have set the different value to it. So you need to keep in mind, even though you can give any value here, but the camera will only set the resolution which is available for it. So let's give a very big value here. So I'm going to provide, let's say 3000 here, and height also 3000, and let's run the script once again and let's see what happens. So when we run the script, you will see the resolution is changed, but the resolution will change to the maximum resolution of my default camera, which is 1280 and 720. This is the maximum resolution which is available for my webcam. So let me just close this window. So this is how you can set some values. So there are many values you can set using this set method. You just need to go to the documentation and then search for the value you want to set. So in the last two videos, we have seen how to capture videos from our default camera device, or how to add geometric shapes on the images. Now in this video, we are going to combine the knowledge we have gained in the last two videos. So if you haven't seen the last two videos, I will recommend you to watch those videos and then come to this video. So in this video, we will see how we can just draw something on a video, and more specifically, the aim of this video is how to show the current date and time on a live video. So now in the last video, we have seen how to draw shapes on images, and we have also seen how to put text on our images, right? So let's say we just want to print the value of width and height on the default camera. And let me just remove this line which we have used to convert the BGR image to the grayscale image. So we will just see the colored BGR image. So now what we want to do is we want to print the width and height which we get from these properties on our video which we are capturing. So in the last video, we have already seen that we can use a method which is cv2 dot put text. Yeah, so this method we have seen in the last video. And first of all, we will define the font which we will pass to our put text method. So the font I'm using here is cv2 dot font Hershey underscore simplex. And now the first argument here will be the frame which we are capturing, because every frame is just like an image and a video is the combination of multiple images. So the first argument here will be the frame. The second argument here will be your text. So the text which we want to show here is, let's say, width and height. So let's define a variable which we want to show on our video. So let's say the variable name is text, and first of all I'm going to define the width. So just say width, and then we are going to provide the value of the width using the concatenation operator. Now because this value will be in integer and we want to convert it to the string, so we will use the str method to convert the integer to the string, and then we can pass the width here inside our string variable. Once again, we will use the concatenation operator, and then let's provide some space here, and then we will just write height colon, and then once again the concatenation operator, and once again we will use this string method, and inside this string method we will now take the height. Okay, and now we will pass this text to our put text argument. Now the third argument is the coordinate. So let's say I want to just put this text at the coordinate 10, 50. The fourth argument is the font which we have already declared. The fifth argument is the thickness. So let's say the thickness we want is 1, and then the color. So let's say the color we want is 0, 255, 255, and then the thickness. So I think the thickness comes after the color, and the value 1 we have set for the font scale. So you can change the font scale 1, 2, 3, 4, any font you can change it from here. So this value 1 is for the font scale, and the value we are providing right now is for the thickness. So let's say the thickness is 2, and the last argument here will be the line type. So I'm going to just provide the line type as cv2 dot line underscore AA. So what do you think? Will this text will be printed on our image or not? So it will not print yet because we need to write on the frame this text. So we need to just write frame is equal to, and then put the text on the same frame which we are seeing right now. So So now this will work, and let me just break this line so you will see all the code. And now let's run the code and let's see what happens when we run the code. So let me run this script, and you will see here that now we are seeing the width and height on top of this video, which is 1280, and the height is 720.0. So this is how you can show text on your video which you are capturing from the web camera or from the video file. Now let me just comment these lines of code because they are changing the resolution of our video and it's not fitting this video screencast. So I have commented this code, and now let's do something more interesting. So now let's say we want to show the current date and time on the video, and you might have guessed how to print it, but let me show you if you don't know how to print the date and time on your live video. So first of all, we are going to import the package which is available inside Python, which is date time, and then we are going to create this date time variable. Let's say the date time variable name will be date t, and then first of all we are going to use the str method to convert the date and time to string, and then there is a method inside this date time library. So we just need to write date time dot date time once again, and then the method called now, which is going to show you the current date and time. So once we have converted our current date and time to the string variable, then we can pass this variable as the second argument. And now let's run this script and let's see what happens once again. So I am running this script, and now you will see that it shows the current time and current date on the video itself. So this is how you can put the text on your video. You can even put some shapes which we have seen in the last video on this video itself. So you can put the line or the rectangle or the circle on your video which you are capturing from the camera or some file. So this was some kind of a mini project which we have created from the knowledge which we have gained from the last two videos. In this video we will learn how to handle mouse event in OpenCV. Now mouse event can be anything, for example a right click event or left mouse button click event or left button double click event. So there are many mouse event available in CV2 package. Now to list out all the events in the CV2 package, you can write this kind of code. So first of all, I'm going to create a variable called events, and then I'm going to just iterate over all the events inside CV2 library. So I'm going to just write I for I in dir inside our CV2 package. So this dir method is the inbuilt method which is going to show all the classes and member functions inside your CV2 package. Okay, so we are iterating over all the function names or member variable names, and then we want to see what are the events available inside this package. So we can just filter those events using a condition. So we are going to just say that we want to just see the variables or the member properties which have this keyword event in them. So event in I, and then we are going to just print out all the events. So I'm going to just print out all the events, and then I'm going to run this code, and here you can see the list of all the events which are available inside your CV2 library. So you can see there is an event called event flag R button for the right button for the mouse, or there is event for left button double click event, or the event for L button down event. So there are many such events available here, and we are going to use those events to listen for the mouse events. So this is how you can print all the events which are available inside your CV2 library. And now we will create a script or a program to listen for the mouse event. So first of all, we will create a mouse callback function which is executed when mouse event takes place. So in order to create this callback function, we are going to just define a function, and then we will give the name to our function. For example, click event function, and this callback function generally takes few arguments. So the first argument will be the event which is taking place when we click our mouse, and then it's going to give us the x and y coordinate on the image where we are clicking with our mouse. So we are going to get the x-axis value and the y-axis value whenever we click the mouse at certain position in our image. Also, we will get the flags and we will get the param. So for creating the mouse click callback function, it has this kind of specific format which is same everywhere. So these are the parameter it takes, and then inside your callback function you can define the logic. So let's say whenever I click the left button down, then I want to show the x and y coordinates on the same image. So I can just say if the event variable is equal to cv2 dot event, and then I will just look for the left button down click event. So if this event occurs, then I will first of all print the x and y axis values. So let's print x comma y, and you can also provide some space between x and y coordinates using this kind of string. And then what we are going to do is we are going to just put this x and y coordinate values on the same image which we are opening. So we have already seen in the last videos how to put text on the videos. We just need to create this font variable for the font, and then there is a method called cv2.putText. So we are going to just write cv2.putText, which takes few arguments. First is the image. Now you can see this image shows error, and this error says unresolved reference, but don't worry, when we write our code fully, this error will go. So first will be the image, the second is the string which we want to put. So let's say we want to put the string str for the x and y value. So I'm going to just write x, y, and then we are going to just print the x value, then concatenation operator, and then comma, and then once again concatenation operator y. And don't forget to convert these coordinate values into the string using the str function. So str function here, and for the y-axis also you need to use this str to convert it to the string value, and then the string we pass as the second argument. The third argument will be the location where we want to put the text, and this location we already know from this x and y value. So it's easy for us. We are going to just say x comma y because we already know the x and y coordinate using this callback event. The fourth argument will be the font. The fifth argument will be the font scale. Let's say it's 1. And then the next argument is the color. So let's say color we want to give here is 255 comma 255 comma 0. And the last argument I want to give here is the thickness. Let's say thickness we want to give here is 2. And then we will show this text on the image using cv2 dot IamShow method. So I'm going to just write IamShow and then the name of the image window, for example image, and the image itself, which is img. So right now this is showing error to us, but when we will call this callback function using a standard function called setMouseCallback, then this error will go. So I'm going to define the img variable first of all, and let's say we want to create a black image using Numpy. So we will call np.zeros method here. So np.zeros, and the size of this image will be 512 comma 512 comma 3, and the data type will be np.uint8. And once we have this image, we are going to show this image using once again the IamShow method, and this image name will be the same image, and the variable we want to pass here is the image variable, which is the black image which we have created using this numpy zeros function. Now the next and the important step here is calling a method called setMouseCallback method. So this method we are going to use to call our callback function which we have created, which is click event function, whenever somebody clicks on the image which we are showing using this IamShow window. So the first parameter it takes is the name of your image. Make sure that this name here which you take in the IamShow method, you can see I'm taking the same name here in the IamShow method also here. So the window name should be the same everywhere, then only it will work. So here also you need to just give the parameter. First parameter here is the window name. So the window name is image, and the second parameter is the callback function which we want to call whenever this event take place. So this is the callback function which we have created. Now the next step are the obvious steps which we have already seen. So first of all we will call the wait key method to wait for the escape event, and the second is the destroy all windows. So we will destroy all the windows once we are finished. So let's run this code and let's see what happens. So now you can see the black image which is created by numpy zeros method, and when I click on this image anywhere, you can see the coordinates of the position where I have clicked is printed here. So let's click here. You can see when I give this left down button click event, then the position of the x and y coordinate is printed on this black image. So I'm clicking again and again this left down button, and the position is printed. Okay, so let me just close this window. Now what I want to do is let's just reduce the size of this font to 0.5. Then the font size will be little bit smaller. Now what I want to do is I want to listen for some other events. So I will go to my callback function once again, and I will add one more condition here. So once again, if event is equal to cv2, and this time I want to listen for the right click event. So I'm going to just write event right button down event. Okay, So whenever somebody presses this right button down for the mouse, then this event is going to be captured inside this condition. Now if you remember, I have told you that image is shown in OpenCV in the form of BGR format, and we already have this image. You can see we have declared the image variable. That's why this error is also gone. So using this image, we want to find out the red, blue and green channel. So now inside this condition, what I want to do is I want to print out the BGR channels of the image wherever I click. Okay, so you can first of all declare a blue variable name, and then we have img variable, which is this one, and using this image variable we can get the blue channel using the coordinates. So first of all you can provide y comma x. We already have the y and x coordinates, and then the channel for the blue color is channel 0 because it starts from blue BGR, so blue, and then green and then red. Okay, so I'm going to just copy it 2 more times. The second is green, and the channel for it will be the 1, or index will be 1 here, and for the red channel this index will be 2 here. So I'm going to just write red here, and once again I'm going to just copy this code, and this time what I want to do is, instead of printing the coordinates, I want to print the BGR channel. So here I'm going to just write blue, and then second will be the green channel, and then the third will be the red channel. So I'm going to just write comma and then concatenation operator str and then red channel. Okay, so this will be the string. We are going to name it as BGR, and this string we will put here. The color also we can change, so the color for the coordinates will be different, and the color for this event will be different, 255. Okay, so it's going to print the BGR channels on your image. Now because we are creating the black image, whenever I just click the right click mouse event, you can see the BGR channels for this black image will be always 0 0 0, right? When I click the left click, then these are the coordinates. When I click the right click, these are the BGR channels. So let's change this image from the black image to something visible. So I already have the Lena image, so we can use this Lena image using the cv2.imread method. So I'm going to just write cv2.imread, and the first will be the name of the file, which is lena.jpg. So now let's run this code once again, and now I have this colored image, so we will be able to see these functionality in a better way. So first of all, the left button click event, you see the coordinate, and when I click the right click button event, then you can see the BGR channels are printed. Once again, here you can see the BGR is different. Here also these BGR colors are different. So you can see everywhere they are a little bit different because this is the colored image and the color differs at every pixel level. So this is how the mouse click event works. In the last video, we have seen how to use mouse click event in OpenCV using Python. So we have seen how we can create a callback function which listens to a mouse click event, and then how to use this callback function using the setMouse callback method. Now in this video, I will show you some more examples about mouse click event. So the first example I want to show about drawing a point and then connecting points using the line. So to start with, I'm going to just remove this if condition for the right down button click event, and every time somebody clicks the left button down click event of mouse, then what I want to do is every time the mouse is clicked down, I want to draw a circle, very small circle, and when he clicks on the next point, then I want to join those 2 points using a line. So for that I will need a CV2 circle. So I'm going to remove this code which we don't need right now. We just need this condition which listens for the left button down click event of mouse, and then what we will do is we will just use CV2 to draw a circle. So we will just write dot circle, and first of all this circle method takes the image, so we are going to pass the image, and then the second argument is the coordinates, x and y coordinate. So we already have x and y coordinate using this callback function with the second and third parameters, and then the third parameter will be the radius. So I will take the radius 3, which is like very small, which will give you effect like a point on an image, and then we can give the color. So let's give 0, 0, 255, and then we will give the thickness. Now the thickness I'm going to give here is -1, and you might already know what this -1 do. So this -1, whenever you give as a thickness, it fills your circle or any closed shape. Okay, so your closed circle will be filled with this color which you provide here. Now next what I want to do is I want to create an array of points. So I'm going to just declare a variable called points and initialize it with an empty array. Now this empty array variable we can use inside our callback function, and what we are going to do is we are going to just add or append every time this mouse is clicked. So I'm going to just call an append method here, and then we are going to append the x and y coordinate to this points array. So we know that where this mouse is clicked, and we are saving the coordinates wherever the mouse is clicked in the form of array. Now in the next step what we will do is if the mouse is clicked more than 2 times, so we can just test the length of this array, which is points, and if the length of this array is greater than or equal to 2, because the first click will be only a point, so we cannot connect this point with a line, but when we have 2 or more points, then we can connect those points with a line, right? So if this points array length is greater than 2, then we are going to just create a line between those points or the circles in our case. So I'm going to just call cv2 dot line method, and first argument here will be image. The second argument here will be the point 1, so the coordinate of point 1. Now we want to join the last 2 points, right? So we are going to just use this points array, and then to get the last value of an array we use -1 here. So here as an index we will give -1, which means the last element of an array, and then we will join the second last element of an array. So I'm going to just give this will be points variable, not print. So let's give the points variable, and then we are going to pass the -2 here, which will be the second last element. So last and second last element we want to join, and then the next argument will be the color. So let's say the color we want here is 255 comma 0 comma 0, and the next point will be the thickness. So we will give the thickness of 5 here, and then we will show this image using IamShow method. This code I have already shown you in the last video, so I will not explain what this code is doing. If you want to know more about this code, you can see the last video. And this time I will use the Numpy zeros array, which will be a black image. So let's run this script and let's see what happens. So I'm running this script, and now I click on some position on this image, and you can see this red circle is created. This circle is created using cv2.circle method, and because the radius is 3, the circle is very small, and because the thickness is -1, the circle is filled with the color which you provide here. Now we have said that if the point is only 1, then we don't want to create any line. If there are points which are 2 or more, then we want to connect those points with the line. So let's click here, and you can see point 1 and point 2 are connected with a line. I click here, and you can see the last and the second last points are connected with the line. That's why we have taken this -1 and -2 argument, which means the last element of the array and the second last element of the array. So when I click at any point, it will be now connected with this blue line. So this kind of line drawing you can use in satellite images where you want to connect 2 points together with the line. Now let's see the next example which I want to show you. So in the next example, what I want to do is I want to first of all read an image, and then I want to click on any point on the image, and then I want to show the color of the point on which I have clicked using a second window. So for this, instead of using the Numpy array, which is the black image, I will use the normal image, which is the lana.jpg image. And now I will just remove this code from here. So first of all, I want to read the BGR channels. So first of all, I will just declare these variables. First is blue, and we have the image. And in the last video, we have already seen how we can get the BGR channels, because we have the x coordinate and the y coordinate, and we also know that blue is the first channel. So we use the index 0 here to get the blue channel from this image at this coordinate, which is x and y. Same we will do for the green channel. So green, I am G, and then x comma y, and then the channel index will be 1 here, and then we will just get the red channel from this image. And now what we are going to do is we are going to just draw a circle on this point where you will click this mouse down button click event. So I'm going to just write cv2.circle, and now I will not explain the parameters, because you might already know what these parameters are. In the next line, what we are going to do is we are going to create a Numpy zeros image, and then we will pass our BGR channels which we got from the particular point on an image. So let's create an image. So I will just say my color image, and then we are going to just use np for Numpy, and then we will just call a zeros method here, and it takes 3 argument in the form of this list, which is the size of your image. Let's say this size will be 512 comma 512, and the channel will be 3 channels, and then the next argument will be the data type. So np dot u int 8. So we have a black image using this numpy zeros, and now we want to fill this image with the BGR colors which we got from the particular point of the image. So in the next line, what we are going to do is we are going to just use this variable, and then we are going to just write this kind of notation. This means we want to fill every channel or every point of this list, and then we will just pass our BGR channel values which we got from the image. So blue, green, and then the red channel values we are going to pass. So this will give us the BGR channel, which will be the color of the point where we have clicked. And now we have the new image with the color, so we can show this image using a new window with let's say this is the color window. Okay, so this is how you will get the new window with the color on which you have clicked. So let's run this code and let's see what happens. So I'm going to run this code, and you can see this is the image, which is the colored image. Let's see, I click on this point, and you can see the same color on which I have clicked is opened in the next window. Let's click here on the hat. You can see it's going to give you the same color on which I have clicked. Let's click on the eyes, and you will get the same color on which I have clicked. Let's see what happens when we just load a black image instead of this colored image. So I'm going to just use this numpy zeros image, which is the black image, and let's run this code. And now whenever I click on this, every time I click on any point, it will be the black color window which will open. So this is how you can use some examples to understand how mouse click events can work, and you can use them to develop your applications. In this video, we will see some of the basic and arithmetic operations on images using OpenCV. So let's get started. So here I have this code. Some of this code you already know. So you already know how to read the images using IamRead method, and then show it inside a window using IamShow method, and destroy all windows using this destroy all windows method. But this code in between is a little bit new. So let me explain line by line what this code does. So when you have this image using IamRead method or any other method, you can use these attributes like shape, size, and d type to get different values from this image. So image.shape is going to return a tuple which contains the number of rows, columns, and the number of channels in this image. The image.size will return the total number of pixels which are there inside the image, and image.dtype is going to return the data type of the image which you have obtained. Now here, if you want to split your image in 3 channels, then you can use cv2.split method and pass your image as an argument, and it's going to give you the BGR channel of your image. Now if you have BGR channels and you want to merge those BGR channel into an image, then you can use cv2.merge method and pass these BGR channels in the form of tuple, and it's going to give you the image which you can load using IamShow method. So let's run this code and let's see what we are getting using these attributes. So you can see this messy5.jpg image is loaded, and here you can see first of all the shape of the image. So the shape returns the number of rows, number of columns, and the number of channels. So number of rows here is 342, columns are 548, and number of channels are 3 here. The number of pixel which we have calculated using the size is this number, which is 562248, and the data type of an image is uint8. So sometimes you need to debug the data type of your image, and this attribute will be very useful in those cases when you need to debug if something is correct or wrong. And because we have splitted this method using this split and re-merged these BGR channels using this merge method, so we will at the end get the same image which we have at the beginning here in this code. So there is no change in the code. So once again, let me just load this image, and now let's talk about the ROI of an image. So ROI stands for region of interest. So sometimes you need to work with certain region of the image. So let's say you only want to work with the face here, or you only want to work with this ball. Okay, so this is called the region of interest, or in short form it's called ROI. So let's say we want to just work with this ball here. So this will be our region of interest or ROI, and I want to just copy this ball to other place in this picture. So I want to just copy this ball and place it on the other place, let's say somewhere here. Okay, so how we can do this? So I already have the coordinates of the ball, but you already know how to get the coordinates of some place in the image. We have already discussed this in our previous video, so I'm not going to show you how to obtain those coordinates. But let's say I have those coordinates of the ball, so I'm going to create a ball variable, and we have our image. So we will take our image, and there are certain Numpy indexing features which we can use here. So I'm going to just write 280:340, which is going to give you 1 point on the ball, which is the upper left hand side of this ball. And then we will give 330 here, colon 390, which is going to give us the bottom right hand corner of this ball. Okay, so now we have this ball. So this indexing is going to copy this ball, all the pixels of this ball, and then now we have the ball, so we can place this ball on any place on this messy image which we are reading. So what we can do is we can once again use img, and using those Numpy indexing features, we can place this ball at some other place. So let me just give those indexes here. So let me give 273:333. I have already tested this code, so that's why I know exactly where I want to place this ball. But if you are not sure where to place this ball, then you might have to first calculate or know the coordinates where you want to place this ball, and you already know how to find out the coordinates on an image, and you will be able to place that ROI or interest of region at some other place. So what I'm doing here is I have just copied the ball, and then I am placing the ball on this coordinate. Okay, so I just need to just assign our ball on this coordinate, and then this ball will be copied to this index on the image. So let's see what happens when we run the code. So now you can see we have copied this ball and we have placed this ball here on the image. So this is how you work with the ROI, or region of interest. Okay, so let me close this window. Now the next thing which I want to show here is how you can add two images. So for that I need one more image. So you can see in my project I have this messy 5.jpg, and I have this other image which is OpenCV -logo.png file, which is of the same size as the messy.jpg image. So I'm going to just write img2 and then once again cv2.imread method, and then I'm going to give the name of this file, which is OpenCV -logo.png file. Okay, so this is this file. So this file we are reading, and then there is a method called add. Okay, so we are going to use this method here. Let's use this method cv2 dot add, and this method I'm going to show you what it does in a moment. But this method takes two arguments. First is the first numpy array. So let me show you what this method do first of all. So this is the add method inside your cv2 package. You can also see the documentation on the opencv.org, and what it does is it calculates the pre-element sum of two arrays, or an array and a scalar. Okay, so here we can just pass our two arrays which we got from the imread method and pass here as the first and the second argument. So img and img2 are the 1 and 2 parameter, and there are some other parameters also, like output array, input array mask, and int, which is the data type, which are set by default, so we are not going to set them. So we are just using cv2.add method on these two images, and then I just want to assign the new image which we have added to a new variable. Let's say this is dst for destination image, and then we are going to just show this image using this imshow method. Okay, so we have two images. Let me show you those images one by one first of all. So this is the first image I have, and the second image is OpenCV-logo, which is like this one. Okay, so those two images we have, and when I run this code after adding those two images using add method, you will see, first of all, you will see this error. And why this error is coming? Because you will see here that the size of those two input is not matching. Okay, so in order to add two images, you need to have the images or the arrays of same size, and then only you will be able to add those two images. So let's resize those two images into a size which is common to both of them. So what we are going to do next is we are going to resize those images. So once again, I'm going to just use img variable. So what I get after the resizing, I will once again assign to this img variable, and there is a method called cv2.resize, and this helps us to resize the image. So first of all, we need to give the source which we want to resize, and then we are going to give the size which we want to get. So the number of columns and number of rows we can give here. Let's say we want to just resize this image to 512, 512, which is the number of rows and number of columns, right? Same we will do with the next image. So I am G2 and then once again CV2 dot resize, and then the source here will be image 2, and the size which we want here is again 512 comma 512 in the form of tuple. So we have resized this image and this image, which are of different sizes, to the same size. And now let's run the code once again, and now you will see that these two images are merged now. Okay, so you will be able to see the hand here and little bit foot, and here the ball of this image 1, which is messy 5, and then we have the second image, which is OpenCV, which is added to the first image. So this is how you can add two image using OpenCV. Now there is one more method which is called add weighted. Okay, so this add method is going to just add these two images, but if you want to add the weight, for example, you want to give the weight 90% to the first image and 10% to the second image, there is one more method. So let's go to the documentation once again, and there is this method called add weighted method. Okay, so this add weighted method takes several arguments. Here you can see first is the source of the first array, and second argument is the alpha value. Alpha is the weight which you want to give to the first image. Okay, the third argument is the source 2, so in our case this will be the image 2. The fourth argument is the beta. Beta is the weight which you want to give to the second image, right? So this weight you can give from 0 to 1, anything. And this gamma is the scalar value which you want to provide, and this second last parameter is the destination, and the last is the D type or the data type here. Okay, so this is the formula which this method is going to use. So source multiplied by alpha and source 2 multiplied by beta plus gamma. So this is the method which will be used using these arguments, or simply you will use this kind of method. So source multiplied by alpha plus source 2 multiplied by beta plus gamma, which is the scalar you can add to the image. Okay, so let's use this method. So I'm going to just copy this method and then comment this and go to the next line, and instead of using add, I'm going to use the add weighted method. Okay, so the first argument is the source, which is the first source, which is img in our case. Second argument is the weight. So first, this is the messy image, right? So we want to just give the weight here 90, or you can just give 0.9 here. And for the second image, we want to give the weight 0.1. Okay, so the sum of this weight and this weight will be 1. And also we are going to give the gamma value here as 0. So we don't want to add any scalar value to this add weighted method. So the next value here will be 0, which is the value of gamma. And let's run this code, and you can see now we have our messy image, which is dominant here because it has the weight 0.9, which is 90% of the 2, and the OpenCV image have the weight 0.1, which is 10% of the 2. Okay, so the OpenCV image is light and the messy image is a little bit dominant here. You can just give 0.5 and 0.5, so the weight of the two images will be the same, and now you will see those two images in the same domination. Okay, so 50-50%. Now let's say we want to increase this value of OpenCV to 0.8 and the messy image weight will be 0.2, then the dominant image here will be OpenCV, and in the background kind of thing you will see this messy image. So this is how you can add two images with their weight and the scalar. And that's it for this video. So in this video you have seen some of the basic operations on the images and some of the arithmetic operations on the images which you can do using OpenCV. In this video, we will talk about bitwise operations on images using Python and OpenCV. So bitwise operations can be very useful when working with masks. Masks are binary images that indicates the pixel in which an operation is to be performed. So let's see how we can perform bitwise operations on images. So to start with, I have here one image, which is image underscore one.png file, and let me show you the image also. So this image is half black and half white. Now the second image I'm creating using Numpy. So first of all, I've used np.zeros, and I'm just creating this image with the same dimension as this image underscore one is having. So 250 comma 500 is the dimension of this image, and the number of channels are 3, and this code is going to create a black image, as you might already know from our previous videos. Now this code is just creating a white rectangle inside the black image which we got from Numpy's zeros array. Okay, so this is the dimension of the rectangle inside your black image, and the color of the rectangle will be white because this is 255 comma 255 comma 255, and we are taking thickness as -1. That means your rectangle will be filled with white color. Now here I'm just showing both the images using IamShow method, and this code you might already know what this is doing from our previous videos. So let me run this code and let's see what happens first of all. So when we run this code, you will see first image is this one which we have created using the Numpy 0. So this is img1, and this is the black image, and we are just creating a white rectangle inside this Numpy 0's image. And this is the second image which is half black and half white. Now we want to perform some bitwise operations on these two images. So let's see how we can perform these bitwise operations on these two images. So to perform these bitwise operations, we have some methods inside the OpenCV library. So the first method will be bit and. So I'm going to just create a variable called bit and with let's say like this, and the method inside OpenCV is cv2.bitwise underscore and. So this bitwise underscore and takes several arguments, as you might see here: the source of the first image, the source of the second image, and the destination, which is none by default, and the mask, which is also optional. So we are going to just provide our images here. So I'm going to provide the img2 here first of all as the first argument, and the second image will be img1. And once we perform this bitwise AND operation on these two images, we are going to show the result in the form of window. So I'm going to create one more window which is cv2.imshow, and I'm going to name this window as let's say bit and the second argument will be our variable bit and, which we got from the operation bitwise and on these two images. So let's run this code once again and let's see what happens. So now as a result we have the third image. So let me just open all the images. So this is our first image, this is the second image, and the last one is the result, which is the bit and operation on these two images. So now you might already know how the logical AND works, But those of you who might not know how the logical AND works, let me show you the truth table of logical AND. So this is the truth table of logical AND, and if the input A and input B is 0, then we get the result 0. Okay, if input A and input B, either of them is 0, then also we get zeros, right? The result 1 we will only get when both the sources are 1. So A and B are 1, then only we will get a 1 in case of AND logic. So same AND logic will work here. So this is the zeros array, right? So we have created this black region from the zeros. So here in these images, black is performing as zeros and white part is performing as 1. So when 0 and 0, the result will be 0, right? So from this truth table we have seen when the input is 0 and 0, the result is 0. Same here we are seeing. So when the image is black and black, we get the result black. When the input is white and black, this means 0 and 1, the result will be once again 0 using the logical AND. But when the input will be white and white, that means 1 and 1, the result will be white, that means the 1. Okay, so the only region white here is the result of this white and this white, and the resulting image you can see here, and all the other part is black, because the AND operation on 0 and 0 is 0, and 0 and 1 is also 0. So this is how bitwise AND works. Let's see how bitwise OR and other operation works. So I'm going to just comment this code, and now we are going to just create the bitwise OR operation. So for that, I'm going to just instead of writing bit AND, I'm going to just write bit OR, and instead of bitwise AND, we are going to just write bitwise OR here, and then we will simply call this image using IAMShow method. So we are just calling here bit OR. Now let's run the code once again and let's see the result. So you can see the result here. So let's see the truth table. So in the logical OR, if only one input is 1, then the result will be 1. So either A or B is 1 or both are 1, then the result will be 1, and if both inputs are 0, then the result will be 0. So same you will be able to see here. So when the first source and the second source is 0, the result is 0. But when the first source and second source is 1 or white, the result is white. When the first source and the second source is 0 and 1 or black or white, the result is once again 1 or white here. Okay, so this is how the logical OR works on the image. Now let's see how the XOR operation work on those images. So I'm going to once again comment this code, and this time I'm going to just perform the XOR operation on these two images. And now we are going to run this code once again, and you will see this kind of result. So once again, let's see how the XOR logic works. So when both the inputs are 0 or both the inputs are 1, then we will get the 0, and if either A or B is 1, then only we will get the result 1. So same you will be able to see here. So when both first and second source is 0, the result is 0. When both the first and second source is 1, you can see here and here, the result is once again 0 here, right? But when the input is 0 and 1, result will be 1. And in this case also, the black and white will result in the white image, which is the logical XOR operation. So once again, let's close this. And now let me show you how the NOT operation work. So I'm going to just comment this code, and then I'm going to just use the bitwise NOT. So here bit NOT, let's say we will perform the bit NOT on the first image and the second image. So I'm going to just write bit NOT on the first image because it only takes one argument. Bit NOT is just the opposite of the source. So if you get the input 0, then the result will be 1. If you have the input 1, the result will be 0. So the opposite of the input. So let's perform this operation on image 1 and image 2. And let's comment this code, and we are going to just show these two result windows using the IamShow method. And also I need to change this name, otherwise we will face problems. And here also I haven't changed the name of these IamShow windows, so let's change the name of these windows, and let's run the code once again. And now you will get these results. So we will get the first result. So the first bit NOT 1 is the NOT of the first image, and bit NOT 2 is the NOT operation on the second image. So you can see wherever we have white, we got black, and wherever we have black, we got white. So just the opposite of the input. Here also, wherever we have the black region, we got the white image here, and wherever we have the white pixel, we got the black pixel. So this is how bitwise NOT operation works on the images. So these are some of the bitwise operations which you can perform on your images. And as I said, bitwise operations can be very useful when working with masks, which we will see in the later videos. In this video, we will talk about track bars in OpenCV. Now, track bars are really useful whenever you want to change some value in your image dynamically at runtime. So let's see how we can use track bars in OpenCV. Now, to start with, I have this simple code which you might know what it does. So first of all, I have imported CV2 as a CV, and then I'm creating an image using the Numpy zeros array with these dimensions, and then I'm creating a named window with the name image. So this might seem new to you because I haven't created a named window in the previous video. So the named window you can use to create a window with a name, and this time we have given the named window name as image. Now in this while loop, we are just using this IamShow method to call this window and then loading this image inside this named window. Now you might already know what this code does. It just waits for the key, and if the key is escape key, then we will break out of this loop. And in the last, we are just destroying all the windows which we have created. Now in order to create a tracked bar, you just need to use CV and then call a method called create track bar. Now the first argument here you need to give is the track bar name, because you can create multiple track bars in your image window. That's why you need to provide a name which is unique to this track bar. So I'm going to just give the name to my track bar as B, because what I want to do is I want to change the BGR values of the image using the track bar. So the first track bar will change the B channel values. That's why this first argument is the track bar name, which is B, and the second argument here we will give is the name of the window. So that is why we have created this named window, so that we can provide the name of the window, which is image in this case, and that is how we know that in which window we need to add the track bar. So in the image window, which is this one, we want to add the B track bar. Now the third argument here will be the value, which is the initial value at which your track bar is set, and the next value here will be the count, which is the final value you want to set for your track bar. Now there is this last thing which we want to set here, and this is the callback function, which will be called whenever your track bar value changes. So here, for example, I'm going to create a callback function called nothing, and this callback function definition or signature I'm going to create here. So we can just create a callback function with a name nothing, and this function can take this value x, and this is the value of the current position of your track bar. So we will see what it does little bit later, and what we are going to do is we are going to just print the value of x, so we will know the current position if this track bar is changed. So this is the callback function which will be called whenever your track bar value changes. Same we will do with the other track bars. So we will create the 3 track bars in the same window with the name B, and the next track bar name will be the G, and the last track bar name will be R. Okay, so this will be capital R. So now let's run this code and let's see what happens when we run this code. So I'm going to right click and run this script, and you can see here inside this named window with the name image, we have this black image which we have created using Numpy zeros array, and now we have 3 track bars here with BGR names. So these track bar values you can change using this scroller, and as you can see here, let me show you in this terminal, whenever you change the value of any bar, the corresponding value will be shown here using this callback function, and inside this callback function we have the print statement. Okay, so as I said, whenever you change this value, this callback function is called and it will print the value of the current track bar. Okay, so for this functionality, what we want to do is we want to get the current position of the track bar, and because we can change the value of BGR channels from 0 to 255, that's why I have given the range between 0 to 255 to the track bars also, so that you can change these BGR channel values. So now in order to get the current value of your track bar, first of all we will just check the value of the B track bar. So we will just use cv dot get track bar position, which is this method, get track bar POS, and then we just need to give the name of our track bar. So let's say we want to check the position of track bar B, then we will just say we want to have this track bar position with the name B, and the second argument here will be the name of your window. So in which window this track bar is present. So our track bar is present inside the image window, right? So same we will do for the G and R values also. Now we have the values of B, G, R channels from the track bar. So now we want to set these values to our image. So what we can do here is we can just write, for example, I am G. Inside these square brackets, you can just give this kind of notation and then give the BGR channel values. So I'm going to just write B comma G comma R. That means we want to set the current B, G, R values to this image. So let's run this code and let's see what happens now. So I'm going to run this code, and now when I change the blue channel values, you can see this image becomes blue colored, right? Let's bring it to 0 once again, and now let's change the value of G. So you can see this image color is changing to green, and then we can try changing the red color, and you can see when it goes to 255, the color of the image is red. You can change the values of different track bars, and the corresponding color will be displayed in this window here, right? So you can see the color is changing. You can change any track bar here. One more example I want to give here is how to add a switch using a track bar. So for that, I'm going to use one variable called switch, and then here I can add first of all the name of the switch. And in the next line we will once again call cv2 dot create track bar with the name switch. Okay, so now the name of our track bar will be switch. So now we have added one more track bar to our named window, and now here we will get the current position of this switch track bar. So I'm going to name it as S, and the name of the window is switch. So we will just give the first argument of this get track bar position as switch. Okay, and the window name is image itself. So now we can add some condition here. So let's say if this position of the switch which we have, if this position is equal to 0, because we only have 0 and 1 in this last track bar. So if this position is equal to 0, what we want to do is we want to set I am G, and then in the square bracket this colon, and we don't want to change any value, so we will say that I am G this square bracket colon is equal to 0, which means that we don't want to do anything. Or in the other condition, which is when your track bar is at position 1, then only we want to change the BGR channel of the image. Okay, so let's run this code and let's see what happens. So I'm going to run this code, and now you can see the position of this track bar switch is 0, and when I change it to 1, so let's change this position to 1, you can see the value to 1. And when this position is at 0, you can change anything here, any track bar, nothing happens, because this condition is met, which means that we don't want to do anything. As soon as we change the switch to 1, that means we want to change the BGR values. You can see this color is changed inside the image. So the 0 is just like off switch, so we don't want to change any color, and 1 is like on switch, so when it's 1, the value of RBG channels can be changed. Now I want to give one more example of track bar to use, so that's why I have created one more file, which is Python OpenCV track bar example 2, and this time I'm going to use just 2 track bars here, so that's why I'm going to delete some of the code here. So using the first track bar, let's say I want to just change some values inside our image and I want to print that value on that image. So let's say now our range is between 10 to 400. Okay, so the lower range is 10 and the upper range is 400, and using this track bar I want to print the current value on our image, and also I want to have a switch which I can toggle, and I want to change the color of the image from the colored value or colored image to the grayscale image. So now our switch is between color to the grayscale image. Now in here what we want to do is we want to just assign this IAmShow value to the image variable itself, and then we want to get the current position of the track bar, so we will use this method to get the current position of the track bar, and I'm going to name this current position as POS variable, and the name of this track bar, let's change this name to something else. Let's say CP for current position, and also here CP for the current position, and the name of the named window is image itself, so we are not changing it. So now we have the current position. So first of all we will just create the font, and then we will just use the cv dot put text method. You already know what this method does. It just print the text on your image, and then we will provide the parameters. First argument is the image, the second argument is the value which we get from the track bar, so this is the position, and because it's a number we need to convert it to the string using str method, and then the position at which you want to show this text. So let's say it's 50, 150, and then next is the font, so I'm going to just give the font, and then the next value is the font scale, which is 4, and the next value is for the color of the text. So let's say the color here will be 0, 0, 255, and this should be cv dot font Hershey complex. Let's change this font also. Let's say this is just the simplex font. Okay, so this code is going to just print the current position of the track bar on your image, and then inside this condition what we want to do is we want to get the switch value. So let's use this s variable and then get the current position of the switch using this switch name from the image window, and then if the switch is at 0 position then we want to do nothing, so we will just pass this situation, and in case the value of this switch is 1, then what we want to do is we want to change the image value from color to the grayscale value, right? So we can just write cv dot cvt color, and the first argument is the image which we are loading, and the second argument is cv dot color bgr to gray, which is to convert this colored image to grayscale image. But you can see here we are just creating a black colored image, and in our project we also have this image. So let's read this image. So I'm going to just write cv dot im read and then give the name of the image, which is lena dot jpg. So this is our colored image, and this way we will be able to see the change of color to gray scale image in a better way. So let's run this code and let's see what happens, and you can see image appears and disappears, and there is an error. So let's see what is the error. So the error here is coming from this line. So we need to read this image inside the while loop. Okay, so this is why our error is coming, and at the last we want to load this image after this if condition. Okay, so now let's run this code once again, and you can see this value is printed on our image, which is 10, which is the value of CP, and if we change this value, it is changing on our image also, right? And once we change this 0 to 1, then our image is converted from colored image to the grayscale image. You can also change the font size here. For example, let's say it's 6 here, and the thickness also, if you want to change, you can change it using this parameter. Let's say it's 10, and let's run this code once again. You can see the thickness and the size of the font is changed, and you can see this value in a better way. Okay, so this is how you can use track bars in OpenCV. In this video, we will see how we can perform object detection using HSV color space. Now we have already seen how to work with BGR or colored images or grayscale images, and we have already seen how we can convert from colored images to grayscale images. So there are more than 150 color space conversion methods in OpenCV, and one of them is colored image to HSV image. Now what is HSV color space? So HSV stands for hue, saturation, value. So H stands for hue, S for saturation, and V for the value. Now generally RGB in RGB color space are all correlated to the color luminance. That is what we loosely call intensity. In other words, we cannot separate color information from luminance. So HSV or hue saturation value is used to separate image luminance from color information. So this makes it easier when we are working on or we need luminance in our images. That is why generally we use HSV in the situation where color description plays a very important role. Now, as I said, HSV stands for hue, saturation, and value. But what is the meaning of each and every single word in HSV? Now, HSV is also known as the hexagon color model. So this color space can be described in this kind of cylindrical cone model, where hue is this circular angle which varies from 0 to 360, and hence just by selecting the range of hue you can select any color. So you can see different colors are available at different angles. So these colors are basically red, yellow, green, cyan, blue, and magenta. So hue is this angle in this cylindrical cone. Now we have saturation. So the saturation is amount of color, that is the depth of pigment or the dominance of hue, and this value is described from the center towards the outer layer of this cylindrical cone. So here you can see at the center this saturation start at 0 and it can go up to 1 at the end of this cylindrical cone, and this saturation can be increased from 0 to 100%. Similarly, the value is basically the brightness of the color. So this brightness can be increased from 0 to 1, from the bottom of the cone to the top of the cone. So all these three values, hue, saturation, and value, can be used to pick any color, as we can do with the BGR color space. So this is the brief introduction about HSV color space. And now let's see how we can use this HSV color space to detect an object in an image. So here I have this simple code to load an image using imRead method and show it inside a window. So by now you might already know how this code works. So let's run this code and let's see what does this code do. So I have this image which is called smarties.png, and here are some circles in different colors. So we have blue circles or green or red, orange and brown circles here inside this image. So let's say we somehow want to detect only the blue circles or balls or green circles or balls. How can we just detect only these balls? Let's say we just want to detect the green balls. How can we achieve this using OpenCV? We are going to see this using this HSV object detection. And here we have one more window, which is the tracking window, which is coming from this code, which is cv2.named window, and the name of the window is tracking. So this tracking window we are going to use little bit later when we will add the track bars to our image. But let's say we want to use this image and detect these colored balls. So first of all, after this image is read, what we want to do is we want to convert our colored image into a HSV image. And by now you might already guess how to convert an image. You can just write HSV is equal to cv2.cvt color, and then your frame name, which is frame in this case, and then cv2 dot whatever color space you want to convert from and whatever color space you want to convert to. So you can just write color underscore bgr to HSV. So this is the property we are going to use. Now in the next step, we will threshold the HSV image for a range of blue color. So we are going to just define L underscore B for lower blue color, and then we are going to use the Numpy array, so np dot array, and inside this array we are going to define the lower range of blue color. Now by experience I know that these HSV value for lower blue color will be 110, 50, 50, right? But you might not have every time the idea what is the lower color range or the upper color range of some color. So that is why later in this video we will use the track bar in order to perfectly define the lower and upper values for this HSV color space, right? So right now I'm just going with my experience. So for the upper value I'm going to define the next variable, which is ub is equal to np dot array, and then once again I'm going to define these three color channels, which is 130, 255, 255. So this will be the upper limit for the blue color for our HSV image. Now in the next step, what we are going to do is we are going to threshold the HSV image to get only the blue color, let's say. So I'm going to just define a variable called mask here, and then I'm going to use cv2 dot in range method, where I will provide first of all my HSV variable or image, and then I will provide the upper and lower range for this function. So my lower range is this numpy array for the blue color. So I'm going to just say L underscore B is my lower range and U underscore B is my upper range. Now we have already seen how we can use bitwise AND or bitwise operations on images. So what we are going to do next is we are going to define a variable called res, and then we will just call cv2 dot bitwise AND to mask the original image. So here the first value will be our frame, which is the colored frame, right? So this is the frame which we have read from this image, which is the Smarties image. So this is the source 1. Source 2 will be the same. So the frame itself will be the source 2. And what we want to do is we want to provide the mask of the lower blue color and the upper blue color values, right? So here we can just say mask is equal to whatever mask variable we have created. So this is the attribute we can set in order to apply the mask for the lower blue value and the upper blue values. So once we have this result frame, what we can do is we can use this cv2.imShow method in order to show the mask, let's say. So we are going to show the mask and we are going to show the result using res variable. So this is going to open 3 windows, and let's see what happens when we run this code. So we are going to run this code and this opens 3 windows here. And now you can see the mask first of all. So we are just detecting the blue colored balls using this mask. That's why we have defined the lower boundation of the blue color and the upper boundation of the blue color, right? So that's why it's only detecting, you can see the blue ball is here, here and here, and here also you can see the mask also detects only the blue values here, right? And then in the result you can see when we have applied this mask and we have masked all the other things other than the blue colored ball, you can see only the blue balls here. So the same method you can apply to detect any other colored ball from this image. Now, as I said, it's not easy to detect these lower and upper boundation for the colors. So that's why you can use the track bar for adjusting these lower and upper boundation of any color. So for that, what we are going to do is, first of all, we will create a named window, and then we are going to create a new window which we will use to adjust the lower and upper boundation of HSV values. So now I'm going to just use cv2 dot. We have already seen how to create a track bar, so I'm not going to explain in detail how this works, but let's say this track bar name is lower hue for LH. Okay, so this is the lower hue value, and then the name of the window, which is tracking, which is this one. So we are going to provide the name of the window, and the next argument will be the starting and the ending value. So we are going to define the start value 0 and the end value, let's say we are going to define the 255 here. Okay, and the last thing we want to give here is the callback function, which I have already created, which is this function, which is just doing nothing. We are going to just provide this callback function as a dummy function, so it's not going to do anything. So this is the track bar for the lower hue value. Similarly, we are going to define the track bar for lower saturation and lower value, and upper saturation, upper value, and upper hue. Okay, so this will be lower saturation, this will be lower value, and then this will be UH, which is upper hue, and then this will be US for upper saturation value, and this will be upper value, right? So HSV lower values and HSV upper values. So here we are going to set the initial value for the upper value. So let's say everything is set to the maximum, so 255, 255 and 255 here. Okay, so the lower values are set to zeros and upper values will be set to 255. Now you already know how to get the values from a track bar. So you can use, for example, L_H for the lower hue values is equal to cv2 dot get track bar position. So just use get track bar position method, and then first of all give the name of the track bar from which you want to get the position. So let's say we want to get the position from the LH track bar, and then the name of the window which is tracking in our case. So here is the second argument. And similarly, what we are going to do is we are going to define the other lower values and upper values. So and also the name of your track bars. So once you have the values of lower HSV and upper HSV, you can provide these values here in place of these static values. So first element of this array will be LH, and then the LS variable, and then the LV variables. Similarly, for the upper boundation, we will provide these three upper boundation variables. And now when we will run our code, let's see what happens. So we are running our code, and you can see these windows, these three windows. One is the mask, other is the result, and the third one is the frame. And we also have these track bars in order to change the value of lower and upper HSV values. So first of all, let's set this mask for the blue color. So I'm going to just move it to 110 as we have done in the last step, and then this will be around 50, and this also will be around 50. Okay, so let's move it to 50, and upper value here will be around 130, right? So you can see once again, using this track bar, it's easier to adjust these lower and upper boundation. And now you can see all the three blue colored balls. So you can refine this object detection by moving these track bars little bit left or little bit right. You can see here. Now let's adjust this value to detect some other balls. So let's say we want to detect the green balls. So let's see what happens when we just change the saturation values here, and you can see now you almost see the green values, and the blue color is almost disappearing. So you can see now there are only green balls which are detected, and all the other balls are masked. So you just need to play with this track bar for the lower HSV values and the upper HSV values, and you will be able to detect the object, whatever colored object you want to detect from the image. Now this is the object detection from the image. Similarly, we can use the same method in order to track an object from a live video. So I'm going to just escape to just close all the windows. And in order to change this code for the video input, what we can do here is we can just add this code. So we are going to just add the cap variable, which is the capture variable, is equal to cv2 dot video capture. So we are going to use this one, and we are going to capture the video from our default camera, which is at the index 0. And then you already know how we can read the values from the camera input. So I'm going to just comment this code, and instead of reading the image, what we are going to do is we are going to write underscore comma frame is equal to cap dot read, which is going to read the frames from your default camera. And at the end, when you are done playing with your images, you can just destroy this cap using the release method. So you can just write cap dot release, which is going to release all the cameras you are just capturing, right? So now this is the 3-line code you need to use in order to capture the camera input and then track any object of any color. So I'm going to run this code now, and you can see I'm just holding a blue colored object here, and I'm moving this object on the left and right, and you can see only blue colored object is detected and every other frame value is masked. So this is how you can do the object tracking of any color using the HSV color space. So you can see the real image which is captured from the camera, and then the mask, and then the result of the mask and the real image in this blue colored object tracking. So this is how you can do object detection and object tracking using HSV color space. In this video, we will see how we can perform simple thresholding on images using OpenCV. So first of all, what is thresholding? So thresholding is a very popular segmentation technique used for separating an object from its background. The process of thresholding involves comparing each pixel of an image with a predefined threshold value. And this type of comparison of each pixel of an image to a threshold value divides all the pixels of the input image into two groups. So the first group involves pixels having intensity value lower than the threshold value, and the second group involves the pixels having intensity value greater than the threshold value. And using the different thresholding techniques which are available in OpenCV, we can give different values to these pixels which are higher than the threshold value and which have the intensity lower than the threshold value. So let's see how we can use simple thresholding techniques on an image. So to start with, I have this simple code which loads an image on a window, and this image is called gradient.png. So let me show you how this image looks like. So this image looks like this. So as you can see in this image, we have on the left hand side the black values, and when we gradually move from left to right, we move towards the white value. So on the left hand side, the pixel value are closer to 0, and on the right hand side, the pixel values are closer to 255. So now we are going to just involve some thresholding techniques, and we will see how this image is affected by the thresholding techniques. So first of all, what we are going to do is we are going to define two variables. One is underscore, because the result of the thresholding gives two results. One is RET value, and the second is the thresholded value of an image. So I'm going to just say the second value which is given by the thresholding technique is th1 is equal to cv dot threshold, and this threshold method takes several values. The first is the source, so our source is image. The second is the threshold value. So as we have seen that our image have on the left hand side 0 pixel value, and when we move towards the right, its pixel value increases to 255, right? So let's say our threshold here is 127, and the maximum value of the threshold is 255, which is the white color on the right hand side. And then the fourth value here will be the threshold type. So there are several threshold type in simple thresholding. We are going to see them one by one. So the first thresholding type is cv2 dot thresh binary. So first of all, let me show you how the result looks like, and then I will explain what does this thresh binary type does. So what we are going to do is we are going to use one more cv2.imShow method to show this thresholded value into a new window. So we are going to just show this value into a new window, and we already have the original image in the image window. So let's run this code and let's see what happens. So you can see in this binary thresholding, we are comparing each and every pixel of this original image to 127. And if the value of the pixel is less than 127, the value is assigned to 0. And if the value of the pixel is greater than 127, the pixel value is assigned 255, that means white. So if the value of the pixel is 0, it will look black, and if the value of the pixel is 255, it will look white. So this is how binary thresholding works, and by the name itself you can understand that this is just a binary thresholding. So it's either 0 or 1. Now let's see the other type of thresholding technique. So now I will just change the name of this variable as th2, and the next type of thresholding is called thresholding binary inverse. And as the name suggests, the thresholding binary inverse is going to give the inverse result of what you get from the thresh binary. So I'm going to once again use the imShow method to show the result of this thresholding binary inverse value, and let's run the code and let's see what happens. So this is the original image, and then we have the thresholding 1 image and the thresholding inverse image. So this image you got from the first thresholding, which is by using thresh binary, and the second image you got from this method, which is thresh binary inverse. And this thresh binary inverse image is just the inverse of what you get using the thresh binary. So if the pixel value is lower than 127, which is our threshold, the pixel is assigned 255. Otherwise, if the value is greater than 127, then the pixel value is assigned 0, which is the inverse of what we got in the previous step. Now let's change this threshold to, let's say, 50, and here also let's say we change this threshold to 200, and let's see how this result changes when we change the threshold value. So I'm going to run this code once again, and you can see this is the result of thresh binary. And now because our threshold is up to 50, that's why our result is like this. So until the pixel value is 50, it's black. Otherwise, if the pixel value is greater than 50, it's going to give you the white pixel value, and the thresh binary inverse is going to give you the inverse value of what you get in the thresh binary step. So I'm going to once again just close these windows, and let's see the next thresholding type. So I'm going to name my variable as th3. So the next thresholding type is called thresh trunk. So this is this type, and let's first of all see what is the result of this thresholding technique, and then I'm going to explain what it does. So we are going to just show this thresholded image into a new window and run the code, and now we have the result. So let's move it like this, and we have here the original image, and the result of the thresh trunk is this th3. So here what happens is, up to the threshold, the value of the pixels will not be changed. So up to 200, because our threshold is up to 200, so when the pixel value is up to 200, the pixel value will not change, and after the threshold, which is 200, the pixel value will remain the same, which is 200. So from here to here, the pixel value will remain 200. Let's change this threshold to some other value, let's say 127, and then let's run this code, and you will see that now from black to 127 pixel value, the value of this image will not change. So original image up to half is the same, and after the pixel value 127, the value remains 127. Okay, so the pixel intensity value will remain 127 until the end. So if the value is greater than 127, the value will remain 127, and if the pixel value is lesser than 127, then the pixel value will remain unchanged. So this is how the trash trunk works. And let's see the other method, which is, let's say, th4, and this is the method which is called trash20. So we are going to just use trash20, and then we are going to open this th4 into a new window, and let's run this code and let's see what happens. So now we have this result. Let's move this to the left, and the result of the trash20 is this one. So in trash20 thresholding, whenever your pixel value is lesser than threshold, the value assigned to pixel will be 0. Okay, so when the pixel value is lesser than the threshold, the pixel value is assigned to 0. That's why you can see half of the image is black. And when the pixel value is greater than 127, which is our threshold value, the image or pixel value will remain the same. So after 127, all the pixels will remain the same. Let's see the other technique, which is called trash20 inverse, which you already understood, I think, what it does. So this is trash20 inverse, and we can just change this variable name to th5, and here we can just open it into a new window, and I'm going to run this code once again. Let me move this here and the result here. So you can see this trash20 inverse is just the opposite of the trash20. So if the value of the pixel is greater than the threshold value, which is 127, the value will be assigned to 0. Otherwise, if the value of the pixel is lesser than threshold, the value of the pixel will remain the same. So this is how some of the simple thresholding techniques works in OpenCV. In the last video, we have seen how we can perform simple thresholding in OpenCV using Python using various thresholding techniques. So we have used trash binary inverse, trash trunk, trash20, trash20 inverse. So these were all the simple thresholding techniques. Now in these thresholding techniques, we were setting a global value of our threshold. So in this example, for example, here the global value of threshold is 50, here 200, here 127. So we were setting in simple thresholding the global value, and this means that it is same for all the pixels in the image. Now in this video, we are going to learn how to use adaptive thresholding. So adaptive thresholding is the method where the threshold value is calculated for the smaller region. So the threshold is not global for every pixel, but it's calculated for a smaller region, and therefore there will be different threshold value for different regions. Now, why do we need this type of adaptive thresholding? So using simple thresholding might not be a good idea in all the conditions. So there might be conditions where the image has different lighting conditions in different regions, and in those cases where the lighting conditions in the images varies from point to point, in those cases we might want to use adaptive thresholding. So as I said, adaptive thresholding calculates the threshold for a smaller region of images. So we get different thresholding values for different regions of the same image, and as a result, adaptive thresholding gives us better results for images with varying illumination. So let me show you the problem with simple thresholding for the image which have different illumination at different regions. So I have this image called sudoku.png which I'm loading using imRead method, and then I'm just showing this image using imShow method. And then let's use the simple thresholding technique, which is thresh binary for this, and we have set the global threshold value of 127 here, and then we will see the result after this threshold is applied to the image. So I'm going to run this program and let's see what happens. So this is our original image, and then this is the result which we got. So in the result you can see when we apply a same global threshold value, some of the region of this image is black and other region of this image is visible, right? So because the image have different illumination value at different regions, that's why we see half of the image which have the good illumination, and we don't see half of the image which doesn't have the better illumination. So in that case, it's a better idea to use adaptive thresholding. So let's see how we can use adaptive thresholding. So here what I'm going to do is I'm going to declare a variable called th2, and then we use cv.adaptive threshold. So this is the method which we are going to use for performing adaptive thresholding, and this takes few arguments. So first is the source. So our source is the image variable. Now the second parameter here is the max value. So the max value is the non-zero value assigned to the pixels for which the condition is satisfied. So in our case, the maximum value which we can provide to a pixel is 255, and we cannot go more than that, right? Now the third parameter here is the adaptive method. So this adaptive method is going to decide how the thresholding value is calculated, and there are two types of adaptive methods which we can use. So the first method is called cv2.adaptive thresh mean c. So what is the meaning of this adaptive thresh mean underscore c? So using this method, the threshold value is the mean of the neighborhood area, and here is the documentation of these two methods. So adaptive thresh mean c gives us the threshold value using this function, and this is going to give us the mean of the block size multiplied by block size neighborhood of x comma y minus c, which is the constant. And the second adaptive threshold type is this one, which is adaptive thresh Gaussian underscore c. And in this adaptive thresholding, the threshold value is the weighted sum of neighborhood values where weights are the Gaussian window. So let's use the first adaptive method, which is the adaptive thresh mean underscore c. Now the next parameter here is the threshold type. So the threshold type which we are going to use is the thresh binary, which we have also seen in the last video also. And then the next value is the block size. So block size decides the size of the neighborhood area. So here we are going to give the block size 11, and the next parameter here is the value of C. So we have seen that we need to give the value of C also when we use the adaptive thresh mean C and adaptive thresh Gaussian C. So this is the value of C which we are going to give, and C is just a constant which is subtracted from the mean in the case of this adaptive thresh mean method, or the weighted mean in the case of Gaussian adaptive threshold. Okay, so constant we are going to give here is 2, and now what we are going to do is we are going to just load this image which we got after applying this adaptive thresholding, and let's just comment the other window. So we will just see the original image and the adaptive thresholding result. So I'm going to run this code, and you can see the original image here and the result of adaptive thresholding, which looks much better than the simple thresholding technique. So let's uncomment this also. So I'm going to uncomment this, so we will see all the three results at the same time. So this is the original image, and you can see the simple thresholding gives us this value using the global threshold of 127, and adaptive thresholding gives us this value or this image which is much more readable than the simple thresholding technique image. So this is how you can use adaptive thresh mean C method. In a same way, we are going to use the other adaptive thresholding technique, which is called adaptive thresh Gaussian C. So instead of this, we are going to use adaptive thresh Gaussian C, and then all the parameters we are going to leave as same, and let's load the result of this type of thresholding which is stored in th3. So let's run this code and let's see what happens. So we have already seen this image which is the simple thresholding. This is the result of the adaptive thresholding mean C, and this is the result of adaptive thresholding Gaussian underscore C. So both of the result looks good because the adaptive thresholding algorithm calculates the thresholding value for different regions. So the thresholding value is not global for each and every pixel of the image. And we have seen the two adaptive methods which are available in adaptive thresholding. So in this way you can use adaptive thresholding in OpenCV. In this video we will talk about a library called matplotlib which you can use with OpenCV images. So first of all, what is matplotlib? So matplotlib is a plotting library for Python which gives you a wide variety of plotting methods. And on the official website, which is matplotlib.org, you can see matplotlib is a Python 2D plotting library which produces publication quality figures. So it's primarily a 2D plotting library, but it's widely used with OpenCV to display graphs and images and histograms. So we will see how we can use matplotlib with OpenCV. It's also written here that for simple plotting, the pyplot module provides a MATLAB-like interface. So first of all, let's see how we can install matplotlib, and then we are going to see how to use matplotlib with OpenCV. So to install matplotlib using pip, you just need to open your terminal and then just give this command, which is pip install matplotlib, and then press enter, and in some seconds this matplotlib library will be installed using pip. So now you can see matplotlib is installed on my Windows operating system, and to check it I'm going to just give the Python command, and here I'm going to import matplotlib. So I'm going to just write from matplotlib import pyplot as plt. Okay, and then press enter. And if this import doesn't give you any error, that means it's imported successfully and you can start using matplotlib. Now, as we are using PyCharm IDE, let me show you how you can install matplotlib on PyCharm. So just open your PyCharm IDE and then here just click on File and then Settings and then go to Project : your project name. My project name is OpenCV Examples, and then click on Interpreter, and you can see other packages are already there, and we just need to install the matplotlib package. So just type here in the search matplotlib and you will be able to find matplotlib here in the result. So just click on matplotlib and then just click on the install package. So I'm going to just click on the install package, and in some seconds matplotlib library will be installed in your PyCharm IDE. So you can see this message which says package matplotlib installed successfully. That means we can close this window, and then you will be able to see matplotlib is available in your project interpreter. So everything is fine, and I'm going to just close this, and now I will be able to import matplotlib. So I'm going to just write from matplotlib import pyplot as plt. Now, in order to show the image which you read using the OpenCV imRead method, you can use this code. So just write plt dot imshow. So there is also a method inside your pyplot library which is available inside matplotlib, and this method you can use to show the image which you have read from the OpenCV imRead method. So for now, just write this kind of code, and to show the matplotlib window you just need to write plt.show. So this is going to show this image using the matplotlib library. So we are opening this image using the OpenCV imshow window as well as matplotlib window also. So let's run this code and let's see what's the result which we are getting. So you can see this is the image which is loaded using the matplotlib, and this was our original image which is loaded using the OpenCV library, and straight away you can see some difference. So this is the original image which is the colored image, and in the matplotlib window we also want the same result, but it's giving us the different result. And the reason behind this is OpenCV reads the image in the BGR format and the matplotlib reads the image in the RBG format. So in order to show this kind of colored window using matplotlib, you need to convert your image from BGR to RBG, and then only you will be able to see this kind of colored image using matplotlib. So I'm going to just close these windows, and now after I'm showing this image using the cv2 imshow method, I'm going to convert this image. So I'm going to just write img is equal to cv2 dot cvt color, and then I'm going to convert this image from BGR image. So I'm going to just write cv2 dot color underscore BGR to RGB. Okay, so our matplotlib library shows the image in the RGB format, and the OpenCV reads the image in BGR format. So now we have converted our image from BGR to RGB image, and now we are showing this image using the matplotlib. And let's run this code and let's see what happens now. So now when we run this code, you see both the image looks the same, right? Now let's see the advantages of using matplotlib. So you can see this is quite static window, but when you see in matplotlib, when you hover over this image, you can see x and y coordinates of the mouse point, and this is helpful. You can also save this image in the form of a PNG file, so you can just press this and save this image wherever you want. You can also zoom this image if this feature is available. There is also configuration subplots options, so you can just increase these values left, bottom, wherever you want to place your image. You can do that. These are some options which are available here. You can also reset these options, and you can see the coordinates here. So because matplotlib is primarily a 2D plotting library, so you can see the x coordinates and y coordinates, and because this image is about 512 by 512 pixels, that's why here it's showing 0 to 512, and here also on the y-axis 0 to 512. So this is how you can load your image using matplotlib. And now I'm going to show you one more thing, and this is when you write plt.xtics here, and then when you pass empty array here, which is empty square bracket, comma plt.ytics, and also here you pass empty array. This is going to hide the tick value on x and y axis. So now when I run this code, and you can see now that these x ticks and y ticks on x and y axis are gone. So let me just comment this out once again, and you will be able to see this x and y coordinates here on the image. And when you use this code, which is to hide the ticks on the x and y axis, then you will see the image without these x and y axis ticks. So if you remember, in the last video we have seen how to use simple thresholding in OpenCV, and we were using 6 windows to show these 6 different images using OpenCV. Now let's say you want to show all these 6 windows in one matplotlib window. How you can do it with the use of matplotlib, I'm going to show you. So first of all, we are going to import matplotlib, import pyplot as plt, and then what we are going to do is we are going to define the titles, and then we are going to define these 6 different titles for 6 different images. So first one is our original image, second was the trash binary, third was trash binary inverse, fourth was trunk, fifth was to 0, and sixth was to 0 inverse. In the same way, we are going to define a variable called images, and inside this square bracket we are going to pass first of all our original image, and then th1 comma th2 comma th3 comma th4 comma th5. Okay, so these are the 6 value we want to show, and these are the 6 titles of these images. And now we are going to use the for loop. So for I in x range, so using the Python x range, we are going to just iterate over these 6 values. So I'm going to just write x range, and then the range we are going to provide here is 6, and then inside this for loop we are going to just call plt, and we are going to call a method called subplot. Okay, and this subplot method takes few arguments. So first argument is the number of rows which we want to show in our matplotlib plot. So because we have 6 images, so we are going to divide these images into 2 rows and 3 columns. So the first argument here is the number of rows, and the second argument here is the number of columns, and the third argument here will be the index of the image. So the index of the image will be I plus 1, and then we are going to write comma plt dot im show. So this is going to show this image and the index of the image. So we are going to just write images and then square bracket I. So this is going to give you a particular image at index I, and then we want to show this image as a grayscale image. So anyway, when you use thresholding, you use the grayscale image, so you just need to write gray here. Then we are going to show the titles of these images. So we are going to just write plt dot title, and then this title method takes the title name which we are getting using this titles array, and then at the index I, this is going to give you the title name which we have declared in this title array. And at last, if you don't want to show the ticks on the images, you can give these two methods, which is plt dot xticks and the argument here is the empty list, and also plt dot yticks and the argument is the empty list. And at the end, what we want to do is, instead of using this kind of code, we just want to show our window. So we can just say plt dot show, and this is showing us this error unresolved reference. Yes, so this is when you are using Python 2, but in Python 3 this x range is changed to a method called range, and that's why it was giving us the error. So let's run this script once again, and you can see 6 different results and 6 different titles. So these are all the titles which are shown here, and then the result are shown under these titles. So using matplotlib, you can include multiple images into one window, and this is very useful when you want to show multiple image at the same time in the same window. So this is how you can use matplotlib library with OpenCV images, and there is a lot of things which you can do with matplotlib. So if you want to learn more, you can just go to the official website, which is matplotlib.org, and then you will be able to see more documentation here. In this video, we are going to discuss about morphological transformations in OpenCV. So we will discuss different morphological operations like erosion, dilation, opening and closing methods, etc. But first of all, what are morphological transformations? So morphological transformations are some simple operations based on the image shape. Now, morphological transformation is normally performed on a binary image, and when we perform morphological transformation, there are two things which are required. First is the original image, and second is called a structuring element or a kernel, which decides the nature of the operation. Now there are different type of morphological transformations, and we are going to see them one by one. Now to start with, I have this simple code which reads the image using OpenCV imRead method, and we are just loading or showing this image using matplotlib. Now if you are unfamiliar with matplotlib and how to use matplotlib to show images, in the last video I have explained this topic in details. So if you want to see that video about matplotlib, you can see it, and this is the code I have used in the last video also, and I have explained this code in details in the last video. So if you are confused what this code is doing, just see the last video. Now there is one important thing to notice here is I am reading this image in a grayscale mode. Okay, so either you can provide here as the second argument of imread cv2.imread underscore grayscale, or you can provide simply 0 here in order to read this image in grayscale. So let's run this code and let's see what it does. So as expected, it's just opening the image in the grayscale mode using matplotlib. Now, as I said, normally we perform the morphological transformations on the binary images. So that's why we need to provide a mask to our image using the simple thresholding. So let's just do that. So I'm going to just write underscore comma the mask. So I'm going to name my variable as mask here. And then I'm going to just write cv2 dot threshold, and this threshold take few argument, as you might already guess. First is the image itself. Second argument is the value of the threshold. So for now I'm going to just provide the threshold of 220 here. The maximum value of threshold will be 255. Then the next argument here is the type of the threshold. So we are going to provide cv2 dot thrash binary inverse. So this is our mask. So let's load the mask in the matplotlib window. So I'm going to just provide in this titles array one more title, which is mask, and then we are going to see how this image looks like after the mask. Okay, and here the range I'm going to increase it to 2 because now the array is of 2 elements, and the subplot is also, let's say, 1 by 2. So we want to show 2 images, and I'm going to just run this code, and you can see this was the image, which was the grayscale image, and the second image is the masked image. Now if you see this image carefully, let me just increase the size of this image, and if you see this image carefully, after masking there are some black dots here on the balls, and let's say we want to remove these dots which are there in between this white area, this black dot or this black dot, or you can see some black dots are there inside your ball in the white area, and we want to remove these dots from the balls. For this we are going to use the dilation transformation. So first of all, what we are going to do is we are going to just write dilation, which will be our variable name, and then we are going to use this method called cv2 dot dilate. Okay, so this method uses the source, which is mask in our case, and then the second thing is the kernel. Okay, so let me explain what the kernel is. So a kernel is normally a square or some shape which we want to apply on the image. So we are going to define a kernel of numpy once, which means we want to apply white square on our balls. So you can see when we run our code, once again it shows us error because this kernel is undefined. So let me define this kernel first of all. So I'm going to just say kernel is equal to np dot once, and then we are going to define the shape of this kernel. Let's say this is of 2,2 size, and then we will just say np dot uint8. So this is our kernel, and kernel in this case is nothing but a 2 by 2 square shape, and this square shape kernel is going to be applied on our image wherever these black dots are there. So now we have defined this kernel. So let's see after this kernel is applied on our masked image how it looks like. So I'm going to just add one more title here, which is dilation, and then I'm going to add the image after the dilation is applied on our image, and then we are just going to increase the range to 3 because now we have 3 images, and let's say this plot contains images 1 by 3, so 1 row and 3 columns, right? So I'm going to just run this code once again, and now you can see all these 3 images. First was the original image, second is the masked image, and the third one is the image which we got after we applied the dilation. Let me just increase the size of this image somehow. So now you can see that, for example, here there was a black dot and now it's reduced, right? The size of this black dot is reduced. Here also there was a black dot, but its size also is reduced, but still we can see these black dots here, right? So how we can remove these black dots completely? So there is a third parameter which we can provide to this dilate method, and it's called iterations, so number of iterations. So we can just provide iterations is equal to whatever the number of times we want to perform dilation on our image. By default it's 1, and you can provide, let's say, 2 here, and let's see what is the result now. So I'm going to just run this code again, and now you can see those black dots which we can see here on the masked image are now gradually gone, but still I can see some little dots on the images. The small dots are already gone, right? So now what we can do here is we can increase the size of the rectangle. So this rectangle is applied to our area which have these spots, so we can increase the size of the rectangle, and the bigger the rectangle is, the better the result will be, but there will be a problem which I'm going to show you. So let's run this code, and you can see now all the black dots from our image is gone. So there was a black dot here which you don't see anymore, and there was a black dot here, 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 and here, and we don't see these black dots here. But you might also observe that the size of this white area is also increased after we applied the dilation on this masked image. So now this ball and this ball in the result after the dilation is merging here, right? So you can see it's merging because the size of our kernel is big, and when we apply dilation, the pixel element is 1 if at least 1 pixel under the kernel is 1. That's why the shape of these balls are increasing. So let's see how our next morphological transformation works, which is called erosion, and after that I'm going to explain you how this erosion works and what is erosion. So I'm going to just declare a variable called erosion, and then I'm going to just call a method called cv2.erode. So the method name is erode, and the first argument here is the source, the second argument here is the kernel as we have seen in dilate method, and the third argument is the optional argument which is the iterations. So for now we just apply 1 iteration which is by default also 1, and now we are going to just add this image to our matplotlib window. So I'm going to add the title and the image, and now I will increase the range of the array to 4, and let's say now we want 2 by 2 matrix of these images, right? So let's run this code and let's see what happens. So now you can see 4 results here, and first was the original image, second was the masked image, third was the dilation, so all the spots in the balls which are black are gone using the dilation, but the size was increased, and using the erosion you can see the sides of the ball eroded. So the basic idea of erosion is just like soil erosion. It erodes away the boundary of the foreground object. So when this erosion is applied, the kernel which we have defined slides through all the image, and a pixel in the original image, either 1 or 0, will be considered as 1 only if all the pixels under the kernel is 1. Otherwise it is eroded, and this means this value will be set to 0, which means this will be a black area. So let's increase the number of iterations here. So let's say we want to apply the erosion 2 times on the same image, and I'm going to just run this code once again, and you can see now these balls are eroded more. Let's say we want to increase this to 5 times and then run the code, and you can see now these balls are really small because we have applied this erosion multiple number of times. So let's say this is 1 once again, and let's make this size of our kernel small, 2 by 2 rectangle size, right? So you can see now our result is better because all the spots from these balls are gone, and these balls are not so much eroded. Now there are 2 more morphological transformation methods which are called opening and closing. So we are going to first of all see how opening works. So I'm going to define a variable called opening, and then I will call cv2.morphologyx. okay, and then we will provide the source, which is mask. The second method is the type of morphological operation which we want to perform. So in this we are going to just call cv2 dot, and then we can specify which type of morphological operation we want to perform on the image. So just write morph and then the type of operation. So we want to perform the morph open for the opening, right? And then the third argument here is the kernel which we have defined, and now we are going to just add this opening to our matplotlib window. Let's add this, and then let's do 5 here, and then let's say our matplotlib is going to show these images in a 2 by 3 format. Okay, so let's run this code and let's see what happens, and let me increase the size of this image now, and this is the result of the opening. So what is opening in morphological transformations? So opening is just another name of erosion followed by dilation. So when you perform this opening morphological operation, first of all erosion is performed on the image, and then the dilation will be performed on the image. So you can see the effect of the erosion followed by the dilation. Still you see some spots here which can go if you can just increase the size of this block. So let's rerun the code. Let's see what happens. So now this image somehow looks better than the older image. So opening is the erosion followed by dilation. Now there is a closing method also, which is just the opposite of opening. In the closing morphological transformation, dilation is performed first on the image and then it is followed by the erosion. So let's see if we get the better result when we perform the closing morphological operations, and the morphological operation here will be close. and run this code. And now you can see the result here. So in closing, as I said, first of all, the dilation is applied and then the erosion is applied. In the opening, first of all, erosion is applied and then the dilation will be applied. Now there are different type of morphological operations you can apply using this morphology X. So for example, I'm going to just use some of them. So the main morphological operations other than opening and closing is, let's say, morphological gradient. So I'm going to just say mg for morphological gradient, and you just need to change the second argument here. So cv2 morph underscore morphological gradient. So we are going to just call this morph gradient, and it's going to apply the morphological gradient. And then the next is the top hat and the black hat. So there are different morphological techniques you can apply. So I'm going to show you one more and then I will leave you with the other techniques. So th for top hat, and here also the second argument you just need to change it to top hat, right? Otherwise you can see there are so many number of techniques you can apply on your image. So there is gradient, close, open, we have already seen, black hat, cross, dilate, ellipse, erode, hit miss, rect, and then top hat, which is we are going to use right now, right? And then we can just add these two things to our list of titles and list of images. So mg, and then we have th for top hat, and now we have 8 images, so range is increased to 8, and let's say we just want to show them in 2x4 matrix here in the matplotlib window. So you can see this is the result of morphological gradient. So morphological gradient is the difference between the dilation and erosion of an image, and this is the result of top hat. That means it is the difference between the image and the opening of an image. So this is how you can perform some of the morphological operations on the images. Now I will show you one more example. I have an image called j.png. So I'm going to just load this image also, and because this j.png is already a binary image, I don't need to apply this mask here. So instead of this mask, I can just directly use our image variable. So I'm going to just write this, and let's load this image 2 times because we already have defined this mask variable inside our title list and image list. And now I'm going to just run this code. So the original image of this j.png looks like this, and after we applied the dilation, you can see the dilation increases the area of this j. The erosion just erodes away the corners of this j, right? Opening is going to apply the erosion first, followed by the dilation, and closing is going to first of all perform the dilation followed by the erosion. This morphological gradient is going to give you the difference between the dilation and erosion of the image. So it's going to give you this kind of result, and you can see the top hat result here, which is the difference between the input image and the opening of the image. So this is how you can use different type of morphological transformations on your images. In this video, we will discuss about smoothing or blurring images in OpenCV. So smoothing, which is also known as blurring, is one of the most commonly used operation in image processing. The most common use of smoothing operation is to remove noise in the images. Now, when smoothing or blurring images, we can use diverse linear filters because linear filters are easy to achieve and are also relatively fast. Now, there are various kinds of filters available in OpenCV, for example, homogeneous, Gaussian, median or bilateral filters, which we will see one by one. So first of all, we will see the homogeneous filter. So homogeneous filter is the most simple filter, and in homogeneous filter, each output pixel is the mean of its kernel neighbors. Now in homogeneous filter, all pixels contribute with the equal weight, and that's why they are called homogeneous filters. Now those of you who don't know what the kernel is, I have explained about kernel in the last video, so you can see the last video. And in simple word, a kernel is a shape which we can apply or convolve over an image. And you can use, for example, Numpy to create this kind of squared kernel. So in homogeneous filter, the kernel looks like this image which you see on your screen. So in homogeneous filter, kernel k is equal to 1 by the width of the kernel multiplied by the height of the kernel. So let's say we want to use a kernel of 5 by 5, then using this formula we will have k is equal to 1 by 25, and then we will have our kernel matrix of 5 by 5 ones. So let's create this kernel first of all, and then we will see how to use this kernel for the image filtering using 2D convolution or homogeneous filter. So what I have right now here is the simple code which loads this image using matplotlib, and this code you might already know because I have explained in detail how matplotlib works and how to read the images using OpenCV. One thing to note here is I'm just converting the image from BGR to RGB because matplotlib reads the images in the RGB format and OpenCV reads the images in the BGR format. So this conversion is necessary. So let's define our kernel. So I'm going to just say kernel is equal to np dot ones, and then we are going to take the kernel of 5 by 5. So we are going to define this kernel 5 comma 5 of ones. So I'm going to just say np dot float 32 here, and then we are going to divide this kernel by 25 because our kernel is of 5 by 5, because the formula which we have seen, in that formula we have the kernel which was a matrix of ones, and then we have the multiplication of 1 divided by the width and height of the kernel. So that's why the multiplication of the width and height is 25. That's why I have taken 25 here. So now we have our kernel, so we can define our destination image using this kernel, and we are going to use cv2 dot, there is a method called filter 2D which we are going to use, which is used for this homogeneous filter. So here the first argument is the image, the second argument is the desired depth of the destination image. So for now we are going to take it as -1. The third argument is the kernel. So now when we have applied this kernel on our image using 2D filter, let's see what the output will look like. So I will name this image as 2D convolution, and the destination is the final image which we got using filter 2D. And let's increase this range by 2, and let's say we want to show this image on matplotlib in 1 by 2 format. Okay, so I'm going to just run this image. So this is the result. On the left hand side is the original image, and on the right hand side is the 2D filter applied image. So this is the image which we got by applying the homogeneous filter using filter 2D function. So you can see on the corners here there is a little bit noise, and after applying this 2D convolution over this image, you can see all the corners are now smoothened, and overall this image is now smoothened or blurred a little bit. So these noises are removed or suppressed by this blurring. So this is one way of blurring an image using filter 2D, right? Filter 2D function. Now, as in one-dimensional signals, images also can be filtered with various low-pass filters or high-pass filters, etc. So low-pass filter helps in removing the noise or blurring the image, etc. And high-pass filters helps in finding edges in the images. Now, when you want to achieve image blurring, we need to convolve over the image with the low pass filter kernel. Now, there are some algorithm. As I said, there are various kind of algorithm available in OpenCV. So we will also see them one by one. So first algorithm is the blur method, or it's also called the averaging. So what I'm going to do is I'm going to define a variable called blur, and then I'm going to call a method called cv2.blur. Okay, so this is the method which we will use to apply averaging algorithm for blurring the image, and this takes two arguments. One is the image and second is the kernel. So the kernel we are going to apply is once again 5 by 5, and now we are going to just see the result of this blurring method. So we are going to just load it using the matplotlib. So range, I'm going to increase it by 1 once again, and let's see this these three images in 1 by 3 format on the matplotlib window. So this is the result, and you can see the original image, the result which we got using the filter 2D method, and the result we got using the blur method, which is also called averaging. So the result is more or less looks the same to me, because we have applied the same kind of kernel to both the functions. So this is the result of filter 2D function, and this is the result of the blur function. Now there are more functions which are available in OpenCV, so let's see them. So the next algorithm which we are going to see is the Gaussian filter algorithm. So the Gaussian filter is nothing but using different weight kernel in both x and y direction. So in the result, pixels located in the middle of the kernel have the higher weight or bigger weight, and the weights decreases with distance from the neighborhood center. So pixels located on the side have smaller weight, and the pixels located on the center have the higher weight. So when we take a 5 by 5 kernel, its result is going to look like this, which is shown in the image. And now let's see how we can use this Gaussian blur in our OpenCV code. So I'm going to remove this semicolon which I somehow added here, and let's declare a variable called g blur for Gaussian blur, and then we are going to use cv2 dot Gaussian blur. So the method name is Gaussian blur, and the argument here are same as the blur method. So first argument is the image itself, second argument is our kernel. We are going to take the same kernel of 5 by 5, and the third argument here is the sigma x value, which we are going to take 0 for now. And let's see the result of the Gaussian blur method when it's applied to an image. So I'm going to just define one more title, which is g blur or Gaussian blur, or let's take this name, which will be more clear. And then our result image is G blur, and let's increase the range to 4, and let's say we want to show this image in 2 by 2 format, so 2 rows and 2 columns. So I'm going to run this code, and for OpenCV logo, the results looks the same. You can see for the 2D convolution or filter 2D method or blur method, using the Gaussian blur, you can see there is a little bit different between the blur method and Gaussian blur method results. The Gaussian blur result is more better in my eyes than the blur method. Let's try this Gaussian blur method with another image. So I have this image called halftone underscore Gaussian underscore blur, and I'm going to run this code now with the new image, and you can see the result now. So this was the original image, which have too much noise here. So you can see the pixels here which have too much noise, and after applying the Gaussian blur, you can see this eye image in a much better way, and all the noise is removed. So the Gaussian blur method is designed specifically for removing the high frequency noise from the image, like this one. Now let's see the next method, which is called the median filter. So median filter is something that replaces each pixel value with the median of its neighboring pixel. So this method is great when dealing with something which is called salt and pepper noise. Now if you don't know what the salt and pepper noise is, you can open the Wikipedia and under this URL, or just search for salt and pepper noise Wikipedia page, and you can see more details about salt and pepper noise. So you can see this is an image, and there are some pixels which are distorted here. So there are some pixels where the white dots are there, or white noise is there, and there are some places where the black noise is there. So that's why it's called salt and pepper, because we have white pixels which are distorted like salt, and we have the black pixels which are which looks like pepper. So that's why it's called salt and pepper noise. So I have this same image which I'm going to use as a source now. So it's called water.png in my case. And now let's see how we can use the median blur method. So I'm going to just define a new variable called median, and then I'm going to use cv2 dot median blur method. So this method is called median blur, where the first argument is the image and the second argument here is the kernel size. Now one thing to note here is that the kernel size must be odd here. So this must be 3 or 5 or 7 and so on, except 1. Okay, so when you just give 1, it's going to show you the original image, and let's say we just give 3 here as the kernel size, or in our case we have the kernel size of 5, so let's take the 5 kernel size here. So let's just show this result of the median filter in the matplotlib window. So I'm going to just increase the range 5, and let's say this is 2 by 3 matrix now, and I'm going to run this code, and now you can see the results of all the filtering method, and you can see the best result you get using the median filter method. So when you have this kind of salt and pepper dots on your images, then you can use the median filter. Now let's see the last filter, which is called the bilateral filter. So by using all these filters, for example homogeneous filter or averaging or the Gaussian or the median filter, we not only dissolve the noise but we also smooth the edges. And sometimes we need to preserve the edges. That means we need that all the edges must remain sharper even if the image is blurred. So let me show you one example. So I have this lena.png image. So I'm going to define a variable called bilateral filter, and then there is a method called cv2.bilateral filter, and this bilateral filter takes the first argument, which is the image. The second argument is the diameter of each pixel neighborhood that is used during the filter. So let's take it as a 9. The third argument is the sigma color, and the fourth argument is the sigma space. So the sigma color is the filter sigma in the color space, and sigma space is the filter sigma in the coordinate space. So for this, we are going to take this filter sigma color and sigma space as 75 and 75 here, and let's see it in the result window. So bilateral filter, and then the result bilateral filter, and this gives me error because this image is called lena.jpg, not png, so jpg, and then we need to increase this range by 1 to see all the 6 images. And let's run this code and let's see what happens. So you can see the result now. So let me make it a little bit bigger so you can see them, and from here also. So now you can see by applying the bilateral filter, the edges are preserved in a much better way. So here you can see the hat border is blurred, but here you can see in the result the border of the hat are preserved. So the images in which you need to preserve the borders, then you can use the bilateral filter. So bilateral filter is highly effective in noise removal while keeping the edge sharp. So these are some of the methods and algorithms you can use to smoothen or blur your images using OpenCV. In this video, we will talk about image gradients in OpenCV. So first of all, what is an image gradient? So an image gradient is a directional change in the intensity or the color inside the image. Now the image gradient of an image is one of the fundamental building blocks in image processing. For example, we use image gradients inside the image to find the edges inside an image. Now there are several image gradient methods available in OpenCV, and we are going to see 3 of them. First is the Laplacian derivatives, second is the Sobel X method, and third one will be the Sobel Y methods. And all these methods which I mentioned are different gradient functions which uses different mathematical operations to produce the required image. So the Laplacian calculates the Laplacian derivatives, whereas Sobel method is joint, Gaussian and differentiation operations. But don't be overwhelmed with the details. You just need to keep in mind that these are just the functions which we use for finding out the gradients of an image to analyze the image. So let's use the first method, which is called the Laplacian gradient. Now to start with, I have this initial code, and you might already know what this code is doing. So first of all, I'm just reading this image messy5.jpg in the grayscale mode using the imread method, and then I'm just loading this image using the matplotlib window. So let's first see how the result looks like. So this is going to look like this. This is just a normal image of Messy, and let's see how we can apply the Laplacian method to find out the Laplacian gradient of an image. So for that, we are going to declare a variable called lap, and then there is a function available inside your CV2 library, which is called Laplacian. And this Laplacian method takes few arguments. First argument is the image. The second argument here will be the data type, which we are going to use, which is called CV2 dot CV underscore 64F. So CV2 dot CV underscore 64F is just a data type, and we are using a 64-bit float due to the negative slope induced by transforming the image from white to black. So you just need to keep in mind that this is just a data type which is 64-bit float, and it supports the negative numbers which we will be dealing with when the Laplacian method is run on our image. Now in the next line, what we are going to do is we are going to take the absolute value of our Laplacian image transformation, and we are going to convert this value back to the unsigned 8-bit integer which is suitable for our output. So I'm going to just write lap and then using the numpy uint method, so np dot uint 8, and as an argument we are going to pass np dot absolute, and then inside the absolute method we are going to just pass our image, which is going to give us the absolute value of our Laplacian image transformation, which is going to convert this into the unsigned 8-bit integer. Now let's see the result of this Laplacian gradient. So I'm going to just add a new title to my title array, which is called Laplacian, and also inside the images list I'm going to add this lap variable which contains this image right after the Laplacian gradient is applied here, and here the range will be 2, and we are going to see it in 1/2 format on the matplotlib window. So here you can see the original image, which is this one, and after the Laplacian gradient method is applied on this image, you can see all the edges which are detected by this method when we applied this method on this messy5.jpg image. And an image gradient, as I said, is the directional change in the intensity or the color in an image. So let's close this window, and there is one more argument you can provide here, which is the kernel size. So you can just say k size is equal to 5. This is the kernel size, and I'm going to just run this program once again, and you can see the kernel size is increased, but our result is deteriorated, right? So let's reduce it to 3, and then once again run this program, and the result looks fine. And if you apply k size is equal to 1, let's see the result, and you can see you get the better result, I think. So for now I'm going to just use k size is equal to 3, and now let's use the other two image gradient methods, which are Sobel X and Sobel Y. So these methods, which are called Sobel X and Sobel Y, are also called Sobel gradient representation. So let's just use them, and then we will discuss how they are useful. So first of all, I'm going to declare a variable called Sobel X, and then I'm going to use the method inside this CV2 library, which is called Sobel. So this is the method which takes again few arguments. First is the image, second is again this data type, which is CV2 dot CV underscore 64, and the third argument here will be the dx. So when you write 1 here, this value can be 1 or 0. So when you write 1 here, that means we want to use the Sobel X method. Okay, and then the fourth argument here is the dy value. Okay, so this is dx, which is for the x direction, and this is for the dy, which is for the y direction, and dx stands for the order of derivative x, and the dy stands for order of derivative y. Now once again we are going to declare the Sobel y variable. So let's declare the Sobel y, and then cv2 dot Sobel, and this also takes a few arguments. Here the difference will be only the third and fourth argument, so I'm going to just use the second argument same. The third argument will be 0 for Sobel y, and the fourth argument will be 1, right? So this is the order of derivative x. If it's 1, this is called the order of derivative, which is in the x direction, and in the second case it is in the y direction. And the fifth argument here can be the k size, as we have seen in the Laplacian method. So if you want, you can provide the kernel size also here as the fifth argument, but we are going to skip it for now. Now again we are going to convert these values into the unsigned int, as we have done in the case of Laplacian. So what we are going to do is we are going to once again overwrite this variable Sobel x, and then we are going to use np dot u int 8, and in the parenthesis we are going to just write np dot absolute, and then we are going to just pass the value inside the Sobel x variable. Same we are going to do with the Sobel y variable. And now let's see the result, how the result looks like. So I'm going to just add these elements inside the title and the image list. So let's add Sobel x and Sobel y here and here also. So Sobel y, and now let's increase the range to 4, and let's see it in the form of 2 by 2 matrix on the matplotlib window. So I'm going to just run this code, and you can see the result here. So original image, Laplacian gradient, and then Sobel x and Sobel y. So you can see when you apply the Sobel x gradient method, the direction or the change in direction in the intensity is in the x direction, and when you apply the Sobel y method, the change in direction in the intensity is in the y direction. So this is like horizontal, and this is in the vertical direction. I have one more image which will illustrate this Sobel x and Sobel y gradient method in a better way, I think, and this is called Sudoku. So I'm going to just write sudoku.png file, and hopefully I didn't do any mistake in the naming. Yes, it works. So you can see the Laplacian result here, and then Sobel x and Sobel y result here. So in the Sobel x you can see more vertical lines, so because Sobel y is good for the directional change in the vertical direction, so you can see more change in intensity in the vertical direction, and using the Sobel y you can see the directional change in the intensity in the horizontal direction or the y-axis. You can also combine the result of Sobel x and Sobel y images, and how we can do this, let's see. So to combine these two result, I'm going to just create one more method which is called Sobel combined is equal to cv2 dot we are going to use the bitwise OR operator in order to merge these two images. So we are going to just write bitwise OR, and then we are going to provide the two sources. One is Sobel X and the other is the Sobel Y image. So this is going to give us the bitwise OR result of these two images, and then we are going to just add this into the title list. So let's say Sobel combined, and also in the image list, so like this. And let's just increase the range to 5, and let's see it in the form of 2x3 on matplotlib. So I'm going to just run this once again, and you can see the result now. So this here is the combination of Sobel X and Sobel Y method, and you can see now, you can see the directional change in the vertical as well as in the horizontal direction, because this is the combination of Sobel Y and Sobel X images. So this is how you can use the image gradients inside OpenCV. In this video, we will talk about Kenny edge detector in OpenCV. So first of all, what is Kenny edge detector? So the Kenny edge detector is an edge detection operator that uses multi-stage algorithm to detect a wide range of edges in images. Now this Kenny edge detector was written and developed by John F. Kenny in 1986. That's why it's named after his name, which is Kenny edge detector. Now the process of Kenny edge detection algorithm can be broken down in 5 different steps. The first step is to apply Gaussian filter to smooth the image in order to remove the noise. The second step is to find the intensity gradients of the image. The third step is to apply the non-maximum suppression to get rid of spurious response to edge detection. The fourth step is to apply double threshold to determine the potential edges, and the fifth step is to track edges by hysteresis. That is to finalize the detection of the edges by suppressing all the other edges that are weak or not connected to strong edges. So this seems little bit complicated, but in OpenCV it's really simple to use. So there is a built-in function in OpenCV which is called Kenny, and we are going to use this function. So to start with, I have this sample code which loads this image which is called messy.jpg using the matplotlib library. I'm going to just run this to show you the result. So this is the image, and we want to detect the edges of this image. So what we are going to do is we are going to first of all declare a variable called Kenny, and then there is a method, as I already said, inside your CV2 library which is called Kenny method, which takes few arguments. So the first argument here is the image source itself. The second argument and the third argument, as you can see, is the first threshold value and the second threshold value. So this first threshold value and the second threshold value you need to provide for the hysteresis procedure. So there is the last step, as I mentioned, and in that step hysteresis take place, and for that procedure we need to provide the values of the threshold 1 and the threshold 2. So for now I'm going to provide 100 as the threshold 1 and 200 as the threshold 2. But later you might want to add a track bar in order to see the changes in the edges when you just move the track bar from left to right for the threshold 1 and the threshold 2. So this might be a small assignment for you. you can just add the track bar and see how the edge detection changes when you change the value of threshold 1 and threshold 2. And I have already explained how you can use track bars with OpenCV. So just watch that video and you will be good to go. So now we have the result of canny edge detection function. So we are going to just add it to our list, first to the list of titles and then second to the list of images, and the range we are going to increase it to 2, and this we are going to just see the images in 1:2 format. So I'm going to just run this Python script and see the result. So you can see we have the original image here, which we have loaded in the grayscale, and on the right hand side you can see the result of the canny edge detection methods. So you can see all the edges which are available here on this messy5.jpg image. You can use this on the other images also. So for example, I have the lena.jpg image. Let's see the result of that, and this is the result of the canny edge detection method on this lena.jpg method. So this canny edge detection is really useful because in the last video we have seen how to find out the image gradients, and let's see in comparison to those image gradient methods how canny edge detection method performs. So these are all the methods I have explained in the last video: Laplacian, Sobel X and Sobel Y, and I have shown you how to combine the result of Sobel X and Sobel Y. And additionally, I have added this line to the previous code which I have shown you in the last video, which is edges is equal to cv2.canny, which gives us the result on the same image using the canny edge detection method, and I have added it to the title and the image, right? So let's run this script once again and let's see the differences in the result using all these methods. So you can see all the 6 results. This is the original image, this is the result of the Laplacian method, this is the result of Sobel X, and this is the result of Sobel Y, and this is the combination of Sobel X and Y. And you can see canny edge detection gives us the result which contains lesser noises. So you can see there is a lot of noise present in the other methods. You can see here all the noise is present which is removed using canny edge detection, or in the Laplacian method also you can see some noises around, but in the canny edge detection method you can see you get the proper edges and more precise edges without any noise. So this is the benefit of using canny edge detection. So this is how you can use canny edge detection. In this video we will discuss about image pyramids in OpenCV. So till now, normally when we have used images, we have used the images of constant size, but sometimes we need to work with the images of different resolution. So for example, if I have an image and I want to search the face inside an image, this face can be of different sizes. So using image pyramids, we just create the images of different resolutions, and then we search for the object, for example face, in all of these images. So pyramid or pyramid representation is a type of multi-scale signal representation in which a signal or an image is subject to repeated smoothing and subsampling. So a normal pyramid, when you create a pyramid of images, it will look like this. So let's say this is the original image at the bottom. Then when you downscale an image using a pyramid function, it's going to give you this image which have the half resolution than the original image, and then when you further go up, it's going to give you the 1/4 of the original image, and then so on. So 1/8 or 1/16 of an image. Now there are two types of image pyramids which are available in OpenCV. First is called Gaussian pyramid and second is called Laplacian pyramid. So first we will discuss about the Gaussian pyramid. So Gaussian pyramid is nothing but repeat filtering and subsampling of an image. Now there are two functions available for the Gaussian pyramid, which is called pyr down and pyr up. So let's see them one by one. So I have this sample code which is just reading an image and then showing it using the IAmShow method. Now in order to use this pyr down function, you can just define a variable, let's say LR for lower resolution, and then you can use cv2 dot pyr down. So there are two functions you can see, pyr down and pyr up. So first of all we will see pyr down, and then we are going to pass our image as an argument here. So I'm going to just pass our image as an argument, and we are already showing the original image, and let's show the image after we have reduced the resolution of this image using the pyr down method. So pyr down is going to reduce the resolution of an image. So I'm going to just use LR here, and let's say this is the pyr down 1 image. Okay, so let's run this code and let's see what happens. So you can see this is the original image, and this is about, you can see 1/4 of this original image, right? So this pyr down method is going to reduce the resolution of an image. When you apply the same method on the second image, so let's say this is LR1, and then we create a second variable LR2, and when we pass LR1 as an argument for this method to create the LR2 image, then let's see what happens. So this will be LR1, and let's just say this is going to give us LR2. The resolution of image will reduce further. So let's see what happens. So this was the original image, this was the image which we got from the first pyr down method, and then we get this image which is further reduced in resolution. So this is the image after applying the pyr down method second time on the LR1 image. Okay, so you can see the resolution of image is reducing, and it's creating a kind of pyramid, and that's why it's called the image pyramid. Now there is a method called pyr up also available in OpenCV. So let's see what this pyr up method do. So as you can expect, it's going to increase the resolution of the image. So here I'm going to just say HR for higher resolution, and then I'm going to just say cv2 dot pyr up. Okay, and it's going to increase the resolution of an image. Now let's say we want to increase the resolution of this image, which is the smallest image which we got using the pyr down method, right? So we are going to apply the pyr up on the last image which we got using the pyr down method, and let's see what happens. So when I'm going to use this HR2 here, and this we got from pyr up method, and let's say this is the pyr up 1, and I'm going to just run this code, and you are going to see that we have converted this image, which was the smallest image, to a higher resolution, which resulted in this image. But when you see this image carefully, so let me just move this to this side, and this was the original image. So let me just minimize this. So this image we have converted to this image using the pair up method. So ideally this image should look like this, but you have to remember that this pair up image is not going to be equal to this image, because once you decrease the resolution using the pair down method, you lose the information about that image. So when you use pair up to just increase the resolution of this image, then you can see the result looks little bit blurred, because some of the information is loosed using the pair down method. So you have to keep this in mind, that when you want to increase the resolution after you have reduced the resolution, you are not going to get the same result as you might expect, that this image should look like this, but they are not equal images. So this image is just a higher resolution of this image, and it has nothing to do with this image. So these are the two methods which are available in Gaussian pyramid. Now if you want to create a pyramid of multiple resolution, instead of just using this pair up or pair down method repeatedly, what you can do here is, I'm going to just remove this and remove this code also. So what I'm going to do is, I'm going to copy the image into a new variable. So I'm going to just say layer is equal to img dot copy. There is a method available for copying the image, which is copy, and then I'm going to create the Gaussian pyramid array. Okay, so I'm going to just create a variable called gp for Gaussian pyramid is equal to, then in square bracket I'm going to just pass this image here as the first element of this list. Then what I can do is, I can use a for loop instead of just rewriting this pair down method again and again. And you might already know how to use for loop in Python. So for I in range, and here we can provide any range. So let's say we want to create 5 image pyramid. Okay, so 5 times we want to reduce the resolution. So we are going to give 6 here, because range goes the number minus 1. So whatever you give here, minus 1, right? So now what we are going to do is, we are going to just use our layer parameter once again, and then we are going to just call cv2 dot pair down method. So pair down, and then we want to just say layer. Okay, and then we want to append to the Gaussian pyramid list. Okay, so we are going to just say gp dot append, and we are going to append the result of this pair down to our list which we have created here. Okay, so this is going to just append this image to our list of images, and then let's just show this image using cv2 dot imshow method. So cv2 dot imshow, and here we can just say str for converting the integer to the string, because the first parameter you give to imshow is a string parameter. That's why I'm converting the integer to the string, and the second parameter is the image. So let's pass this layer here. Okay, so you have the original image which will be shown using this line of code, and then you will see multiple number of images of different resolution using this code. So let's run this code and let's see what happens. So I'm going to run this code, and you can see there are different images resulted using that code which we have written. So this was the first image, which is 0, and then this is the second image, and then this is the third, fourth, fifth, and sixth. So sixth, you can see, have a very small resolution. So this is how you can use pare down method multiple times using a for loop. Now, what are Laplacian pyramids? So Laplacian pyramids are formed from the Gaussian pyramids. There is no exclusive function for creating the Laplacian pyramid. So as you have seen that in Gaussian pyramids, there are two methods available, pair up and pair down, but there is no exclusive function for creating the Laplacian pyramid. So how we can create a Laplacian pyramid if there is no function available for creating them? So you can create a Laplacian pyramid, or a level of Laplacian pyramid is formed by the difference between that level in the Gaussian pyramid and the extended version of its upper level in the Gaussian pyramid. So this definition might be confusing to you guys. So let me explain you with the code what I mean by this definition. So what I'm going to do is, first of all, I'm going to take the top level layer of the Gaussian pyramid. So top level layer of the Gaussian pyramid is the last image which is generated using this for loop. So let's say we have 6 images or 5 images using this for loop. So what we are going to do is, because we have appended each and every image to this list, right? So we have all the images inside this list. So we can just get the last image using the indexing. So again, I'm going to use the layer variable, and then I'm going to just say GP for Gaussian pyramid list, and then there is the index 5, because last image will be available at the index 5 of this list. So we get the last image of that Gaussian pyramid, and then let's show this image. So I'm going to just say cv2 dot show, and this is the upper level or the last image. So I'm going to say upper level Gaussian pyramid, and then we are going to pass this layer variable here. So this is going to show just the last image of this list, and let's just comment this code out because we don't want to see all the images. And then I'm going to create a new list for Laplacian pyramid. So I'm going to just say LP for Laplacian pyramid, and then I'm going to create a list using the layer variable itself, as we have done for the Gaussian pyramid list also. So the first element here is the layer variable itself, and now we are going to use the for loop, and then I in range. And this time what we are going to do is, you might already know how to use the range function, and if you don't know, you can see you can give the stop integer here, or you can give multiple parameters here. So you can see there is one more implementation of this range function. So you can give the start parameter and the stop range. So start is the starting point, stop is the stopping point, and also you can give the steps. So this step means in what number you want to reduce. Okay, so let's say we want to start from 5, and then we want to go until 0, and we want to reduce in the step of -1. Okay, so 5, 4, 3, 2, 1. So let's print the value of I first of all. If you might be interested in the result of this range function, then let's just run this code and let's see what happens. So this is the images which we get, but we are not interested in these images. We are interested in the print function output. So you can see the output of this print function code is 54321. As I said, the lower limit is not reached. So if you give 0 here, then it's going to go until 1 and not 0. If you give 6 here, then it's going to go until 5, not 6. So let me repeat the definition of Laplacian pyramid once again. So Laplacian pyramid is formed by the difference between that level in the Gaussian pyramid and the extended version of its upper level in the Gaussian pyramid. So let's first create the extended version of that level. So we are going to just create a variable called Gaussian extend or extended, and then we are going to extend the level of that image which are there in the Gaussian pyramid list by using cv2 dot pair up method. And here what you need to give is the Gaussian pyramid list, and then we just need to get the index I from this. So this line gives us the extended version of the upper level in Gaussian pyramid. Now let's create the Laplacian pyramid. So Laplacian is equal to cv2 dot subtract, because we want to find out the difference between that level in the Gaussian pyramid and the extended version of its upper level. So I'm going to just say GP for Gaussian pyramid, and then we are going to just say I minus 1 as the first parameter, and the second parameter is the extended version of the Gaussian upper limit. And now we can use the show method to show all these Laplacian images. So I'm going to just say cv2 dot show, and once again I'm going to use str function to convert from a number to string, and then in the next parameter I'm going to just pass the Laplacian parameter here as an image source. So what do you think? Will this code work? So let's see what happens when we are going to run this code. So you can see the Laplacian pyramid looks just like the edge detection. So all the edges are shown here on every image. This is the first level, this is the second level, third level, fourth, fifth level. So these images are called the Laplacian pyramid. Now what is the use of creating those Laplacian pyramids or the Gaussian pyramids? So the Laplacian and Gaussian pyramid helps us to blend the images and the reconstruction of the images. So these are the two benefits of creating those Laplacian and the Gaussian pyramids. So in the next video we are going to see how we can blend the images, or how can we reconstruct the images using the OpenCV and the image pyramids. In the last video we have seen what are image pyramids, and I have told you there are two kinds of image pyramids in OpenCV. One is called the Gaussian pyramid and the other is called the Laplacian pyramid. And we have seen in the last video how we can create the Gaussian pyramid and the Laplacian pyramid. Now in the last video I have also told you some applications of image pyramids, and one of the application of image pyramids is the image blending. So let me show you one example. So here in this code I have two images. One is of apple and other is of orange, and I want to blend or merge these two images. So let me just run this code first of all. So you can see there are two images. First is of apple and other is of orange, and I have also printed the shape of these two images. So you can see the shape is similar, 512 by 512, and orange image shape is also 512 by 512. So here what I want to do is I want to blend half of the orange to half of the apple. So let's say I want to just blend right hand side of this orange to the left hand half of this apple. So how can I achieve this? Now you might say that I can just cut these two images into half, and then I can stack these two images side by side, and I will get the half and half of the two images, and that's how I can just get the result. So let's first of all try this technique. First of all, we are going to just create the half and half of the apple and orange images, and we are going to just stack these images side by side. So let's say I'm going to create the variable called apple underscore orange, and then here there is a method in Numpy. So I'm going to just say numpy dot hstack. So there is this method called hstack, and here what I can do is in the form of tuple I can provide the half of my apple image. So apple is the image variable name, and then what I'm going to do is the half of this image, because this image is 512 by 512. So I'm going to just give this kind of expression, colon, comma, and then colon 256, which is the half of the apple image on the left hand side, right? And then I'm going to just do the same with the orange image. So I'm going to just take orange and then colon, comma, 256 colon. So one thing to observe here is I have taken colon before 256 in the apple image, and I have taken colon after 256 in the orange image. And then I'm going to just show this apple orange image, and let's see what result we get when we run our code. So these two are the apple and orange image, and this is the result of adding the two halves of the orange and the apple image. But still you can see this line which is clearly visible, and from this line you can say half of this is orange and half of this is an apple. So in image blending, what we need to do is we need to blend this line also. So the orange and the apple image should be merged or blended in a perfect way. So for blending this half apple and half orange image, what we can do is we can use the image pyramid techniques to blend these two images. Now in order to blend two images using image pyramids technique, we need to follow 5 steps. The first step is to load two images. In our case, these images are of apple and orange, which we are already doing. So first step is to load these two images. The second step is to find out the Gaussian pyramid of our apple and orange image. The third step will be from these Gaussian pyramids, find out the Laplacian pyramids. Okay, so we will find out the Gaussian pyramid in the second step, and then in the third step we are going to find out the Laplacian pyramids. Now in the fourth step we are going to join the left half of the apple and the right half of the orange in each levels of Laplacian pyramid. And finally in the fifth step, what we are going to do is we are going to just join these image pyramids and reconstruct the original image. So let's follow these steps one by one and let's see what result we get. So as I said, first step is already done, which is just loading these two images. And the second step would be to find out the Gaussian pyramid. So let me just write this step, generate Gaussian pyramid for Apple first of all, and then we are going to find out the Gaussian pyramid of the orange. So first of all, what I'm going to do is I'm going to just copy the Apple image. So I'm going to just say Apple underscore copy is equal to Apple dot copy. So there is a method called copy which you can use to copy this image. So from this copy, what we are going to do is we are going to generate the Gaussian pyramid. So I'm going to once again name my variable as gp let's say underscore Apple, and then we are going to just pass our image which we have copied in the form of list. So I'm going to just say Apple copy here. So these steps we have already seen in the last video, how to create the Gaussian pyramid and the Laplacian pyramid of an image. So I'm not going to explain this in detail. If you want the detailed explanation, you can see the last video. Next, what I'm going to do is I'm going to create a for loop, and I'm going to just say for I in our range. So I'm going to use the range function, and we are going to use the 6 levels in this example. So I'm going to provide the range up to 6, and then what we are going to do is we are going to just say Apple copy, or you might have named this variable as Apple layer also, because we are just creating multiple layer of the Apple image for the Gaussian pyramid, right? And then we are going to use the cv2.pair down method to create the Gaussian pyramid. Okay, this we have already seen in the last video. And now as an argument, we are going to pass our Apple copy variable here. And in the next step, what we are going to do is we are going to just append to our gp underscore Apple variable, which is our Gaussian pyramid for the Apple image, and then we are going to just append this Apple copy after we have applied pair down method on the same image. So this is just giving us multiple layer of the Apple image, right? The same method we are going to apply for the orange also. So I'm going to just copy this code, and then I'm going to just paste this code once again, and this time this will be for orange, and I'm going to just say this is the orange copy, and we are going to copy from the orange image, and then we are going to just generate the Gaussian pyramid for the orange image, and this will be passed here, and also here, and also here, and also here, and this Gaussian pyramid orange will be passed here. Okay, so we have generated the Gaussian pyramid for the Apple and the orange. Now we are going to generate the Laplacian pyramid for Apple and orange. So this also we have seen in the last video. So I'm going to just comment generate Laplacian pyramid for Apple first of all. And to find out the Laplacian pyramid for the Apple, what we are going to do is we are going to once again take our Apple copy, and then using our Gaussian pyramid. So let's take Gaussian pyramid for the Apple, and we are going to use the 5th element of this list. So what we have learned in the last video, how we can find out the Laplacian pyramid. A level in the Laplacian pyramid is formed by the difference between the level in the Gaussian pyramid and extended version of its upper level in the Gaussian pyramid. So this difference we are going to find out in this step. So I'm going to just say this is LP for the Apple, which stands for Laplacian pyramid for the Apple, is equal to, in the list we are going to just pass the Apple copy, and then we are going to use the for loop. So for I in the range, so we are going to take the range, and in the last video I have shown you how to take the range for the Laplacian pyramid. So we want to go from 5 until 0 in the steps of -1, and then in the next step we are going to create the Gaussian extended variables. Gaussian extended is equal to CV2 dot pair up. This time we are going to use the pair up method, and then we are going to pass our GP apple, which is Gaussian pyramid for apple, and then the index here will be I. In the next step we are going to create the Laplacian variables is equal to CV2 dot subtract. So there is a method in CV2 which is called subtract, and then we are going to take our Gaussian pyramid for the apple, so GP apple, and the index here will be I minus 1, and the second argument for this subtract method will be our Gaussian extended variable. So we are going to just pass this Gaussian extended variable, and in the next step we are going to just append to our Laplacian pyramid for the apple. So LP underscore apple dot append, and we are going to just append this Laplacian variable to the Laplacian pyramid for the apple. Same we will do for the orange image also. So we are going to generate the Laplacian pyramid for the orange here, and this will be the copy of the orange copy here and here also, and then this will be the GP orange, right? This also will be GP orange, this also will be GP orange, and here instead of LP apple we are going to just say LP orange, and then we are going to just pass this variable here also. So now we have finished 3 steps. One is to load both the images, second is to find out or generate the Gaussian pyramid, and the third step is to generate the Laplacian pyramid for both the images. Now the fourth step is to just join the half of these 2 images. So what I'm going to do is, now I'm going to just create one more variable which will be apple underscore orange underscore, let's say, pyramid is equal to, and also we are going to create a variable called n, and we are going to see later how to use this variable, and then we are going to use the for loop, and then we are going to create 2 variables, one for the first image. So I'm going to just say apple and then lap comma orange lap. Okay, so these 2 variables I'm creating just same as this I in this for loop in zip. So there is a method zip which we can use to zip the Laplacian pyramid 1, which is for the apple, and for the orange also. So I'm going to just say LP for apple comma LP for the orange, and inside this for loop, first of all we are going to just increment the value of n by 1 each time. So n plus equals 1, and in the next step we are going to find out the shape of the apple image. So the apple image shape gives us 3 values. First is columns, so I'm going to just say COLS for columns, then rows, and then the third value is the number of channels, and then we are going to just say apple lap dot shape. In the next step we are going to just create a variable called Laplacian, and we are going to just join the 2 halves of these 2 images which we are getting inside the variable apple lap and orange lap. So we are basically doing this step after applying the Gaussian pyramid and the Laplacian pyramid on both the images. So np.hStack method we are going to apply in this step. So I'm going to just write np.hStack, and then as an argument what we are going to do is, we in the form of tuple, first of all we are going to take our apple lap variable, which is this one, and in the square bracket we are going to just write colon comma 0 comma int. So we are going to just typecast the number of columns in the apple shape. So this we got from the shape of the apple index, and then divided by 2. So we are going to just dividing the columns into half, and same we will do for the orange lap. So we are going to just say orange lap in the square bracket colon comma int, and then once again in the parenthesis we are going to just say cols for the number of columns divided by 2, and then colon, as we have done in this step also. And at last we are going to just append this Laplacian variable to this list which we have created. So apple underscore orange underscore pyramid dot append, and then we are going to pass the Laplacian variable here. Now the last and the final step is to reconstruct our image. So let's reconstruct our image. So now what we are going to do is, we are going to once again create a variable called apple orange underscore reconstruct is equal to, this will be the first index of our apple orange pyramid. So I'm going to just say apple orange underscore pyramid, and this will be the 0th index, and once again we are going to use the for loop. So for I in the range, so we are going to go from 1 until 6, and the default step is of 1, so we don't need to give the third argument. And inside the for loop we are going to just take this variable once again, and then we are going to apply the pair up method on this. So cv2 dot pair up, and as an argument we are going to pass the same variable. So we are going to just apply the pair up on this apple orange reconstruct from the 0th index of the pyramid up to the 6th level. And the last step will be to add all the layers. So apple orange reconstructed once again, or reconstruct is equal to cv2 dot add. So this is also one method which is called add, and here we are adding apple orange pyramid and the reconstructed apple orange image. Okay, so this is this variable which we got by just adding the left and right halves of each level, and then we are just reconstructing this image using the pair up method, and thus just adding the pyramid level. So this should be, I think, the index I, right? We cannot just add the list to the image directly. Okay, so this will be at each layer we are just reconstructing and adding it to the image which we got by just addition of this half of the images. Now in the end, let's try to just load this reconstructed apple orange image in the I am show window, and let's hope it works. I haven't checked it yet, so I'm not sure it will work or not, and you can see it's working in the first go, so that's a good thing. So you can see the difference. So this result we got by just stacking this apple and orange image side by side, but this line is clearly visible. But when we applied the Gaussian pyramid and the Laplacian pyramid technique for blending the images, then you can see this line is perfectly blended and this line is not anymore visible. So this is the perfect blending of the orange and the apple image. So this is how you can use the Laplacian and Gaussian pyramids to reconstruct and blend two images together, and result is in front of you, so you can see how it can blend two images so perfectly. So this is how you can blend images using image pyramid technique. In this video, we are going to understand what contours are, and we are going to see how to find contours and how to draw contours. So first of all, what are contours? So contours can be explained as the curve joining all the continuous points along the boundary which are having the same color or intensity. Now contours can be a useful tool for shape analysis or object detection or object recognition. Now for better accuracy, we generally use binary image for finding the contour. So first of all, we are going to generate the binary image, and then before finding out the contours, we are going to apply the threshold or canny edge detection to find the contours on the image. So let's start with an example. So here I have a simple code which reads an image and then converts this image into a gray scale image, and then I'm just showing both the images using IamShow method. So let's run this code and let's see what result we get. So this is the original image with these colors, and after the conversion of this image to the grayscale image, this is the result which we are getting. And then we are going to find out the threshold or the canny edge. So in this example, we are going to just apply the threshold. So for applying the threshold on this image, we are going to define first of all two variable ret comma thresh is equal to cv2 dot threshold. So there is a method called threshold which we have already seen how threshold work in detail in the previous videos. So the first argument which this threshold method takes is the image. So we are going to pass our grayscale image as the source. The second argument is the threshold value. So because it's a binary image, let's set the threshold to 127, which is around half of the 255, right? The third argument is the maximum value. So the maximum value here will be 255. The next argument will be the type, and type here will be 0. So this is going to give us the threshold value for this grayscale image, and after finding out the threshold of this image, we are going to find out the contours. So for this, we are going to define two variables. One is contours and the second is the hierarchy, because the method which we are going to use, which is cv2 dot find contours, this is the method. It's going to give us these two values, contours and the hierarchy, and we are going to see what are contours and hierarchy in details after applying this method on this image. So the first argument will be the thresh which we got using this threshold method. The second argument will be the contour mode. So this is called the contour retrieval mode also, and there can be several possibilities here which we can apply, but for simplicity and in the most common case, we use retr underscore tree here, okay, as the mode. The third argument here will be the method which we want to apply, and this is also called the contour approximation method, and here also several possibilities are possible, but for now what we are going to use here is this will be cv2 dot approx none. So now as you are seeing here, this find contour method gives us contours and the hierarchy. So the contour is a Python list of all contours in the image, and each individual contour is a Numpy array of x, y coordinates of boundary points of the object, and the hierarchy is the optional output vector which is containing the information about image topology, and this we are going to see in the later videos. So for now we are only concerned about finding out the contours. So for this, as I said, this contains the number of contours, right? So we can print out these number of contours is equal to, and then we are going to just convert this number into the string, and there is a method called length, and then inside this length method we are going to pass our contour variable. So this line is going to print out the number of contours which are found inside the image which we are providing. So let's run this code and let's see what result we get. So we already know that this gives us a grayscale image and the original image, but we are interested in this print message, and the number of contours which are found is 9 inside the source image which we are providing here. Now we already found out the number of contours. Now we need to draw these contours on the image itself. So how can we achieve this? But before this, let's see the individual contour also. So I'm going to just print out the value of the first contour, which will be at index 0. So let's run it once again and let's see what happens. So we are running this code once again, and you can see after printing out the number of contours, it's going to give us the Numpy array of the x and y coordinates. So if we plot or join all these x and y coordinates, we are going to get the boundary of the contour. So now we are going to just take these contours and pass it to a method called draw contours, which is going to draw or join all these coordinates of those contours. So to get this, we are going to just say cv2 dot draw contours, and then the first argument here will be our original image, because we want to draw the contours on our original image. So this will be the img and it's the original image, and the second argument will be the contours. So we are going to just pass the contours which we found inside the image. The third argument will be the contours indexes. So if we just give here -1, then it's going to draw all the 9 contours which were found inside the image, these all contours. So first of all, we will give -1 here as an argument, and then we will see how to give other arguments as the numbers here also. The fourth argument here will be, I think, the color. So we are going to just give the color 0, 255, 0, let's say, and the next argument will be the thickness. So we are going to take the thickness 3 here. So using this method, what we have achieved is we have drawn the contours on the original image. So let's run this code once again and let's see what result we get. So you can see this was the grayscale image, and this we have used for finding out the contours, but the interesting image here is this one, and here you can see all the contours are drawn on this image. So all the green lines or green boundaries are all contours. So because we have given -1, it has drawn all the contours on this image, and we can also give the contour index. So let's say we just want to find out the contour 0, which will be the first contour which is found inside the image. We are going to just run this code once again, and the first contour which was found out is this contour, this p contour, right? In a similar way, we can go up to 8, so 0, 1, and let's rerun this code again. You will see that the second contour is this contour. So this whole contour from the boundary of this image is the second contour, and in a similar way you can go let's say 2. I'm going to run this code once again. You will see the next contour here, and similarly you can go up to the index 8, because the total number of contours are 9 and we are starting from the index 0. That's why we can go up to 8. So this value depends on the number of contours. Okay, so because we found out the number of contours are 9, so that's why we can go up to 8. And let's run this code, and the last contour which was found out, and we have drawn this contour here on this blue circle, right? Now if we go beyond this index, let's say we give 9 here, we are going to get the error, right? So you can go up to 8 here, and if you want to just draw all the contours, then you can just give -1 here, and it's going to draw all the contour on the image which you are providing. So this is how you can find out the contours and draw contours on the images using find contour and draw contour methods in OpenCV. In this video, I'm going to show you how you can create a very basic and simple motion detection and tracking system using Python and OpenCV. So let me show you what we are going to achieve at the end of this video. So I have this video, which is a sample video, and you can see some people are walking around inside this video. Now what I want to do here is I want to show these rectangles around these moving people or persons. So this is tracking, and when some movement occurs, I also want to show this kind of status. That status is movement because somebody is moving inside the video. So if nobody is moving, this status will be blank, and if somebody is moving, then this status will be movement. So this is what we are going to achieve at the end of this video. So we are going to try to track each and every person, and also we are going to track this person with this rectangle, and also we will show the status as movement when somebody moves inside the video. So let's get started. So to start with, I have this basic code which just reads a video using video capture class, and then if this video is valid, then I'm going to just show this frame by frame inside I'm show window. And I'm sure you might be knowing all this code because I've shown you step by step how to capture the video or how you can read the video frames using video capture method. Okay, so this is just to load this video and show it frame by frame using ImShow method. So let me run this code first of all to start with. So our original video looks like this. So some people are moving, but we want to track the movement of each and every person, and also we want to show a rectangle around them, whoever is moving. So let's get started. So under this video capture code line, what I'm going to do is, first of all, I want to read 2 frames from the cap instance. So I'm going to just copy this code and paste it here. So this will be our frame 1, let's say, and similarly I'm going to just read the second frame. So simply we are just declaring 2 frame one after another. Okay, and we don't need this code anymore. So first of all, I'm going to declare a variable diff, and using cv2.abs_diff method, so absolute difference, we are going to find out the difference between the first frame and the second frame. So this method abs_diff is for finding out the absolute difference between the first frame and the second frame. Now once we have the difference, then we are going to convert this difference into a grayscale mode. So we are going to just say gray is equal to cv2.convert color, so cvt color, and the first parameter here will be our difference which we have found between the two frames. So I'm going to just pass diff as the first argument, and the second argument will be cv2 dot, we are going to convert this BGR color to the grayscale mode. And why we are finding out the grayscale mode of this diff? Because we are going to find out the contour in the later stages, and in the last video we have learned that it's easier to find out the contours in the grayscale mode as compared to the colored mode or the BGR mode. So once we have this grayscale mode, we are going to just blur our grayscale frame. So we are going to just declare a variable called blur, and then we are going to apply the Gaussian blur on our gray variable. So cv2 dot Gaussian blur, the first parameter here will be gray. So let's give this gray parameter which we have defined here. The second parameter here is the k size or the kernel size. So let's say we want to provide the kernel size 5,5, and the third parameter here will be the sigma x value. So we are going to just pass 0 here as the sigma x value. Now we are going to find out the threshold. So we are going to just say underscore because we don't need this first variable, and then the second variable will be thresh is equal to cv2 dot threshold, and the first parameter which it takes is the source. So we are going to pass our blurred image as the source, and then the second parameter here will be the threshold value. So we are going to just provide 20 here, then the maximum threshold value will be 255, then the type will be cv2 dot thresh binary. So in the next step what we are going to do is we are going to dilate the thresholded image to fill in all the holes. This will help us to find out the better contours. So there is a method called cv2 dot dilate. So we are going to just declare a variable called dilated, and then we are going to apply this method. So cv2 dot dilate, which takes few arguments. The first argument will be our thresholded version of the image. The second argument here will be the kernel. So kernel, let's say for now we are going to provide none here. Okay, so the kernel size will be none, and then third parameter will be the number of iterations. So let's provide the number of iterations, and the number of iterations we are going to provide here will be 3. So if it doesn't work, we can increase or decrease the number of iterations. Now in the next step what we are going to do is we are going to find out the contour. So as you all know that contour or find contour method is going to give you two results. One is the contours and other is the hierarchy. So we are going to just say contour, and the second result we are going to just say underscore because we are not going to use this second result, and then we are going to just say cv2 dot find contours, and we are going to find the contours on this dilated image. So we are going to say dilated. Now the next argument here will be the mode. So the mode which we are going to use here will be retter underscore tree. So I'm going to just write retr underscore tree, which is most commonly used, and then the next argument here will be the method. So the method here will be cv2 dot chain approx simple, and once we have our contours we are going to just draw the contours because we already found out the contours. So we are going to just say draw contours, and the first argument here will be frame 1 because we want to apply all the contours on the original frame, right? So we are going to apply all the contours which we have found using all these methods on the frame 1, and then the second argument here will be the contour. So you can just give the contours here, and the third argument here will be the contour ID. I can just say -1, which is going to apply all the contours, and the next argument will be the color. So let's say we want to provide the green color, so I'm going to just say 0, 255, 0, and the next will be the thickness. So let's say we want to provide the thickness of 2 here. So now it's going to draw all the contours which we have found with the difference of frame 1 and frame 2, right? And then we are going to just display this frame 1. So we can just say this is our feed, and the result after applying the contour will be saved in the frame 1, which we will display. Now in the next step, what we are going to do is we are going to assign the value inside frame 2 into frame 1. So we are going to just say frame 1 is equal to frame 2, and then inside our frame 2 we are going to read a new value. So we are going to just say ret comma frame 2 is equal to cap dot read. Okay, so we are reading the new frame in the variable frame 2, and before reading the new frame we are assigning the value inside the frame 2 to the frame 1. In this way we are reading the two frames and finding out the difference between the two frames. So let's run this code and let's see if it works or not. Let's test this. So you can see now there are these contours which are drawn around all the moving persons. Also there are some contours which are drawn around this rope which is also moving, right? So we have successfully determined the contours, and we have already drawn these contours on the frame 1. But this was not the result we are looking for. We want to draw the rectangle around these moving persons, and also we want some noises to be removed. So we don't want to draw the contour on the moving rope, let's say. Okay, so how to remove these noises and how to draw these rectangles, let's see. So now in the next step, what we are going to do is, under or before we are drawing these contours, we don't want to draw the contours now. We want to draw the rectangles, right? So what we are going to do is we are going to iterate over all the contours. So we are going to just say for contour. So from contours we are going to find out contour in contours, right? So this is the list and we are iterating over this list. So inside this for loop, the first step will be to save all the coordinates of the found contours. Okay, so we are going to define the x coordinate, then the y coordinate, and then we are going to just say width comma height. And there is a method called bounding rect which we are going to apply on the contour. So we are going to just say is equal to cv2 dot bounding rect. This is the method which we are going to apply, which is going to give us the x and y coordinate and the width and height, right? And we are going to apply this bounding rect method on the contour which we are getting using this contours list. Now in the next step, we are going to find out the area of the contour, and we are going to just say if this area is less than certain value, then we don't want to do anything. We don't want to draw a rectangle or anything. We just want to continue. Otherwise, if this contour area is greater than let's say some kind of a person's area, then we want to draw a rectangle on it. So inside this for loop, we are going to just define a if condition. So we can say if cv2 dot contour area. So there is a method called contour area, which is this one, where we can pass our contour. So we are going to pass our contour, and if the area of this contour, let's say, is less than 700, then we are going to just say continue. So this code essentially mean that if the area of the contour is less than 700, then we are going to do nothing. We don't want to draw any rectangle. Otherwise, if the area is greater than 700, then we want to draw the rectangle. So we are going to just say cv2 dot rectangle. We have already learned how to draw a rectangle on an image using the rectangle method. The first argument here will be the source, which will be frame 1. The second argument will be the point 1. So we are going to just say point 1 will be x comma y. The third argument will be point 2. So we are going to just say x plus w comma y plus h. The next argument will be the color. So let's say the color will be the same, 0 comma 255 comma 0. The next argument will be the thickness. Let's say we want to give the thickness 2, as we have done with the draw contour. We have provided the thickness of 2 here, right? Now in the next step, we are going to just print some text on the image if some movement is observed. So we can just say cv2 dot put text. This also we have seen in the previous videos how to put text on an image. So this time the source will be our frame 1. The second will be the text. So we will just say status, let's say, and if there is some movement, we are going to just say colon in the curly brackets. We are going to just use the format method. So this is just formatting the result using the string, and we are going to just say movement. The next argument here will be the origin. So where we want to put this text. Let's say we want to put this text on 10 comma 20 coordinate, and then the next argument will be the font face. So we are going to just say font face will be cv2 dot font Hershey simplex, let's say. So we are going to use this font, and the next argument will be the font scale. So let me just do this on the next line. So font scale will be, let's say, 1. The next will be the color of the font. So let's say the color will be 0 comma 0 comma 255, and then the last argument will be the thickness. So let's say the thickness will be 3, and this code is going to put the rectangle around your moving persons if the area of that contour is greater than 700. Okay, so let's run this code and let's see if it works or not. So I'm going to just run this code, and you can see that status is movement because all the persons here are moving, and you can see these rectangles which are drawn around the moving persons, and this noise which we were seeing in the previous result is also gone around the movement of this rope. Okay, so sometimes this rectangle is drawn on the movement of the rope also. So in this case you can also increase the expected area. Let's say we just want to find out the contours which are greater than 900, and we can now you can see these rectangles are drawn around these moving persons with the area which have the contour area more than 900. So you can remove these kind of noises from the frame using this area. So this was a very basic example how you can detect the motion and track your moving object inside your video using Python and OpenCV. In this video, we are going to see how we can detect simple geometrical shapes using OpenCV. So to start with, I have this simple code which reads an image and then show it into a IAmShow window. So let's run this simple code first of all, and let's see what it does. So you can see I have this image which I'm loading into a OpenCV window using IAmShow method, and here we have some shapes. So we have a pentagon, circle, rectangle, square, triangle, and this star shape, right? And let's say we want to detect using OpenCV which shape it is based upon the geometrical shape, and we want to write the name on top of this shape. So how we can achieve this, let's see using OpenCV. So as you can see, the first step is to read an image, and then in the second line I'm just converting this image into a grayscale mode image. So using this code I'm just converting this image into a grayscale mode, and in the next step we are going to find out the threshold. So I'm going to just say underscore comma thresh is equal to cv2 dot threshold. So cv2 dot threshold, and we are going to pass our image, which is a grayscale image which we have converted as a source, and then the next two values are the threshold values and the maximum value of the threshold. So for now I am giving the threshold value to 40 because I know this will work, but if you want to be more flexible you can always use the track bar to find out which threshold will work with your image. The second value is the maximum value of the threshold, and the next value will be the type. So the type here will be cv2 dot thresh binary. So we are going to just say cv2 dot thresh binary. Now in the next step we are going to find out the contours. So contours we have already seen in the last videos, how to find out the contours and what are contours. So for that I'm going to define two variables. One is contours variable, other is the underscore variable, because we don't need the second result. And then I'm going to just say cv2 dot find contours. The first argument here will be the thresholded image, and then the second argument here will be the mode, and third will be the method. So let's give these two values. So cv2 dot retr tree, and the method will be cv2 dot chain approx none. Okay, so let's give this method. So this is the simple procedure to find out the contours inside an image. Now in the next step I'm going to iterate over all the contours. So I'm going to just say for contour in contours. So we are going to iterate over all the contours, and then we are going to first of all use a method called cv2 dot approx poly dp. So I'm going to just declare a variable. First of all I'm going to just say approx is equal to cv2 dot this method which I have mentioned, which is called approx poly dp. So this method approximates a polygonal curves with a specific precision, and the first argument which it takes is the curve. So our curve here will be the contour which we have found on the shape. The second argument here will be epsilon. So epsilon is the parameter specifying the approximation accuracy. So here what we are going to do is we are going to define epsilon is equal to 0.01, and then we are going to multiply this number by cv2 dot arc length. So there is this method called arc length. And what does this arc length method do? It calculates a contours parameter or a curve length. So here in this arc length parameter, we are going to pass once again our contour variable, and the second argument here will be if it's closed or the open contour. So in our case, we know that all the shapes which we want to detect are closed, so we are going to just pass through here. And the next argument in the approx poly dp method will be once again if it's a closed shape or the open shape. So once again we are going to pass through here because all the shapes which we have are closed shapes. Now once we have this approximation, we are just going to draw all the contours first of all. So we are going to just say cv2 dot draw contours on which image? On our original image. So we are going to draw these contours on the original image, and then we are going to pass the second argument, and this will be our approximation. So we can in the square bracket, this is one other notation of just giving the number of contours as an argument to the draw contours method. So in the square brackets you can just pass the approx. The next parameter here will be the contour index. So because we are iterating over all the contours, that's why the index will always be 0, because there will be only one contour which we are working at a time. So this index will be 0. The next argument here will be the color. So you can give any color here. I am going to give 0, 0, 0, let's say. And then the next will be the thickness. So thickness I'm going to give here is 5. Now the next step is to print out the shape. So which shape it is, we want to print on the shape, which shape it is in simple English, let's say. So for that we need to find out the coordinates on which we want to print this text on the shape. So we need to find out the x and y coordinates. So we can find this x and y coordinates using this approx variable, and we can just say approx dot revvel. So this is a method called ravel, and then the first index here will be the x coordinate, and in the same way we are going to just say approx dot ravel, and on this method the second argument or the second index at index 1 will be the y coordinate. So on these x and y coordinates we are going to print our text. Now in the next step what we are going to do is, so because this approx poly dp is going to approximate the number of polygonal curves, so based upon the number of polygonal curves we can just approximate which shape it can be. So if this approx length, so let's just find out the length of this approx, and if the length of this approx variable is equal to 3, then we are going to say that it's a triangle, because triangle can be made with 3 points. So this length of approx variable, if it's equal to 3, then we are going to say that it's a triangle, because if the number of curves here are 3, then most probably it's going to be a triangle. So if we know that this is a triangle, then we can easily just print or put text on that image. So we are going to just say put text, and the first variable here will be the image. So we are going to put text on the image. The second variable will be the text, and we know that this will be a triangle. So we are going to just say triangle here, and then the next argument here will be the coordinates on which you want to print this text. So we already found out the coordinates at which we want to put this text. The next argument here will be the font. So we are going to just say cv2 dot font Hershey complex, and the next argument here will be the font scale. So let's say font scale will be 0.5, and the next argument here will be the color. So you can give any color. Let's say we just want to print this text in the black color itself. So we are going to just say 0, 0, 0. Then using this logic, we can also say that if the length of this approx is equal to 4, then it can either be a square or a rectangle. So here, if the approx length is 4, then it can be a square or a rectangle. But we don't know if it's a square or a rectangle. So for now, we can just write that it's a rectangle, and we are going to decide if it's a rectangle or a square in the next step. But let's define the other if else conditions also. So this was elif. Similarly, if number of approx points are 5, then we are going to say that it's a pentagon. So we are going to print out the pentagon text on the x and y coordinates. And if the number of points are 10, then we are going to just say that it's a star shape. So we are going to just say star, because in the star the number of points are 10. And then we are going to say that in any other condition, so we are going to just say else, and we are going to just remove this condition from here. Else, in any other condition, it's going to be a circle. Okay, so if approx length is 3, it's a triangle. If approx length is 4, it's a rectangle or a square. If 5, pentagon. If it's 10, it's a star. If it's nothing out of all these options, then it's a circle. You can also find out, for example, octagon or hexagon here. If it's 6, it's a hexagon. If it's 8, it's a octagon, and so on, right? Now let's once again come to this step, and in this step we just know that if the number of points are 4, then it's a rectangle or a square. But how can we find if it's a rectangle or a square? So let's decide that now. So what we are going to do for that is we are going to just say x comma y, and then we are going to just say w comma h for width and height. And there is a method called cv2.bounding rect, which is going to give us the x and y coordinates and the width and height of the rectangle, right? So we are going to apply that method. So cv2.bounding rect on our approximate variable or approx variable, which is going to give us the x and y coordinate and width and height. Now based upon the width and height, we can find out the aspect ratio. So we are going to just say aspect ratio is equal to float. First of all, we need to typecast the width into a float. So we are going to just say float w divided by height, and this will be the aspect ratio of the rectangle. Now if this aspect ratio, let's print out the aspect ratio also, so we know what aspect ratio we are getting using the rectangle or the square. And we are going to just say if this aspect ratio is between 0.95 and 1.05, then it's going to be a square, right? Because the width and height are almost same. Okay, so we just give some room for some noises. That's why we are providing here. Ideally it should be a 1, aspect ratio should be 1 in order to have a square, but let's say we are just approximating, so we can just say if it's 0.95, if it's greater than 0.95, and if it's less than, so aspect ratio is less than or equal to 1.05, then it's a square. Okay, in ideal situation you might want to give here 1, but in images it can be a little bit different, so we are just giving this limit. So if the aspect ratio falls in this limit, then it's going to be a square, otherwise it's going to be a rectangle, right? And I'm going to just say that if this is the case, then it's going to be square, otherwise. So in the else condition, so let's give this else condition here, else it's going to be a rectangle. So let's print rectangle in the put text. Okay, so this is the code which we have written. And now finally what we are going to do, we are going to just show the shapes image, including all the contours and the text which we have put on these shapes. So let's run this code and let's see if it works or not. So you can see now it's going to work like this. So all the contours are drawn across these shapes, and you can see the text on top of these shapes. So circle, rectangle, pentagon, star, triangle, and squares. What you can also do here is you can just change this text position using the x and y coordinates. So let's say I just want to change this y position to just little bit top of the shape. So I just added -5 offset here in the y-axis, and now you can see it goes little bit up, this text, right? So now it's much visible, this text. And you can see rectangle and square text is not going up because we have declared the local x and y here also. So we can just say x1 and y1 here, and then run this code once again, and you can see this rectangle and square text is also moved little bit up. So I think the offset of 5 is okay to show these text on top of these shapes. So this is how you can detect simple geometric shapes using OpenCV. In this video, we will discuss about histograms in OpenCV. So what is a histogram? So you can consider histogram as a graph or a plot which gives you an overall idea about the intensity distribution of an image. So let me give you some examples, and then I will be able to explain you better how histogram works and why they are useful. So to start with, I have this example which is a very normal example. Here I'm creating 200 by 200 pixel image using Numpy zeros, which essentially mean that we are going to get a 200 by 200 pixel image of black pixels. So let me just start this example, and you can see this is the final result. So all the pixels here in this image are black, and the size is 200 by 200. Now let's say we want to calculate or find out the histogram of this image. So there are several ways of finding out histogram of an image. So let's see them one by one. So first of all, we are going to find out the histogram using the matplotlib because the plot using matplotlib you can draw easily. So let's use that first of all. So for that, what I'm going to do is I'm going to use PLT because I have already imported this matplotlib library as PLT. So PLT dot hist, there is a function called plt.hist which calculates the histogram of an image. And because it's just a grayscale image or it's just a black image, so it's easier to find out the histogram. So what you can do here is the first argument here will be your image or your source. So I'm going to just say image dot ravel. Okay, so there is a method called ravel. The second argument here will be maximum number of pixel value. So I'm going to just say 256. The third argument here will be the range. So the range will vary from 0 to 256. Okay, so this is all you need to find out the histogram using the matplotlib, and you just need to show this plot in a matplotlib window. So you can just say plt.show. So that's it. So let's run this code and let's see what happens. So you see this plot using matplotlib and also our original image. So as we have created the image of 200 by 200 pixel of black pixels, so all the intensity of this graph you can see is 0. So you can see here 200 multiplied by 200 is equal to 40,000. So these are the number of pixels. So on the y-axis you will see total number of pixels, and here the intensity. So intensity starts from 0 to 256. So this graph is showing how many number of pixels inside an image which have this pixel values. So in our example, all the pixels inside this image have the pixel value 0. That's why this graph is like this. So all the 40,000 pixels inside the image have the pixel value 0. So you will get this type of histograms. So once again, the histogram is a graph or a plot which gives you the overall idea about the intensity distribution of an image. Now histogram is just another way of understanding the image. By looking at the histogram of an image, you can get the intuition about the contrast, brightness, intensity, distribution, etc. Now let's improve this example which we have. So I'm going to just close this window, and let's say I want to add some white pixel also inside this image. So what I'm going to say is I'm going to just cv2 dot rectangle. So I'm going to just add the rectangle inside this image, and the source here will be the img variable. Then where I want to introduce this rectangle. So I want to introduce this rectangle at this point, which will be, let's say, which starts from 0 comma 100, and the second point here will be, let's say, 200 comma 200. Okay, so this will be 200, and the next value here will be the color. So let's say we want to add the white pixels. So this will be 255, which will be the maximum value, and then the next argument will be the thickness. So I'm going to just say -1, which will fill this rectangle inside this image. So when I run now this code, you will see this graph and this image. So you can see half of this image contains black pixels and half of this image contains the white pixels, and we already know that the size of this image is 200 by 200. That's why here in the graph you will see 20,000 pixels are black, which means that 20,000 pixels have the pixel value 0 and 20,000 pixels have the pixel value 255. That's why you see this here. So you can see, you can easily find out the pixel intensity of an image easily using histograms. Now next we are going to add some more pixels into this image, and this time what we are going to do is we are going to add the rectangle inside the same image. So let's say it goes from 0, 50 to 100, 100, and the color here we are going to provide the pixel value of 127, let's say. Okay, so which is the half of 0 and 255 approximately. So I'm going to run this example once again, and now you will see this kind of image. So you can see half of the pixels here are white. That means 20,000 pixels have the pixel value of 255. So you can see here. Now around 15,000 pixels here in the half of this image have the pixel value of 0. That's why you can see this line here, and we have added the rectangle of pixel value 127 also. So around, you can see around 5,000 pixels here have the pixel value of 127. So this is how the histogram is going to work. So let's use now the original image, so some kind of image instead of this black or white image. So now what I'm going to do is I'm going to just once again declare a variable, and then I'm going to just say cv2 dot I am read, and we are going to read some file. So let's say I have this lena.jpg image, so I'm going to just read that. I hope the extension is correct, jpg, and we are going to read this image in the grayscale mode. So I'm going to just say 0 here, and now I'm going to run this example once again, and you can see this Lena image is loaded in the grayscale mode, and here is the histogram of this image. So these are all the pixel intensities inside this image. So you can see from this graph that most number of pixels contained inside this image have the pixel value around 150. Now you can also find out the pixel intensity of different colors. So till now we have been just using the grayscale mode or black or white pixels, but you can also use the same histogram for the BGR values also. So let's see how we can do that. So what we are going to do is, let me just remove this code, or I'm going to just leave it commented, and here I'm going to just say b comma g comma r, and there is a method we have already seen which is called cv.split, which is going to split your image into BGR values. So we are going to just give the source, which is our image, and then if you want to show these BGR values, you can just show in the I'm show window. So BGR, and here also BG and R, and when you want to show the histogram of BGR values, then also you can use matplotlib.hist method. You just need to change this source from image to BGR. So B, G and R. Okay, so now what we are going to do is we are going to run our code, and let's see what happens. So it's giving me this error because I'm reading this image in the grayscale mode. So I'm going to remove this extra parameter from IMRead, because we want to read this image in the color form, and then only we will be able to get the BGR channels, right? In the grayscale mode, there are no BGR channels. So I'm going to run this script once again, and let's see what happens. So you can see this histogram of blue channels and green channels and the red channels, and these are the images which are loaded in these different channels. So this is the image which is loaded in the blue channel, and this is the green, and this is the red channel, and you can see the histogram of each channel differently using matplotlib. So let me just close all these windows. Now there is a method in CV2 also, which is called calc_hist, which is going to give you the histogram of an image. So for that, what you can do is, I'm going to just comment all this code, because I just want to show how you can use the CV2 calc_hist method. Okay, so what you can do is, you can use a method. So let's say hist and then cv dot calc_hist, and this method takes few arguments. So the first argument here will be the image. So it's the source which you give, but the only special thing is you just give this image in the square brackets. Okay, the second argument here is the channels. So it is the index of channels for which we calculate the histogram. So here in our case, because we are going to read the image in grayscale mode, we can just give the channel 0 here. So for one channel you can give 0 here, for different channel you can give 0, 1, 2 value. The next argument here is the image mask. So to find histogram of full image, it is given as none, because our image is loaded in the grayscale mode, so we can give here none. The next value is the hist size. So this hist size is the representation of bin counts, and this is also given in the square bracket. So we are going to just say 256 here. The next argument is the range. So range will vary from 0 to 256. So minimum and the maximum range of the x-axis, you can say. So 256, and then we can just show this hist or histogram inside the plt. So plt.plot method. So dot plot, and then we can just give this histogram value here. Okay, so let's run this code and let's see what happens. So you can see you get the histogram of this image using the OpenCV calc_hist method. And what are the uses of the histogram? So a histogram can tell you whether or not your image has been properly exposed. So when you take a digital image, it's very useful. It can also tell you whether the lighting conditions were flat or harsh when you took that image, and using the histogram you can also make the adjustments which will work best for your digital images. So this the usefulness of the histograms we will see in the later videos. This was just the basics about the histograms in OpenCV. In this video we will discuss about template matching in OpenCV. So first of all, what is template matching? So template matching is a method of searching and finding the location of a template image inside a larger image. In OpenCV, there is a method called match template for achieving this purpose. So let's get started and let's see an example about it. So I have this simple code which just loads this image, and let's see what this image looks like. So this is the image, and this is the messy image, and what I want to do is I want to match the face template which I have, which looks like this, which is the smaller template which is also available inside this image. So this will act like a template for us, and we will try to find this template inside this larger image. So let's get started and let's see how we can search this template inside this larger image. So first of all, what we need to do is obviously we need to load this image and also load our template. So before loading our template image, I'm going to just convert my original image, which is the larger image, into the grayscale image. So I have declared this variable gray underscore image, and then I'm going to just say cv2.cvt color, which is going to convert my image img, and let's convert this image into cv2.color underscore bgr to gray. Now let's load our face image, which is called messy underscore face dot jpg. So I'm going to just change this name, messy underscore face dot jpg, and this will be our face image, or you can also say this is a template. And I'm going to also load this image as a grayscale image. So I'm going to just pass the second argument in the read method as 0, which is going to load this messy image as a grayscale image. Now in the next line we will simply use this method which is called match template, and we are going to save it into some variables. So we can just say res is equal to cv2 dot match template, which is this method which takes few argument. First is our image, so I'm going to pass our grayscale image here. The second argument here will be the template which we are trying to search inside this image. So this will be our template. The third is the method. So the method can be several method. There are several methods available for the template matching. So I want to show you these method for the template matching. So you can see type of template matching operations, and there is separate formula involved in order to match that template inside that image. So for now we are going to use this method, which is tm underscore c coef underscore normed dot tm underscore c coef normed, which is this method. Now let's try to print this result, and let's see what is the content inside this result. So I'm going to just print the content inside this result which we got. So I'm going to run this code, and this image is loaded, but for now we are interested in this array matrix which you are seeing here. So you can see when you observe these values carefully, you will see all are relatively smaller values. So you can see 0.2, 0.2, almost every value is around until 0.3. So the maximum value I can see here is 0.3. So let me just show this image once again, and the template also. So what this result contains is these all values, and there will be one value which contains the number, for example 0.8, or the brightest point. Okay, so if here this matrix contains a value which have the value 1, it is the brightest point, and it will be there inside this image after applying this match template method, which will be around this point, at which this template matches. So top left corner of this template. So at the point at which this left top corner of this image will match inside this large image, there will be a brightest point there, and that brightest point will be reflected inside this image in the form of this decimal number, and all the other values will be slightly darker values. Okay, so that's how this matrix, from this matrix we will come to know the top left corner of the template inside this larger image. So now how can we filter out that value which is the brightest point inside this matrix? So all the points you can see looks like under 0.3, but there are some points here. You can see 3 dots, and there are thousands and thousands of values will be available here. All the values are not printed. Okay, so what we are going to do is we are going to try to find out the brightest point. So this we can find out with the Numpy method. There is a method called where, using which we can find out or filter out those values which are greater than certain number. So I'm going to first of all declare a variable called threshold is equal to, I'm going to declare the value of threshold initially as 0.8, which will be a relatively brighter point inside the matrix which we are getting using this result variable, right? And then there is a method called where, Numpy where. So I'm going to declare once again loc variable, and then np dot where method, and here we are going to pass our result which we got, and we are going to filter out using this expression. So this will be a Boolean expression. So I'm going to just say give me all those values which are greater than or equal to the threshold inside this result matrix. Okay, so this where method is going to just evaluate this expression. Each and every value will be evaluated, and if this value inside the matrix is greater than 0.8, which is our threshold, then it's going to give those values to us. So let's print out those values after the filtering out of most of the values, and let's just print this loc variable also. So I'm going to run this code once again, and you can see here this is the matrix which we got. So you can see this is the array which we got. So still we can increase this threshold in order to find out only one point. So there are several points available here. So let's say I'm going to increase this value to 0.9, and let's run this code again, and you will see only 2 points, 85 and 220. So this is what we were expecting. So we wanted to find out this point which will be the brightest point inside this result matrix. So once we got the brightest point which will be around here, which will be the top left corner, as I said, of this template, and it will be located somewhere here in the original image, then we can draw the rectangle around this original image, same as the size of this template. So this will be the easier task, because we already know the width and height of this template. We already know how to get the width and height of this template, and same size rectangle we just want to draw on this original image. So let's see how we can do this. So there is already a method, so I'm going to just declare two variables, width and height, and you already know the method. So template dot shape is going to give you the shape of your image, right? So I'm going to just say template dot shape, and then inside the square brackets we are going to just give two colons and -1. This means that we want to get the column and the rows value in the reverse order, so width and height. That's why I have given this -1 index here. Now in the next step, what we are going to do is we are going to just draw all the rectangles where the template is matched. So by seeing this template image and the original image, we know that there is only one messy face inside this image. But let's say there are several number of matched templates inside our original image. For that we need to iterate over the result which we got after applying the filter on the result. So for that we are going to just iterate over that result. In our case, as we know that there is only one point, so we don't even need to iterate over it. But if there are multiple number of matched templates, then this for loop will be handy. So for PT in your LOC variable, so we are going to just say zip, which is going to iterate over this LOC variable. So asterisk LOC, and then we are going to find out the width and height here also. So we are just reversing the x-axis and y-axis, right? So we are going to just say colon colon -1 here, and then once again inside this for loop, so cv2 dot rectangle method, and the first argument here will be our original image because we want to draw the rectangle on the original image. The second argument will be the first point of the rectangle. So the first point will be this one PT, which we are getting using the LOC variable. So as you all know that the first point here will be the top left corner of the rectangle, and the second point here will be the bottom right corner. So how can we get the bottom right corner? We will get the bottom right corner using this PT variable, and then on the 0th index we are going to just add the width, comma, on the first index, so PT square bracket first, we are going to add the height. Okay, so essentially we have just found out the width and height of our template, and we are getting the second point using this addition on the first point, width and height. So it's going to give us this bottom right corner of this template or this point. So this is how we are getting our 2 points to draw the rectangle. Now the third and fourth variable will be simple, which are the color. So you can just say 0, 0, 255, which will be the green color, and the width, let's say 2 here. So we want to give the width 2 here. So let's run this code and let's see what happens. So I'm going to run this code, and you can see this red rectangle is drawn on the face of the messy, and you can here also see this rectangle will match our template image. So whatever image is inside this rectangle will be exactly same as our template. And once again you can see the result. Let me explain this code once again. So if this point, this threshold will be 0.08, let's say, In the case of 0.09 threshold, we are only getting two values, this 85 and 220, right? That's why we are seeing the clear rectangle here. When we are giving the threshold 0.8 here, let's see what happens. So I'm going to run this code once again. You can see there will be this rectangle, but it will be much thicker. Why it's much thicker? Because we are getting several number of values, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we are getting the 9 points on the x-axis and the y-axis. So this for loop will iterate 9 times, and this rectangle will be drawn 9 times on the image, and that's why this rectangle is much thicker. Let's just change this value to 0.9 once again, and you will see this rectangle is the single rectangle. That's why it's much thinner, right? Now when you give this value, let's say we give the value 0.3, so most of the point, as you can see here, have the value 0.3, and when we run this code, you will see so many rectangles here. So that's why this thresholding is essential for us to find out the brightest point or the value which have the maximum value, right? So that's why we were filtering out these points and finding out the values more than 0.9 threshold. And about the methods, so let's try different methods. So let's try to give different methods here. These two methods behave a little bit differently. So we can start with this TMCORR normed, and we can apply it here, and it's going to give us this kind of result. You can see we are getting several points here after filtering. So let's try to increase this value to 0.95, and let's rerun this code, and let's see what happens. So now you are getting 4 values. You can also filter that out. Let's say 0.99. Now let's see what happens. So now you are getting only 2 values. Okay, so you need to try to change this value to the maximum point. So try to change this value, and you will get this kind of rectangle, only one rectangle. So every method is going to give you different result, and that's why you need to try all the result. Not all the result will give you the perfect rectangle or template matching, so you need to try different methods on your images. So this is how you can do template matching in OpenCV. In this video, we will understand the concept behind half transform. So first of all, what is half transform? So half transform is a popular technique to detect any shape if you can represent that shape in a mathematical form. Half transform can detect the shape even if it is broken or distorted a little bit. Now this explanation might seem a little bit confusing, so let me explain it by an example. So let's say you have an image of this road and you want to detect these lane lines in this road image. So the first step in order to detect these lane lines in this road is to find the edge pixels using canny edge detection or any other edge detection method. Now after you found out the edges using any edge detection method, you want a geometrical representation of that edge. And in order to find out the geometrical representation, for example, you want to find out the slope of this edge or its intercept, you can use half transform to represent these pixels or edges in the mathematical or geometrical form. So after you find out the edges using any edge detector, you just have the sequence of pixels, so you can loop through all the pixels and somehow figure out the slope and intercepts, but it's a very difficult task. So we want some mechanism that gives more weightage to pixels that are already in line, and this is what we can achieve using Huff transform. So let's begin and let's start with the lines. So a line in the image can be represented by two coordinate systems. First is using the Cartesian coordinate system, and using this equation you can represent a line which is y is equal to mx plus c, and you can also represent this line using polar coordinate system using this equation, which is x cos theta plus y sin theta is equal to r or rho sometimes. So let's start with this equation first, which is a Cartesian coordinate system equation, which is y is equal to mx plus c. So when you represent a line in x and y coordinates, which is also called the xy space, this equation looks like this. So y is equal to mx plus c, where m is the slope of the line and c is the intercept of this line. So if you know the values of m and c, you can represent this line in the x and y coordinates. Now in Huff transform, you can represent this line in other form also, and this is called the MC space or the Huff space. So using this equation, when you take m on this axis and c on this vertical axis, then this is called the MC space. So earlier we have represented this line in the xy space, and now we are saying that we want to represent this using the MC coordinate, where m is on the horizontal line and c is on the vertical line. So when you represent this simple line in the MC space or the Huff space, it can be represented as a point. So this line can be represented as a point. So we all know that a line is a collection of points, and managing the collection of points is tougher than managing a single point. So if you want to manage a collection of points, and if you were to manage a single point, which will you prefer? And an obvious answer will be to manage the single point. And this is what this MC space is doing. It's representing a line in the form of a point in MC space or the Huff space. And the opposite of this concept is also possible. So if you can represent a point using these coordinates in the xy space, then it can be represented as a line in the MC space. Okay, and the formula now will turn into this equation, which is c is equal to minus xam plus ya, right? So you can represent a point, and if you have the x and y coordinate in the MC space, you can represent this as a line, and this will be the equation where x will be the slope now and y will be the intercept. Earlier m was the slope and c was the intercept, but when you just transform or just represent this point into MC space, then your x becomes, or minus x becomes the slope and y becomes the intercept. So how does these concepts are going to help us? So the Huff transform is all about doing what we have learned, converting points in the xy space to the lines in the MC space or the Huff space. So for example, you can see 4 points, 1, 2, 3, 4, which are joined by a line, right? So you can represent these 4 points and you can join all these 4 points, and it's a representation of a line, and here slope is equal to m and intercept is equal to c in the xy space. The same line you can represent in the MC space using these 4 lines. Okay, so every point is a line in the MC space, and you see the intersection point here, which is on the MC coordinate. So you have taken an edge detected image, and for every point that is a non-black point, you draw lines in the MC space. And obviously when you draw these lines will intersect with each other, and these intersections mark are the parameter of a line. Okay, so in the MC space you can represent each and every point as a line, and they will intersect on a single point, and now this intersection point can be used to draw a line. So this was the representation of points in a line using MC space using a Cartesian coordinate system. Now let's apply these same concepts which we have learned using the Cartesian coordinate system into a polar coordinate system. So as we all know that in the polar coordinate system we can represent a line using this equation also, which is r is equal to x multiplied by cos theta plus y multiplied by sin theta. Or in other form, you can also represent this equation like this, where y is equal to minus cos theta by sin theta multiplied by x plus r divided by sin theta. So this is your xy space where line can be represented like this, and we are going to transform or represent this line using this equation into the r theta space or the half space. Okay, so this line using this equation can also be represented as a point in r theta or the half space like this. So let's take an example about this. So as I said, the equation was r is equal to x multiplied by cos theta plus y multiplied by sin theta, where this theta is the angle of the line and r is the distance from the origin to the line. So let's say we want to represent a point which is from xy space into a half space into r theta space. So we give the values of x0 and y0, which will be the first point. We can represent this point in the form of line in the half space or the r theta space in this formation, which looks like a sine curve using this equation. So this is for the 1 point representation in xy space to a line representation in the half space. So let's say you have multiple points. So we take 3 points, then it's going to look like this. So let's say x0 is equal to 8 and y0 is equal to 6, x1 is equal to 4, y1 is equal to 9, and x2 is equal to 12 and y2 is equal to 3. So we have 3 points in the xy space. They can be represented in the half space using 3 lines. And as we have seen in the Cartesian coordinate system, these points can be represented in these lines in the half space in the polar coordinate system also using these curved line. And this intersection is going to represent a line in the half space. So which representation we are going to use in order to use the half transform? So this equation is not able to represent the vertical lines. That's why generally we use this equation or a polar coordinate system in order to use half transform. So the half transform algorithm involves these 4 important steps. In the first step, edge detection is done using Kenny edge detector or any edge detection method. In the second step, mapping of the edge points to the half space is done, and all these edge points are stored in an accumulator. In the third step, interpretation of accumulator to yield lines of infinite length is done, and this interpretation can be done by thresholding or any other constraint. The fourth step involves the conversion of infinite line to finite lines. Now OpenCV implements two kinds of half-line transforms. The first is the standard half transform, which is done using half lines method. The second type is the probabilistic half line transform, which is done by half lines P method. So this is the half lines method and this is the half lines P method. In the last video, we have seen a brief theory introduction about half line transform. So I have told you that OpenCV implements two kinds of half-line transforms. One is a standard half-line transform using half-lines method, and the second is the probabilistic half-line transform using half-lines capital P method. So we are going to use the half-line method in this video and see how we can use this half-line method to detect the lines inside an image using half transform. Now, I also told you that there are 4 steps associated with half transform. So the first step was the edge detection step using any edge detection method, preferably Kenny edge detection. The second step is the mapping of edge points to the half space and store these edge points to an accumulator. The third step was the interpretation of accumulator to yield lines of infinite length, and the fourth step was the conversion of these lines to the finite lines. So let's say we have this image of this sudoku.png, and you can see all these lines here which we want to detect. So this is the line and this is the line. So all these lines we want to detect using the half line transform. So I have already written this code. So I'm going to go step by step to explain how this code works. So in the first step, you just need to import the normal CV2 and the Numpy as NP. Then here I'm just reading this image using imRead method. In the next step, I'm converting this image into a grayscale image and storing it into this variable which is gray, because for Kenny edge detection it's preferred to have grayscale images rather than your normal colored images. Now in the next step, we are applying the Kenny edge detection method on this grayscale image. So here this cv2.kenny method takes these arguments. First argument is the image, second and third argument is the first threshold and the second threshold. So I'm giving the first threshold as 50 and the second threshold here as 150, and the fourth argument here I'm giving aperture size is equal to 3. Now in the next step, I'm using this half lines method. This is the normal half transform method which is implemented in OpenCV. Now this half line method takes few arguments. The first argument is the image. So we are just passing this edge detected image to the first argument of this half lines method. The second argument here is the row value. This row value is the distance resolution of the accumulator in pixels. Normally it's taken as 1. The third value is the theta value, which is the angle resolution of accumulator in radians. So for that we are just using Numpy. So np.pi divided by 180. So this is also typical in this method. And the next argument here is the accumulator threshold parameter. So what does this mean? It's a threshold. So only those lines are returned that get enough vote. That means that those lines will be returned which have threshold greater than this value. So starting value I have taken here as 200 as threshold. So now this half lines method is going to return the output vector of lines. Now I have explained you how polar coordinate works for the half transform in the last video. So these lines will be in the polar coordinate. So each line is represented by 2 or 3 element vectors, either rho and theta or rho, theta and votes. So as you can see, this is the output vector of lines. So I'm going to iterate over each and every line vector, and what it gives is the first element of this line is going to give you these two values, rho comma theta. It's going to give you rho comma theta or rho comma theta comma vote, right? So right now I'm using just two parameters here, rho comma theta. So rho is the distance from the coordinate 0, 0, which is the top left corner of the image, and the theta is the line rotation angle in radians. So all this rho and theta I have explained you in the last video, and we have seen how we can represent these rho and theta values in the half space. So first of all, what we are going to do is, once we get the rho and theta value, is we are going to just get the cos theta value and the sin theta value, because we want to convert these polar coordinates into the normal Cartesian coordinates for the line method. Because this line method, as you can imagine, takes these coordinates, right, which are the Cartesian coordinates. So this is the 0.1 parameter and this is the 0.2 parameter. So x1 y1 and x2 y2. So first of all, we are just getting the cos theta value, and theta here is this theta. So cos theta we are just assigning to A, and the sin theta value we are just assigning to B, and we are just multiplying this A to the rho. So this will give us the x0 value and the y0 value when you multiply B by rho. So this rho is this rho value. So this x0 and y0 is going to give you the origin, which is 0, 0 or top left corner of the image. But we want the lines, not the top left corner of the image. So how we can get these x1 and y1 coordinate and x2 and y2 coordinate? This is given in this equation. So once you get your x0 and y0 value, you can get the value of x1 and y1 coordinate using this equation. So you just need to typecast everything into integer. So this equation, x1 value stores the rounded off value of rho, as I have shown here. So this r represent rho. So rho multiplied by cos theta. Cos theta we have already taken in the a variable. So we are essentially here multiplying the rho multiplied by cos theta minus 1000 multiplied by sin theta. Sin theta value is the value of the b, right? So x0 plus 1000 multiplied by minus b here. Okay, y1 we get using this equation. So y1 is equal to int in the bracket y0 plus 1000 multiplied by a, which is essentially this equation, which is rho multiplied by sin theta plus 1000 multiplied by cos theta. So these two values are going to give you the first coordinates, and similarly we are going to get the x2 and y2 coordinate using these two equations. So here everything is same, just this minus is new, right? So in this equation you just need to replace a plus by minus and you get the x2 value. Same you have to do in the case of y2. So in this equation, if you just replace this plus by minus, you will get the y2 value. And we have already seen how to use the cv2.line method. It takes a few arguments, as you can see here. First is the image. So image is our original image. Second is the x1 and y1 coordinate, which is the first point, comma the second point. So as you already know that a line is a collection of points, so you need at least 2 points to create a line, right? So this is the coordinates of the first point and this is the coordinates of the second point. The next argument here is the color. So color I have taken simply 0, 0, 255, and the last parameter here is the thickness of the line, which I have taken 2 here. And the next line of code you already know, I think. So after this line we come out of the loop and we are just plotting all the lines using this loop on the original image. And once we get all these lines on the original image, we are just showing it using IamShow method, and at the last we are just destroying our window once we are done with the image. So let's run this code and let's see what happens. So I'm going to run this code and you can see all these lines are plotted here. Let's see the Kenny edge detected image also. So I'm going to just after the Kenny edge detection, I'm going to once again add this IamShow method to show the Kenny edge detected image also. So you can see here, this is the Kenny edge detected image. All the edges are detected, and based upon all these lines which are detected here, these lines are drawn. But the problem here is these lines are of infinite length, so there is no end to these lines. These lines just go from the start or the corner of the image to the other corner of the image. So you can see they start from here and go to the next corner. They don't just stop here. So in this half transform, you see that even for the line with 2 arguments, it takes a lot of computation and we don't even get the correct result. So this problem can be solved using the other method, which is implemented using this half line P method, which is the probabilistic half line transform, which I'm going to show you in the next video. So how we can get the better result using half line P method, we are going to see in the next video. In the last video, we have seen how to use standard half transform using half lines method in OpenCV. Now in this video, we are going to see how to use probabilistic half line transform using a method called half lines P method in OpenCV. So let's go to our editor, and this was the code we have written last time, and we have used half lines method for detecting lines inside this image, which was the Sudoku image. So let's run this example really fast to see what was the result which we got last time. So this was the result which we got last time, and the problem with this result is you can see these lines just go from one end to the other end, and in this kind of half transform you will be able to see that even for the lines which have 2 arguments, it takes a lot of computation. So in OpenCV there is also a method called half lines P, which stands for probabilistic half lines transform, and this probabilistic half line transform is an optimization of the normal half transform which we have seen in the last video. So let me close this example and let's open the example which we are going to see in this video. And you can see in this example we have used this half lines P method. So when we use this half lines P method, it doesn't take all the points into consideration. Instead, it takes only the random subset of the points which is sufficient for the line detection. So let's go through this code from the top to the end. So as you can see, I have imported these two packages, CV2 and Numpy as NP, and then I'm reading this image Sudoku using imRead method, and then I'm converting this image to the grayscale image using CVT color method in CV2. Now the next step is to find out the edges of the images. This we have also seen in the last video. So until here everything is same. So once we got the edge detected image using Kenny edge detection, instead of using the half lines method, we are now using this half lines capital P method, and it takes few arguments. The first argument is your edge detected image. The second argument is the row, which is the distance resolution of the accumulator in pixels. The third argument is the theta value, which we have taken np.pi divided by 180, which is the angle resolution of the accumulator in radians. The next value is the threshold. So right now we have taken this threshold as 100, and this threshold is the accumulator threshold parameter, which means that only those lines are returned that get enough vote, that means greater than the threshold value. The extra two arguments here are a little bit different from the half lines method. So you can see all these arguments are almost same, these four arguments, but there are two extra arguments here or parameter here which we need to provide. So the first parameter here is the min line length, and this we have taken 100. So this min line length is the minimum length of the line, which means that line segments shorter than this length, which is 100 in our case, will be rejected. The next argument is the maximum line gap, and it is the maximum allowed gap between the line segments to treat them as a single line. So these are the two extra arguments we have taken, and this half lines capital P method is going to return again the output vector of the lines, but the difference between this return value from half line P method and the half lines method is, you can see here, this line at index 0 is going to directly give you the values of x1, y1 and x2, y2, which are the 2 points which we will be able to join, and we will be able to draw the line using cv2.line method. In the last video, I have shown you that you have to do so much calculation in order to find this x1, y1 and x2, y2, and this probabilistic half line transform method is going to do our job easy, and it's going to directly give us these four values. So you don't need to do anything, you just need to pass these x1, y1 and x2, y2 value to the cv2.line method. So cv2.line method is going to take the first argument, which is the image, and then the second argument is the point 1 coordinate, which is x1 and y1, which we got from the line variable at index 0, and the third parameter here is the point 2, which are the coordinate of the point 2, which is here x2 and y2. The next argument here is the color, which we have taken right now 0, 2, 55, 0, and the last parameter here is the thickness of the line, so we have taken 2 here. And the next 3 lines are going to just show this image. First of all these lines which we found out are drawn on the image, this image which is the original image, and then we are just showing this image after drawing all the lines which we got using half lines P method on the original image, and then we are just loading this image using this I'm show method, and then after we are done, we are just destroying all the windows. So let's see what result we get after this script is run. So I'm going to run this script, and this is the canny edge detected image, and this is the image you got when you apply this huff lines p method on your canny edge detected image. So you can see these lines are no longer going to the end to end. These are more accurately detecting all the lines which are there in this Sudoku image. You can see some lines are broken here, so that's why these lines are not even drawn, because they are not even detected by canny edge detection. So this one or this one are not detected by canny edge detection, so that's why these lines are not drawn. So let me show you these results side by side. So this was the result which we got after applying the huff line transform method, which is huff lines on our canny edge detected image, and you can see all these lines here, and this is the result which we got after applying huff lines p method, which is the probabilistic huff line transform. So these two methods are available in OpenCV to detect these lines in an image. Now let's go back to our script, and here instead of this image, which is the sudoku.png image, I have one more image which is called road.jpg, and this is the image which contains a road, and inside this road we have some lane lines. So you can see this result now here, which is the road, and these are the lane lines which are detected using this huff lines p method. So in case of lane line detection, you can use this huff line p method, but you need to decide your ROI or region of interest, because you can see some lines are detected here, 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 and here. So you just need to define your line of interest region, and you will be able to detect all the lines or lane lines on the road. So maybe in the next video we are going to see how we can detect these lane lines on the road accurately without these noises which we are seeing here on the other part of the image. So we just need to detect these lane lines and nothing more, and we will do the same on a video. So on the video in which these lane lines are there, and we just need to continuously detect these lane lines. So in the case of, let's say, self-driving car, you need to detect these lane lines. We are going to see how to detect these lane lines. In the last videos, we have learned some important concepts in OpenCV. Now in this video and the next few coming videos, I'm going to create a simple project which uses most of these concepts which we have learned in the previous videos. So what we are going to do is we are going to create a very simple lane detection system. So first of all, we will start with a still image. You can see there is an image which contains this road, and this road contains lanes. So what we want to achieve is we want to detect these lanes on which our vehicle is traveling. So first of all, we will do this with this image, and gradually we will move towards the video frames. So first of all, we will see how to detect these lanes in this image, and then we will see how to detect these lanes in the moving video. So let's get started. So I have created this new project in my PyCharm IDE. You can use any other editor of your choice, and first of all, obviously you just need to install OpenCV Python package and matplotlib package. Once you have done that, I will create a new file here. So I'm going to just right click here and create a new file, and I'm going to name this file as detector.py file. So here we are going to import a few packages, for example matplotlib. So matplotlib .pyplot as plt. So let's say as plt. Also we are going to import the cv2 package, and we are going to import numpy. So import numpy as np. In the next section, what we are going to do is we are going to simply load an image. So I'm going to create an image variable. So image is equal to cv2.imRead, and we are going to read our image, which is the road image. So road.jpg. Now in the next line, we are going to convert this image into the RGB format, because we are going to load this image using matplotlib. So I'm going to just write once again image. So I'm going to overwrite this image variable with the converted image. So cv2.cvt color, and the source is our image. So this is the variable, and then cv2.color from BGR to RGB, right? So this is what we want to use. Now in the next line, what we want to do is we want to load our image using plt.imshow method, and at last we are going to just say plt.show. So this is how we are going to just load our image. So I'm going to right click on this file and then run this script, and you can see this road.jpg image is loaded. Now on this plot you also see these values, and one thing to observe here is horizontally these values goes from 0 to 1200 something, and vertically normally in the graphs you will see that values increases from the bottom to top, but in matplotlib this value goes from top to bottom, right? So 0 is at the top, and then the maximum value will be at the bottom. So this is one thing to note, because we are going to define our region of interest, and that will be based upon these values. Now in the next step we want to define our region of interest. So once again let me just run this code once again, and one thing to notice here is this lane in which our vehicle is traveling is parallel. So there are two parallel lines, and eventually they are going to merge here, right? So all the lanes on which the vehicle travels have the same pattern. So this lane and this lane are parallel to each other, and they are going to merge at some point. So it's not merging, but it seems to be merging at some point. So we can define our region of interest from this point to this point, and from this point to this point. So this region of interest will be the triangle. So this region of interest we are going to define for our vehicle will mask any other obstruction. For example, this is also one lane line. For us it's not important because this is the other side of the lane. So here the vehicle will come in the opposite direction. So this is our region of interest. So it will mask out this lane line or any other lines or distortions which we have in this picture. We are going to just mask them, and we are going to just concentrate on this triangle. So let's do this first. So first of all we are going to find out the shape of the image. So I'm going to just print, and then we are going to just say image dot shape, and also we are going to just define the height and width of the image. So I'm going to just say okay. So let's print this value and let's see what happens. So what's at 0 and what's at 1? So you can see it prints 704 as our height and 1279 as the width. So this is what I am just taking from this image shape method. So it's going to return this kind of tuple. So at 0th index there will be height, and at the first index there will be the width. And as I said, it starts from 0 to 704 from top to bottom, and horizontally it goes from 0 to 1279 from the left hand side to the right hand side, right? So once we have the width and height, we can define our region of interest. So we are going to define a variable called region of interest vertices, and here we are going to provide some values. So we are going to provide 3 points, which will be the 3 points of our region of interest. So as I said, that our region of interest we want is this point, which is the left bottom corner, this point, which is the right bottom corner, and somewhere in the middle of this image, so here. So in the image, because the vertical height starts from 0, so I'm going to just say 0 comma height, and the second point will be the half of the width and half of the height, which will be the center of the image. So I'm going to just say width divided by 2 comma height divided by 2, and this will be inside these parentheses, and the third point will be the next corner. So this will be width and then the height. So let's try to see these points in our matplotlib window. So the first point here is 0 comma 704, which is this point. The second point is somewhere here, which is the half of the height and half of the width, and the third point will be here, which is width comma height, which is 700 comma 1279, which is this one, right? So this will be our region of interest. Now we are going to define one function to mask every other thing other than our region of interest. So I will just define this function def region of interest, and this is going to take 2 parameters. First will be the image and second will be the vertices. So vertices, and inside this function, let me just minimize this terminal also so you can see the function. So inside this function, in the first step, we are going to define a blank matrix that matches the image height and the width. So this will be the easy step. We are going to define a variable called mask, and we are going to use np.zeros_like method, which is going to take 1 parameter, which will be our image matrix. Now in the next step, we are going to just retrieve the number of color channels from the image. This will be the easy step also. So channel count, and then we are going to just say image dot shape, and at the second index we are going to find out the channel, because we have seen that image dot shape is going to give you 3 values: height, width, and the channel count. So this channel count is coming from this index. Now in the next step, what we are going to do is we are going to create a match color with the same color channel counts. So I'm going to just say match underscore mask underscore color. This will be our variable name, and then we are going to just take 255 comma and then multiply it by the channel count. So let's multiply it by the channel count. So this is going to create a match color with the same color channel counts. Now in the next step, we are going to fill inside the polygon using the fill poly method, because we have our region of interest and we want to mask every other thing other than our region of interest. So we are going to just say cv2 dot fill poly, which is going to take few arguments. First will be our mask, Second will be the vertices, which we are providing using the second argument, and the third argument will be our match mask color variable. So we are going to pass this variable as the third argument, and in the next step we are going to just return the image only where the mask pixel matches. So I'm going to just say masked underscore image is equal to cv2 dot bitwise AND. So we are going to just apply bitwise AND using this bitwise AND method, and the first argument here will be the image, and the second argument is the mask, which we got using this zeros like method, right? And in the last step we are going to just return this. So I'm going to just write return this masked image, and that's it. So we are going to just apply our region of interest on the image using this method, and then we are going to just get our image which contains region of interest, and any other thing will be masked. So now it's time to use this method. So we are going to just use this method using this variable. I'm going to just define a variable called let's say cropped image or masked image, whatever you want to write here. So let's say cropped underscore image, and then we are going to just use this function, which is a region of interest function, which takes this argument. So because we have already read our image in the image variable, we are going to pass this as the first argument, and the vertices is simply our region of interest variable. So this region of interest variable we are going to pass using numpy dot array method. And let's split this line so we will be able to see what I'm doing inside this np.array method. So first of all, the first argument will be our region of interest variable, which is this one, region of interest vertices. So in the square bracket we are going to just pass region of interest vertices, and the second argument here will be np.int32. So np.int32, and now we are going to just show this image using our matplotlib window. So let's run this code and let's see what happens when it runs. And there is a problem here, so let's see what the problem is. So you can see this problem is coming from this line, and most probably this region of interest has some problem. So you can see we have passed this first element as the tuple, second element as the tuple, and the third element also we need to pass as a tuple, and that's why it's giving us the problem. So I have just fixed it, and let's see what happens when we run this code again. And you can see our image is now masked with our region of interest. So we have defined our region of interest from this point to this point to this point. So now we have only this region of interest, so we will be able to easily find out this lane line and this lane line inside our region of interest, and any other distraction will be masked now, right? So this is the first step which we have achieved, which is masking our image and just applying our region of interest on the image. In the next step we are going to see how we can apply the edge detection and find out the lane lines on the image. In the last video we have started our simple project of detecting lane lines on the road using OpenCV, and we came to the point where we were able to define our region of interest, and our result was looking like this. So let me run this project. So we have defined this region of interest, and now the only thing which remains here is to detect these lane lines. So we will once again go to the next step, and the next step will be to find out the edges, and then we are going to apply half line transform to draw the lines. So first thing first, what I'm going to do is I'm going to just move this region of interest function which we have created in the last video on the top of this script, so we can see this other code clearly, this code which we have written. So we have this region of interest function which we have created, then we have just created this region of interest variable, and then we just used our region of interest function using this region of interest vertices variable. So the next step, as I said, is to find out the edges, and for that we need to first convert our image into a grayscale image. So I'm going to just say a gray image, and then we all know how to find out the gray scale image out of an image. So we just need to write CVT color, and the source is our cropped image. So we are going to pass our cropped image, and then we are going to just convert it into a grayscale image using cv2 dot color underscore RGB to gray. So let's do this. So once we got our grayscale image, we can apply canny edge detection on this image. So I'm going to just write canny image, and then I'm going to just say cv2 dot canny, which is the function which we want to use, which takes few parameter. First parameter will be our grayscale image. The second parameter will be the first threshold and the second threshold. So generally we are going to take here 100 as the first threshold and 200 as the second threshold. Now in the next step, we are going to just display this image on our matplotlib window, and let's see what happens once we apply this canny edge detection method on the image. So now you can see this result which detects all the edges, and here you can see the lane line edges are detected, but there is one more thing here, which is the edges of our region of interest are also detected. So how to solve this, how to remove these edges, because these edges doesn't interest us. The interesting edges here in this image for us are these edges which are of the lanes, road lanes, right? So to solve this problem, we can apply this canny edge detection before we find out the region of interest. So I'm going to just copy this code and paste it just before we apply this region of interest method which we have created in the last video. So now in our canny edge detection, we will pass the grayscale image, but here instead of this cropped image which we were getting in the last step from this variable, we directly are going to pass our image which we have read using the imRead method, right? So let me just remove all these line breaks so you will be able to see the code at once. So here you can see I have directly passed now this image variable to the CVT color method. So we get the grayscale image of the original image, and then we apply the canny edge detection on the original image, and then we are applying the region of interest method which we have created in the last video. Now because we are applying this region of interest method on the grayscale image or the edge detected image, therefore we don't need this channel here. So we can comment out this code which was counting out the number of channels, and for the grayscale image and the canny edge detected image, we just take this match mask color as 255 because it's only one color, right? We don't need any color channels here because we are just passing the grayscale image which has only one color. So that's why we don't need any channel, because there will be only one channel, and that's why I have commented this code, and the value of the match mask color will be 255 now. Once you do that, let's try to run this code and let's see what happens. Once again, we need to load the cropped image, not the canny image. So just replace this variable here in the IAmShow method, and let's run this code once again. So you can see now there is some mistake here, because we were expecting the edge detected image and we are getting this image. So let's see what's the problem is. So the problem I see here is because we have applied this region of interest on the original image, which we don't want now. We want to apply this region of interest on the canny edge detected image. So we have to pass as the first variable of the region of interest method this canny edge detected image, not the original image, right? So once again, for you can see this code, region of interest method, and all this code at one glance. Let's run the code and let's see what happens. So now we get the better result. So we have these edges which are detected by the canny edge detection for only the lane lines inside our region of interest, and now it will be easier to draw the lines on these edges which we have detected. So the next step will be to draw the lines on these edges using the half line transform. So we have in the previous videos have already seen how to use the half line transform, so I'm not going to go into the details. So let's just directly jump into using that half line transform. So what we are going to do is, in the next line, after we have got our cropped image, we are going to just define a variable called lines, and we are going to use this half line transform, probabilistic half line transform method. So here cv2 dot half line transform, and this will be this method which takes few arguments. First argument will be the image, so I'm going to pass this cropped image here. The second argument here will be the value of row, so let's provide this row variable value, which will be 6 in our case. Then in the next parameter we have to pass the value of theta, and theta will be equal to np dot pi, which is the method inside the numpy library. So np dot pi divided by 60. So I'm going to pass here divided by 60. Then the next parameter here will be the threshold. So the threshold value we are going to provide here will be 160. The next parameter here will be lines, which is equal to none by default. So I'm going to provide this variable lines is equal to, and then we are going to pass the empty numpy array. So I'm going to just say numpy np dot array, and then we are going to just pass the blank square bracket here. The next two parameters will be the min line length. So let's provide this min line length, and let's say we want 40 as the minimum line length, and the max line gap. So let's provide that also, max line gap, and this will be let's say initial value for that will be 25. So now after applying this half line transform, you know that it's going to return the line vector of all the lines which are detected inside our image, which we have provided as the source here. So if you don't know what are these parameters which I'm using here, you can see my last videos about probabilistic half line transform, and you will be able to know what they actually mean. Now once we got our line vectors, then we can draw the lines easily, and for that we are going to define our next function, which is to draw the lines. So I'm going to just define this function with the name draw the lines, for example, and it's going to take few parameters. So let's pass these parameters. First parameter will be the image, or the original image. The second parameter will be the line vectors which we have found out, and that's it. So there are these two parameters we are going to pass here. Now inside this function, what we are going to do is we are going to first of all copy our image. So I'm going to just say img is equal to np dot copy, and then we are going to just make a copy of the image variable which we are providing, and then, or you can write here copy image whatever. I'm just reassigning this copied image to the same variable, but you can define a new variable here for the copied image also. Now in the next line we are going to create a blank image that matches the original image size, so the dimension should be equal. So for this we can just say line image, and then we are going to just say np dot zeros. Inside these parentheses we are going to provide the shape of our image, right? So you can provide the shape of our image using the image variable. So first of all it's going to take the height, and then the width, and then the number of channels. So because we know that this is a colored image which we are working with, so we are going to just say img dot shape, and we all know that the 0th index parameter here will be the height. The second parameter img dot shape, the value at the first index will be the width, and the number of channels for the colored image are always 3, so we are going to provide the third parameter as 3 here. So this is in the form of tuple I'm providing, and the next parameter here will be the data type or d type. So let's provide that. D type is equal to numpy dot uint 8. okay, so uint 8, not unint 8, uint 8. so this will be the second parameter. So once we have this image which is exactly same as the size of our original image, we are going to loop around these line vectors, and then we are going to draw the lines, right? So let's loop around these line vectors and draw all these lines which were found. So for that we are going to use the for loop, and then we are going to say line in lines, and this lines variable is coming from this lines variable. So we are going to use this draw lines function, and we are going to pass this lines vector as the second parameter here. So this is how this line variable is coming here. So now inside this for loop we are going to just define one more for loop, because this line is going to give us 4 parameters, which is the coordinates of the first point in the line and the coordinates of the second point in the line. So we are going to just once again say for x1, which is the first coordinate of the first point, and the y1, and then similarly x2 and the y2. So this will be the line coordinate in the line which we got from the line vector. And then inside this for loop we are going to draw a line, and drawing line is really easy by using cv2.line method, which takes a few parameters, as you already know, the image, and then the second parameter is the coordinate of the first point, which we already have using this iteration, which is x1 comma y1, and third parameter here will be the coordinates of the second point, x2 comma y2, and then you can provide the color and thickness. So let's provide this color. So the color here I'm going to take, let's say 0 comma 255 comma 0. You can take any color here. And the thickness, so the thickness here I'm going to take is let's provide this parameter, thickness is equal to 3. Okay, so this is the thickness of the line which we want to draw, and here I think this blank image should be given, because we want to draw the line on the blank image and then merge it with the original image. So here we have to provide this line image, or you can say this is the blank image, which is more appropriate in this case. So we want to draw the line on the blank image, which is of the same size of the original image. And now once we draw these lines on the blank image, we can merge this blank image and the original image, which will give us the line which are drawn on the original image. So outside this for loop, we are going to merge the image with the lines into the original image. So our original image is the image itself. So image variable is our original image, and then we are going to just say cv2 dot add weighted. This function also we have seen in the last videos, and this is the function which we use to merge two images with some weights. So the first parameter here will be image. Now the second parameter here will be the value of alpha, so which we are going to give here 8. This is like a weight to an image which we want to provide. And then the third parameter here will be the second image. So we want to merge the blank image with the original image. The fourth parameter is the value of beta. So this value we are going to take as 1, and the last value will be of gamma. So gamma we are going to take as 0.0 here. Okay, so this add weighted also we have seen in the last video how to use it, so I'm not going into the details. And at last, once we have the lines on the image, then we are going to simply return it. So let's return this image img. So once we have this function, we are going to call this function after applying the half line transform method, which is the probabilistic half line transform. So here in the next line, we are going to just define a variable called image with lines, let's say, is equal to our method, which is draw the lines method. The first argument is the original image, so we are going to pass the original image. The second argument is the line vector which we got from this method, right? So the original image and the line vector variable which we got here. At last, we are going to just see what is the result which we got after applying this draw the lines method on the original image. So let's run this code and let's see what happens. So now you can see, let me just maximize it. You can see this line is drawn on our image. So this is the first line and this is the second line. So we got the result which we wanted. If you want to change the thickness or the color of this line on the image, you can just change it using this draw lines method. So this is the line and thickness parameter. So for example, I want to change this to 255 here, some different color, and the thickness, let's say 4, and I'm going to run this code, and now you can see this yellow color here, right? So you can change the thickness and the color using this method. So let's say for now we want the red color, so we are going to go with this red color on the lane lines. So this is what we wanted to achieve. We wanted to draw the lane lines on these lanes, and we have achieved this. In the next video, we are going to see how we can apply the same concept on a live video or on a video of this road, for example. So for example, this car is running on the road and we want to continuously draw these lines on the lane lines. How we can achieve this using OpenCV, we are going to see in the next video. In the last two videos, we have seen how we can detect the lane lines on the road using OpenCV. Now, till now we have only worked with this image, and in this video we are going to try to apply what we have written not on an image but with the video frames. But you have already learned in the previous videos that a video frame is like an image. So a video contains many number of frames. So if we apply the same technique on each frame, we will be able to detect these lane lines on the video frames also. So let's apply that concept on our script, what we have till now. So right now I have added this test.mp4 video inside my project. So let me show you how it looks like. So our video looks like this. So we are going to apply all these concepts which we have applied on an image on this video. So let's get started. So I hope you have this code which we have written in the last two videos. The only thing we need to do here is we need to read the video instead of an image and then apply those concepts on the frame instead of an image. So we till now have two functions, region of interest, draw the line, and we have this code. So this all code we are going to enclose inside the function so that it will be easier to apply all this code on the video frames. Now, as you already know that this will not be used because we are reading the videos, so we don't need to read the image obviously. So we are going to comment these two lines out. So we don't need to convert BGR to RGB because we are going to use the native CV2 library, not the matplotlib library for which we have converted this BGR to RGB image. So now we are going to define a function. So let's define this function, and I'm going to name this function as process, and it's going to take an argument which will be the image argument. And all this code which is under this, which we have written in the last video, we are going to enclose this code inside this process function. We don't need these two lines because we are not going to use matplotlib for processing this video. So I'm going to remove these two lines, and I'm going to just give a space here for this code so it can be enclosed inside this function. Now at last, or at the end of this function, we are going to just return this image with lines. So we are going to return this image with lines using this process function. That means on every frame we are going to draw the lines and return it using this process function. Next, we are going to read the video using the video capture functions. So I'm going to declare a variable cap is equal to cv2 dot video capture, and then we are going to just pass one argument which will be our video file, which is test.mp4 in our case. So test.mp4, and then once we have this video, we are going to check if the video frame is available using the while loop. So let's use this while loop, and we are going to check if cap.isOpen is valid or not. So is opened, and this function is going to return the boolean value. So if this video frame is still available, is going to return true, and whatever we write inside the while loop is going to be executed. Now in the next line, we are going to just read every frame. So we all know from our previous videos that this cap.read returns two result or two variables. One is ret and the other is the frame, and we are going to just say cap.read, and then we are going to apply our process function on this frame. So we are going to once again take this frame variable, and we are going to overwrite this frame with the lines on the frames. So this we are going to get from our process function. So let's call the process function and pass the frame variable inside it. Okay, so this frame is going to go to the process function. It's going to process everything, and then the final result which we get is going to be saved once again into the frame variable with the actual lines on the frame. In the next line, we are going to just show our result using cv2.imshow method, and we are going to just pass the frame variable here. In the next line, we are going to just write the code for the quitting from this loop. So we are going to just say if cv2.waitKey is going to be 1, and then we are going to apply the AND operator and then write 0xff for the cross platform functionality, and then we are going to just say is equal to ORD. So whenever somebody presses the Q key, then we are going to exit from this loop, and then in the next line we are going to just say break, so break out of the loop. In the last two line outside this loop, we are going to just call the release function on the cap variable, and we are going to destroy all the windows in the cv2. So we are going to just say destroy all windows. That's it. Hopefully this is going to work. So let's just run this script once again and let's see what happens. And here we got the error, and it's coming from this line, which is cv2.imshow. We forgot to give the first argument here, which will be the name of this window. We're going to just say frame here, and let's run this script once again and let's see what happens. And you can see on this video, on this lane line, our lines are drawn, right? So this is the result which we were expecting. We can improve this result by adjusting few variables. So we are going to first of all press Q to quit, and let's change some of these values here in the half line transform. So we are going to just say that the max line gap is going to be 100. We are going to reduce the threshold value to 50 and row value to 2, okay, inside this half lines p method. And let's run this code. So let's see what result we get. This is also okay. Let's improve it a little bit more. In the Kenny edge detection, we can reduce this threshold value here to 120, the second threshold value, and let's run this code once again. And now we get the better result. So the problem might be the edge detection. So we have reduced our second threshold, and now we get the better result. You can see on this middle lane, the lines are drawn clearly. So this is how you can write a simple script to detect lane lines on the road. I hope you have enjoyed this video, and I will see you in the next video. We have already seen how to use half line transform to detect lines in OpenCV. In this video, we are going to see how we can use half circle transform to detect circles in an image. Now, as you can see here, I have this small example which loads an image and shows it into the IMShow window. So let me run this code and let me show you how this image looks like. So you can see there are so many Smarties here inside this image, and all the Smarties are of circle form, right? They are not the perfect circles, but they are in the form of circles, and we want to detect all these circles forms inside the image. We can use half circle transform for that. So let's see how we can use this half circle transform to detect the circles in the image. So a circle is represented mathematically by this equation which you see on your screen. So here x center and the y center are the coordinates of the center, and r here is the radius of the circle. So if you know these three parameters, then you can draw a circle. So the coordinates of the circle and the radius of the circle we need to detect. So now let's see how half circle method is applied using OpenCV. So you might observe here that I have created a copy of this original image which I have read using this IMRead method. In the next step, I'm going to just convert this image into a grayscale image. So I'm going to just write gray is equal to CV dot CVT color, which is going to take two parameters. First is the source and second is the method. So we are going to convert the color BGR to gray. Now in the next step, because our half circle method works better with the blurred images, so we are going to create this blurred image using median blur. So I'm going to just say gray. So we are going to override this gray variable with cv2 dot median blur, which is going to take a few arguments. First is the image itself, so we are going to pass gray here, and the second is the k size or the kernel size. So we are going to initially provide the kernel size of 5 here. Now we are going to apply our half circles method. So I'm going to declare this circles variable, and then I'm going to just call this method, which is called cv dot half circles method. So this is the method, and you can see it takes few parameters. So we are going to give these parameters one by one. First is the obvious one, which is the image. So we are going to provide the gray scale image here, which is already blurred. So the second parameter here is the method which we want to use. Currently the only implemented method is half gradient method. So the choice is very simple here. We are going to just provide this cv dot half gradient method. The third parameter here will be dp. dp is the inverse ratio of accumulator resolution to the image resolution. So for example, when dp is equal to 1, the accumulator has the same resolution as the input image, and if the dp is equal to 2, then accumulator has the half as big as width and the height. So we are going to take this dp value as 1. The next parameter here will be min dist. It is the minimum distance between the center of the detected circles. Okay, so here we are going to give initially the value of 20, and later we will adjust this value if the circles are very near to each other. The next parameter which we are going to give here is the value of parameter 1 and parameter 2, or param 1 or param 2. The param 1 is the first method specific parameter. In case of half gradient, it is higher threshold of the 2 passed to the Kenny edge detector. Param 2 is the second method specific to the method which we have provided here, which is the half gradient method. It is the accumulator threshold for the circle centers at the detection stage. So we are going to provide the value of the param 1 and param 2 here. So let's start with the param 1 value, and we are going to provide param 1 value is equal to 50 and param 2 value is equal to let's say 30. So those param 1 and param 2 parameters are specific to this method which we are using. The next parameter which we are going to pass here is the min radius, and the min radius is the minimum circle radius, and we are going to just start with the 0. So we are going to say that anything which is greater than 0, we are going to just draw it, and then we are going to provide the max radius. If this max radius is greater than or equal to 0, it uses the maximum image dimension. If it's only greater than 0, it returns center without finding the radius. So this also we are going to start with 0. Let me just break this function so you can see all the parameters here. So this half circle method is going to give us the circle vector which we can iterate upon. But first of all, we need to convert those circle parameters which we got using this circles variable, that is x and y coordinate and the radius, into an integer. So to do that, we are going to just declare a parameter called detected circles, and then we are going to use numpy to convert them into an integer. So I'm going to just say np.uint16, and then in the parenthesis I'm going to just use np.around, and we are going to pass our circles parameter which we got using the half circles method. Now in the next step, we are going to iterate over those detected circles. So we are going to just say for, and because this circle vector is going to give us x, y and the radius, we can directly just extract those values. So we are going to just say x comma y comma r, and then in our detected circles, and those circles will be at this index. So 0 comma colon, and then inside this for loop we are going to first of all draw the circle, and also we are going to draw the center. So to draw the circle, we already know that we have this circle method available which takes few parameter. First is the image. So we are going to pass the copy of this image here. So let's pass this copy, which is output. The second argument here will be the center, which are the coordinate of the center, which we already got in the form of x comma y. So we will give them in the form of tuple. The third argument is the radius. So radius is extracted in the r parameter here. So we are going to pass the radius here, and then the next parameter will be the color. So let's start with let's say green color, and then the thickness. So we are going to give the thickness of, let's say, 3 here. Similarly, when we use the same circle method and we want to draw the center, then we know that this is the center. So these are the coordinates of the center, and if the radius is very small, let's say 2, then it's going to just draw a small point, right? So that's why I have given very small value, for example 2 here. So it's going to just draw a very small circle which will look like a dot on the circle. That's why this value is very small, and we are going to just say that this will be also 3, and let's change the color of this dot. Let's say this will be this color. Okay, so we are just drawing those circle on the copy of the image, which is called the output. So let's run this code and let's see what happens when we run this code. And you can see this dot is first of all drawn on each circle which is detected, which is in the form of yellow, and also in the form of green. All the circles are drawn. So you can see this circle is drawn. So every circular shape is enclosed by the detected circle. We also strangely detected this circle somehow, because OpenCV think that this is also a circle. I have one more image which is shapes.jpg. So we are going to just see that also. So I'm going to just say shapes.jpg. Let me show you this image first of all. So it looks like this. So it has only one circle and some other shapes, right? So we are going to just run this code once again, and you can see it just detect this circle and it just draws a small dot on the center, and all the other shapes are undetected. So this is how you can detect the circles inside an image using half circle transform. In this video, we are going to discuss about the basics of face detection using HAR feature-based cascade classifiers. So object detection using HAR feature-based cascade classifiers is an effective object detection method proposed by Paul Viola and Michael Jones in their paper. Now, HAR feature-based cascade classifier is a machine learning based approach where a cascade function is trained for a lot of positive and negative images. Now, what are these positive and negative images? So first, a classifier is trained with few hundred sample views of particular object, that is a face or a car or any other object. That is called a positive example. So whatever you want to detect, if you train your classifier with those kind of values, so for example, if you want to detect face, then you need to train your classifier with the number of images which contain faces. So these are called the positive images which contains the object which you want to detect. Similarly, we want the classifier to train with the negative images. That means the images which doesn't contain the object which you want to detect. So in our case, for example, we want to detect the face, then the image which doesn't contain the face, then it is called the negative image, and if the image contains face or number of faces, then it's called the positive image. And after a classifier is trained, it can be applied to a region of interest in an input image, and the classifier outputs a 1 if the region is likely to show the object, or 0 otherwise. So let's see how we can use HAR cascade detection in OpenCV. So OpenCV comes with a trainer as well as a detector. So if you want to train your classifier for any object, for example a watch or a car or a train or anything, then you can use this classifier. Also on OpenCV's GitHub page, you can find some trained classifier XML files. So let me show you these classifiers on the OpenCV's GitHub page. So here is the OpenCV repository, and inside this repository you can see this data folder and then go to HAR cascades. I will just share the link with you in the description so you can directly navigate to this website and this location, and you can see plenty of trained classifiers are available inside this repository. So for our example, we want to detect the face, so we are going to use this trained classifier which is called HAR cascade underscore frontal face underscore default.xml file. So you just need to open this file and then download it. You can just click on the raw icon here, this button, and once this raw file is open, you can just right click and save it on your computer. So you can just say save page as, and then you can just save this inside your OpenCV project. So I have already saved this file inside my OpenCV project. You can see this file here, which is a XML file which I have downloaded using this repository. So as you can see here, I have this code which is the minimal code to load an image and show it using OpenCV window. Now in the next step, what I'm going to do is, before this reading, we are going to just define our classifiers. So because it's a face classifier, I'm going to name my variable as face cascade, and then in OpenCV there is a method called, so I'm going to just call this method, and there is a method called cascade classifier. So this is this method called cascade classifier, where you can provide your classifier name, which is the XML file. So just provide your trained classifier file name. In our case, it's har cascade underscore frontal face underscore default dot XML. So once we have our classifier, we read the image, and then because this classifier will work with the grayscale images, we are going to convert our image into a grayscale image, and it will be really easy to convert our image to a grayscale image. Now once we have our grayscale image, the next step is to detect the faces inside this image. So for that, we are going to declare this variable, let's say faces, and then we are going to use this result which we got using this cascade classifier, and then we can call a method called detect multi scale. So we are going to just call this method, which takes few arguments. First is the image, so we are going to provide our grayscale image here, and the second argument we are going to use here will be the scale factor. So the scale factor parameter specifies how much the image size is reduced at each image scale. So to start with, we are going to provide 1.1 value here, and then the next parameter which we are going to provide here will be the min neighbors parameter. So min neighbors parameter is going to specify how many neighbors each candidate rectangle should have to retain it. So we are going to provide this value 4 here to start with, and if it doesn't give us the proper result, we are going to change it. And the last step here will be to iterate over all the faces which we have detected, and then draw a rectangle on them. So this face variable will be the vector of rectangle, where each rectangle contains the detected object. In our case, this will be the detected face. So the rectangle may be partially outside the original image if it's on the corner. So if the object or the face is on the corner, then this rectangle may be little bit outside the original image. So we are going to iterate over this faces object, and here we are going to get the parameter x comma y comma w comma h, which means the values of x and y and the width and height of the rectangle of the object. In our case, this is the faces, right? So we got all the 4 parameters for drawing the rectangle, and then we can just call cv2.rectangle method to draw the rectangles. The first parameter here will be the image. The second parameter will be the point 1, which will be x comma y, which we got using this faces vector, and then we need to give the second point, which will be x plus w comma y plus height. Okay, and then the next 2 parameters are the color and the thickness. So we are going to give the color 255 comma 0 here, and the thickness to start with we are going to give 3 here. That's it. So it's this simple to detect faces inside the images using har cascade classifiers. So now I'm going to run this code and let's see what happens. So you can see this is the face. So this is how you can detect the face or a multiple number of faces inside an image. Let's try to detect the face inside a video. So I'm going to just close this window, and now we are going to try to detect the face inside a video. So this will be nothing different than this approach. We just need to apply this approach on each and every single frame. So instead of this code, we are going to use the video capture method to capture the video. So you can see I have this test.mp4 video here. So we are going to define a cap variable is equal to cv2 dot video capture, and then in the parenthesis we are going to provide the test.mp4 file here, or if you have the camera you can provide 0 here as the parameter. And then all this code we are going to just enclose inside a while loop. So we are going to just say that while cap dot is opened. So if cap dot is opened is going to give us a true value, then we are going to read the frame. So underscore, let's say the parameter name will be img in this case also. Normally we take the variable name frame here because we are reading each and every frame. And then I'm going to just say cap dot read. Okay, so cap dot read, this means we are reading every frame. And let's enclose this code also inside this while loop. So I'm going to just provide a little space here. So basically we are getting every frame and then applying the same procedure on each and every frame. And at last, outside our while loop, we are going to release our cap. So we are going to just say cap dot release. And here, instead of using this cv2.wait key, we are going to provide a condition if cv2.wait key, and in the parenthesis we are going to provide 1 and 0xff is equal to ord, and we are going to listen for the key q. So if somebody presses the key q, then we are going to break out of this while loop. So let's run this script and let's see what happens when we run the same script on a video. So this is the video, and this is in this video. So you can see in this video the face is detected in real time in the real live video. So this is how you can use HAR based cascade classifiers to detect faces or any other object inside an image. In the last video, we have seen the basics of face detection using HAR feature based cascade classifiers. In this video, we are going to extend our code to detect eyes using the same HAR cascade classifier. So for that, first of all, you need to download the pre-trained classifier for the eyes from the same source which I have shown you last time also, which is the GitHub repository of OpenCV. Again, I'm going to give you this link in the description so you can directly come to this page. And this time we are going to download this XML file with the name har cascade eye underscore tree underscore eyeglass.xml file. So this is the pre-trained classifier for detecting eyes. So you can just click on raw and then save it as this same file name in your project. Okay, so I have already downloaded this XML file. You can see here har cascade eye underscore tree underscore eyeglass.xml file, and now we are ready to write our code. So this is the code which we have written last time. So if you don't know how this code works, you can see the last video. I'm going to just extend this code to detect eyes. So first thing first, we need to create the cascade classifier for the eyes. So instead of face cascade, we are going to name it as eye cascade, and this file name will be the file which we have downloaded, which is eye underscore tree underscore eyeglass.xml file. So once we have our classifier, then in the last video we have already seen how to detect faces. So our region of interest will be the face this time, because the eyes will not be present outside the face, right? So eyes will always be present inside the face. So our region of interest will be the face, and face we have already detected last time. So this face will be now our region of interest. So go inside this for loop where we are iterating over this face variable, and then we are going to create our ROI. So I'm going to create this variable which is called ROI underscore gray, and this will be the original grayscale image which we have created here, but we just want the face out of this image. So we can just index this face using y colon y plus h comma x colon x plus w, which is the width. So this line is going to give us the grayscale region of interest, but we also want the colored image also. So we are going to just say ROI color, which will be the colored ROI, and here instead of gray we are going to take the direct image, which will be before we have converted this BGR image to the grayscale image. So we have the colored ROI and the grayscale ROI. Once we have this, we will follow the same concept which we have applied for detecting the faces. So we are going to use this detect multiscale method. So I'm going to just write eyes is equal to, because we already have our eye cascade which is a classifier, so we are going to use this variable and then use this method called detect multiscale, and then we are going to simply pass our ROI gray which we got using the faces. Now we are going to iterate over those eyes. So inside this for loop we are going to create one more for loop to iterate over all the eyes which are found on the face. So for, and then this will be ex comma ey comma ew comma eh for xy coordinate and the width and height. Now we will just say in eyes, and then we are going to just draw this rectangle, which is also very simple, cv2 dot rectangle, and then we are going to pass our image first of all, which will be our colored ROI image, which is this one. So here we will pass this ROI color, and then the first point in the rectangle, which will be ex and ey. So I'm going to just say ex comma ey, and the second point will be ex plus ew, which is x plus width. So we are going to just write this ex plus ew comma ey plus eh, which is the y coordinate and the height. The next parameter will be the color. So let's provide the color. Let's say this will be 0 comma 255 comma 0, and then the next parameter will be the width. So let's say the width we want here is 5. So that's it. So hopefully this code is going to work out of the box. We don't need to do anything else. We just need to define our classifier, and then we just need to use this detect multiscale method to detect the eyes, and then we just need to draw the rectangle on all the eyes which are detected. So let's run this code and let's see what happens. So we are going to see, you can see eyes are detected, but there is some problem because something is wrong. So I'm going to just quit this script and see what's going wrong here. So you can see this should be ex comma ey, and then our problem will be solved hopefully. So I'm going to run this code once again, and you can see the eyes are properly detected. So this is how you can detect eyes in the face using OpenCV and HAR cascade classifiers. In this video, we are going to try to understand how we can find out the corners inside an image using a method called Harris corner detection. Now, first of all, what are corners? So corners are the region in the image with large variation in intensity in all the direction. Now this Harris corner detector was first introduced by Chris Harris and Mike Stephens in their paper in 1988. Now, detecting corners using Harris corner detector contains three main steps. So the first step is to determine which windows produces very large variation in intensity when we move in the x direction and the y direction. Now, what are windows here? So windows in this case means that, let's say we want to just find out this corner here. So windows will be your small box here, and then you check for the intensity when you move in the vertical direction and also in the horizontal direction. So you check for the change or large variation in the intensity when you move in the x direction and when you move in the y direction. In the second step, with each such window which we found, a score R is computed. So this R value which is computed is going to give us the estimate or give us an idea about where this corner is located depending upon the value of R. And in the third step, after applying a threshold to this score, the important corners are selected and marked. So let me explain you all these steps one by one. What do I mean by detecting the windows and calculating the value of R's? Let's see step by step. So as I said, in the first step, we determine which windows produces very large variation in the intensity in the x direction and in the y direction. So let's say a window or a center is located at the position x, y. And let's say the intensity of the pixel at this location is I, x, y. So if this window is slightly shifted to a new location, and let's say this displacement is u, v, then the intensity of the pixel at this location will be x plus u and y plus v, because our displacement is u, v, so we are just adding it to the x value and the y value, and hence the difference between the shifted intensity and the original intensity will be the difference in the intensities of the windows shift. So for a corner, this difference will be very large, and that's how we detect the corners using this Harris corner detection method. Now, as you can see here, this value will be given in the E, u, v format. So we have to maximize this function for the corner detection, and this we can achieve by applying a Taylor expansion to this equation which is given here, and by using some mathematical steps. So I'm not going to go deep into the mathematical steps, but after applying the Taylor expansion, you will get this kind of approximate value where m is equal to this value. And here in this equation, ix and iy are the image derivatives in the x and y direction respectively. So this can be easily found out using the cv.sobel method in OpenCV. Now comes the second step, and in this step we find out or calculate the score for R. So this R is equal to this value, and the m we have already seen how we can get this m value in the first step, right? So in this equation, det m is equal to lambda 1 multiplied by lambda 2, and trace m is equal to lambda 1 plus lambda 2, where lambda 1 and lambda 2 are the eigenvalues of m. So again, if you want to go into the details, you can refer to some book or you can go to the Wikipedia page to learn more about this equation. So once we got the value of r, then based upon the value of r, we can make some decision, and this we can do in the third step. So if the value of r is very small, that means the value of lambda 1 and lambda 2 are also very small, and we can conclude that the region is a flat region and not the corner. If the value of r is less than 0, that means lambda 1 is very large in comparison to lambda 2 or vice versa, and that means it's an edge and not the corner. And if the value of r is large, which happens when lambda 1 and lambda 2 are large, and this means that this region is a corner. So if the value of r is very large, that means the region is a corner, and that's how Harris corner detector detects if it's a corner or a edge or a flat area. So this was the theory about Harris corner detector. Let's see how we can use this Harris corner detection concept inside OpenCV using our Python code. So I have this script already written here. So just import CV2 and Numpy, and then we are reading this image called crossboard_image.png using imread method. And after we read this image, I'm just showing the original image. So we have the original image and the output at the end to compare. Now in the next step, I'm converting this image into a grayscale image to get the better results. And because this cv2.cornerHarris method takes the grayscale image in the float 32 format, that's why we need to convert our image into float 32 format. So that's why we are using numpy.float32 to convert this image into floating point values, because our cornerHarris method, which we are going to use in the next step, is going to take this kind of value and not the value which comes directly from the conversion of this image to the grayscale image. So this step is necessary for the Harris corner method. And in the next step, we are just applying the cv2.cornerHarris method, which takes few arguments. First is our image in the floating point. So this we have passed. And the second parameter here is called the block size. So here I have given the value 2 here. So block size means the window in the first step. So we have seen we have to define the window, right? So for example, we define this block size 2. That means neighborhood size is equal to 2. That means for each pixel value, block size multiplied by block size, that means 2 by 2 neighborhood is considered. The next parameter here is called the K size, and it's the aperture parameter for the Sobel operation. And then we have the next parameter here, and this next parameter is called the K, which is the Harris detector free parameter in the equation. So after applying this Harris corner method to our image, we get this destination image, and to get the better result, we need to dilate this result. So we apply cv2.dilate method on our image which we get using the Harris corner. So this image are marked through the dilated corners. And then in the next step, we are reverting back to the original image with optimal threshold value, and we are just marking all our corners with this color. So basically we want to mark all the corners with the red color here. And in the next step, we are just showing our result in the I am show window, and at last we are destroying all the windows. So let's run this code and let's see what happens when we run this code, and we will see the results. So you can see this is the original image which have so many corners, and all the corners are detected and it's marked with this red color here. So this is how you can find out and mark all the corners using Harris corner detection in OpenCV. In the last video, we have seen how we can use Harris corner detector in order to find out the corners inside an image. In this video, I'm going to show you how you can use Shi-Tomasi corner detector method to detect the corners inside an image. So in late 1994, J. Shi and C. Tomasi made a small modification in the Harris corner detector method in their paper, which was called Good Features to Track. So this Shi-Tomasi method is similar to Harris corner detector, apart from the way the score of R is calculated, which we have seen in the last video. So this Shi-Tomasi method gives us better result in comparison to Harris corner detector, and also when you use this Shi-Tomasi method, we can find the top n corners, which means we can provide the number of corners we want, and this might be useful in cases where we don't want to detect all the corners inside an image. So let's see in the code how we can implement this Shi-Tomasi corner detector in OpenCV. So here I have already written all the code, so let me explain you all the lines of the code one by one. So as you can see here, I'm just importing the libraries in the first two lines, and in the next line I'm just reading the image using IamRead method, and then I'm converting this image into a grayscale image using this CVT color method. So I'm converting this image from BGR to grayscale image. Now, as I said, the paper which was published by Shi and Tomasi was named Good Features to Track. That's why in OpenCV, this method is also called Good Features to Track. So here in this line, we are just using this method cv.goodFeatures to track, which takes few arguments. So first argument here is our input image, which is a grayscale image, which we are providing as the first parameter. The second parameter is the maximum number of corners. So here we can limit the number of corners we want to detect. So for example, I have given 25 here. That means we just want to detect 25 corners, and if there are more than 25 corners which are present in the image, they will not be shown. So this value means maximum number of corners to return, and if there are more corners than the corners found, then the strongest corners will be returned, right? Now the third parameter here is called the quality level. So this is the parameter characterizing the minimal expected quality of the image corner. The next parameter here is the min distance, which is the minimum possible Euclidean distance between the returned corners. So I have taken 10 here as the minimum distance and 0.01 as the quality level. Now once all the corners are detected using this good features to track method, we convert those corners into the integer values, and here int 0 is a mere alias for int 64, and once all the corners are detected, we iterate over all the corners, and then we find out the value of x and y using this I, and then it's easier to just draw the circles over these values using the cv.circle method. So this cv.circle method takes few arguments. First is the input image. So the second parameter is the center. The third parameter is the radius of the circle which we want to provide. The fourth parameter is the color we want to provide, and the fifth parameter is the thickness, and if it's -1, that means we want to fill the color inside that circle. And at last, once all the circles are drawn on the corner which are detected, then we are just showing this using IamShow method. So let's see how this works in the case of Shitomasi method on an image. So I'm going to run this code so you can see all the corners inside this image are detected, and because we have just provided this number 25 here, so maximum number of corners which will be detected here will be 25, and rest of them will not be shown. So if we increase the value of the maximum number of corners, let's increase it to 100, let's say. So I'm going to just increase it to the value 100. You will see more number of circles are drawn on an image. Now let's compare the result of the Harris corner detector and Shitomasi corner detector. So on the left hand side you can see the original image, and this middle image shows the Harris corner detector method, and you can see all the corners are detected using Harris corner detector. And using the Shitomasi corner detector, it gives us better result, and we can control the number of corners we want to detect. And you can see all the important corners are detected using Shitomasi corner detector in a better way. So that's how Shitomasi corner detector works. In this video, we are going to see how to use background subtraction method in OpenCV. So first of all, what is background subtraction? So background subtraction is common and widely used technique for generating the foreground mask, which is also known as the binary image containing the pixels belonging to the moving object of a scene when these images are captured using a static camera. And as the name suggests, background subtraction calculates the foreground mask, performing the subtraction between the current frame and the background model containing the static part of the scene. So for example, the background subtraction method can be used in the case of visitor counter, where you have a static camera capturing the number of visitors entering or leaving the room, or you have a traffic camera which wants to count the various telematic data from the moving car or moving car data which is captured by that traffic camera. Now there are several algorithms which were introduced for the purpose of this background subtraction, and OpenCV has implemented few of them which we are going to see one by one. So as you can see here, I have this example which is a very simple example of just taking a video, and then we are extracting each and every frame of that video and showing it into a window. So using IamShow method, I'm just showing each and every frame of that video. So this you already know from the previous videos, how to capture the video frames from a video file or the live camera. So when I run this code, you will see that there are few persons which are moving here, and we want to detect all those moving persons which are moving in the image. So for that, we are going to use a few methods which are available in OpenCV. So let's first write some code, and I will explain you what this code is going to do. So I'm going to define a variable after this line of code, and I'm going to define a variable name fgbg for foreground background, and then I'm going to just call cv.bg segm. So bg segm, and then I'm going to call a method called create background subtraction mog method. So this create background subtraction mog method is a Gaussian mixture based background and foreground segmentation algorithm. So using this line, what we are doing is we are just creating a background object of the function using this method create background subtraction mog. Now this method has some optional parameters like history, number of Gaussian mixtures, and threshold, but all of them are set by default, so you don't need to set anything specifically unless you want to change some of the optional parameters. So I'm going to leave everything as default, and I'm not going to give any argument here for this method. And then after I captured each and every frame inside this while loop, what I'm going to do is I'm going to create a new variable called fgmask for foreground mask. So I'm going to just write fgmask is equal to, and for getting the foreground mask, we are going to just call a method called apply on this fgbg or the background subtractor image. So we are going to just take fgbg, and then we are going to call a method called apply here, and it takes one argument, which is the frame which we are capturing. Okay, so we have applied this method, and then we are just getting the foreground mask using the apply method on this background subtractor variable, and that's it. So this is your foreground mask. So when I just use one more I'm show window, and this is for the fg frame, let's say, so fg mask frame, let's say. Okay, so fg mask frame, and we are going to just pass this argument here. So let's see what result we get after we apply create background subtractor mog method. So you can see this normal image here, and also you will see these moving persons in the foreground mask, right? So you have subtracted the background from the foreground, and you can easily detect the moving persons here inside this image using this mask. You will also observe that there is a very little noise, not much, when you use this kind of subtraction using create background subtractor mog method. There is one more method which is called background subtractor mog2, which is also Gaussian mixture based background and foreground segmentation algorithm. So let's use that method also. So this method is directly available under cv2. So you just need to write cv.create background subtractor mog2. Okay, and everything will remain the same. So it's going to return you the background subtractor variable, which you can use with this apply method to get the foreground mask. Okay, so let's see how this method performs. So you can see the result, which is quite different from the first method which we have used. So in the previous case, we have to create the background subtractor object, and here in this method you have an option of detecting the shadows. So there is an optional parameter which you can give into this method, which is this create background subtractor mog2, which is called detect shadows. So by default, this detect shadows is true, that's why you see the shadows there. If you just write detect shadows is equal to false, then it's not going to detect the shadows. So I'm going to just run the code once again, and you can see now shadows are less visible, right? So let's run the default case once again. So let's say we just write true here, and you will see the shadows in the gray color, right? So these shadows in the gray color, and when we just make it false, so detect shadows false, you will not see that gray color. Okay, so shadows are displayed in the gray color. So if you don't see any gray color, then shadows are not detected. This is a noise which is detected but not the shadow. Okay, so this is the difference between the first background subtractor method and the background subtractor emoji2 method. There is one more method which is called the background subtractor GMG. So this algorithm which we are going to use, so let's use this method first of all, which is called background subtractor GMG, which is available under cv.bg segment as the first method. So just write bgsegm dot create background subtractor GMG method. So this create background subtractor GMG method algorithm combines statistical background image estimation and pre-pixel Bayesian segmentation. Let's see how this method performs when we just use this GMG method. And when you will see here, there is nothing on this foreground mask frame. So to get the better result, you need to apply morphological opening to the result to remove the noises. So we are going to do just that. So I'm going to just overwrite this FG mask frame using a method called cv.morphologyx. This also we have seen in the previous videos, right? So the first parameter here will be FG mask parameter. The second parameter here will be the op. So cv2 dot morph open, we are going to use the morph open method. And then the third parameter will be the kernel. So we need to define the kernel also. So for defining the kernel, let's define the kernel outside this while loop. So I'm going to just write kernel, which takes few arguments. First is the shape. So we are going to say we want the morph eclipse shape. So I'm going to just write morph eclipse, and then the kernel size will be, let's say, 3,3. Okay, so we are going to apply this kernel using this morphologyx method. And when we are going to run this code, you can see these kind of results, which are not as good as you have seen in the first method. Now let me show you the last background subtraction method, which is called the background subtractor KNN method. So this method is available under cv2 directly. So we are going to just comment this kernel code, because for this method we don't need to define any kernel. So we can just write cv dot create background subtractor, and then at last you just need to write KNN in capital. Okay, and it also takes few optional parameters like history and other parameters, but these are optional parameters. So for now we are not going to set any parameter. And let's see the result which we get using this KNN method. So I'm going to run this code, and you can see this KNN method result. It also shows the shadows in the form of gray pixels. So whatever gray pixels you see here in this image are the shadows. In this method also there is an optional parameter which is called detect shadows, which is set by default to true. So when you make it false, the shadows will not be detected. So you can see no gray pixels are visible now. When you make it true, then the gray pixels will be visible, and those gray pixels indicates the shadows, right? So these are the few methods which you can use for the background subtraction in OpenCV. In this video, we will talk about an object tracking method which is called mean shift. So first of all, what is object tracking? So in simple words, object tracking is the process of locating a moving object over time using a camera. And what is mean shift? The idea behind mean shift is really simple. Consider you have a set of points. It can be a pixel density like histogram back projection, and you are given a window which is a very small window, which can be a circle or rectangle or a square, and you have to move that window to an area of maximum pixel density or maximum number of points. So in the image you can see this illustration very easily. So essentially the working of mean shift algorithm can be summarized in following points. So in the first step, we pass the initial location of our target object and the histogram back projected image to a mean shift function. And then in the second step, as the object moves, the histogram back projected image also changes. And in the third step, the mean shift function moves the window to the new location with the maximum probability density. So we will see all these steps with the help of an example. So here I have the simple code where I'm loading a video which is called slow traffic small.mp4, and I'm just iterating over each and every frame of that video. So this code till now you already know how it works. So I'm going to just run this code, and let's say I just want to track this window of the white car. Okay, so let me just run this video once again. So I want to track this window of the white car, or window in general of each and every car, let's say. Okay, so how can I track this window using mean shift algorithm? Let's see. So as I said, the first step is the passing of the initial location of our target. So this can be, you can say, a disadvantage of mean shift, that you have to provide the initial location of your target. In our case, that target is the car window. So what I have done is I have just calculated the initial position of the white car window, and that we are going to see in the next step. So first of all, we are going to take the first frame of our video. So the first frame of our video can be retrieved by this code. So ret comma frame is equal to cap. We have this cap function, and we will read the first frame using the read method, and this is going to give you the first frame of the video. So this is our first frame. Now once we have our first frame, we are going to define the initial location of the car window. In our case, we want to track first of all the white car window, right? So I'm going to define 4 variables. First two are x comma y, and the next two are width and height. So, and because I have already calculated the initial position of the window, I'm going to hard code this position of the window. So 300, 200, comma 100, comma 50. Okay, so this is the hard coded value which I have already calculated, which is the initial position of the car window. Now we can say that this x, y, and width and height is our track window. So we are going to define a variable called track underscore window, let's say. and then we are going to just pass all these four variables: x comma y comma width comma height. Okay, so let's pass all these four variables, and in the next step we are going to define our region of interest. So let's define this region of interest with the variable called ROI, and we already have our first frame, so we are going to take our first frame and then we are going to pass that window. So y colon y plus height comma x colon x plus width. So this is our window or the position of the window. So as I said, in the first step we will pass the initial location of our target object and the histogram back projected image of the mean shift function. So histogram back projection, in simple words, creates an image of the same size but of a single channel as of our input image. In our case, this will be our frame, where each pixel corresponds to the probability of that pixel belonging to our object. That is, the output image will have our object of interest or region of interest in more white color compared to the remaining part of that image. So this is back projection. So for calculating the histogram back projection, there are some steps which are involved. So we are going to follow all these steps to calculate the histogram back projection. But first of all, let's just see the region of interest, because we already have our region of interest. So I'm going to just write cv dot I'm show and our region of interest. So let's say how our region of interest looks like. So I have this video and this image, which is our region of interest, right? So this is the initial position I'm going to pass to our mean shift function, right? So now in the next step, what we are going to do is we are going to define the histogram back projection. So we already have our ROI. So in the next step, we are going to just convert this ROI to the HSV color space. So I'm going to just write HSV underscore ROI. HSV we have already learned in the previous video, so I'm not going to go into the details of HSV color space. I'm going to just write CV dot CVT color, which is going to convert this image into the HSV color space. So our input image will be the ROI, and the next parameter will be CV dot color underscore BGR to HSV. Okay, so we are converting this image to the HSV color space, and then we are going to calculate the mask. So let's say we define a variable called mask, and for the mask we are going to just write CV dot in range. So this also we have learned in the HSV tutorial. So if you want to learn more about all these functions, you can just go to that video. So first parameter we are going to pass is our HSV image, and the second parameter and the third parameter will be the lower and the upper bound. So the lower limit will be 0 dot comma 60 dot comma 32 dot. Okay, so let's pass this, and the upper limit, so let's define the upper limit also. So the third parameter will be the upper limit in the form of the tuple, but we need to use the numpy for that, right? So numpy dot array, and inside that we just pass this tuple value, which will be 180 dot 255 dot 255. Okay, so 180 dot comma 255 dot comma 255. So why we use the in range function? Because for the histogram only hue is considered from HSV, right? So the first channel, right? And also to avoid the false value due to low light or low light value, we use the in range function. Okay, so these low light values are discarded using the in range function. And then in the next step, we are going to calculate our histogram value. So I'm going to define this variable called ROI hist. This also we have learned in the previous video, so I'm not going to go into the details. So I'm going to just use the function called calc hist, which takes the first parameter, which will be the image. So I'm going to just pass our HSV ROI. So just pass HSV underscore ROI. The second value here will be the channels. So we are just using only hue channel, the first channel in the HSV space. So we are going to just write 0 here. Mask. Now the next parameter will be the mask. So we have already calculated the mask. So we are going to just pass this mask parameter here. The next parameter will be the hist size. So as we have already learned in the previous videos, that this hist size starts from 0 to 179. So essentially 180 values. And then we just need to pass the ranges. So as I said, it starts from 0 to 1. And now in the next step, we are going to just normalize these values using the normalize function. So this normalize function takes few values. First is the source. So the source is our ROI hist variable. The next value is the destination. So let's say we have the same destination. We just want to overwrite this ROI hist value. The next parameter here will be the value of alpha. So alpha will start from 0 and the value of beta will be 255. So we want to normalize these values between 0 to 255. Okay, and then the next value will be the norm type. So the norm type we are going to take is CV dot norm min max. Okay, so we are going to just take this one, norm min max. So all these steps which we have written here is going to give us the histogram back projected image. Now once we have this histogram back projected image, we are going to use this histogram back projected image, which is also going to change with the moving object. So now in the next step, we are going to go inside our while loop and read each and every frame one by one. And first of all, what we are going to do is we are going to calculate the HSV value of the frame as we have done with the first frame also, right? So we are going to just take the frame and then calculate the HSV ROI value. Let's say this time we are going to name it as HSV, and we are going to pass frame as the source instead of this ROI value. Now in the next step, we are going to use a function called calculate back project. So let's define the variable called dest for destination, and then cv dot calc back project, which is the function for calculating the back projection. And this function takes few arguments. First is the number of images. So we only have our HSV image, so we are going to pass in the form of the list. The second argument will be the channels. So as I said, we just want to use the hue values here, so only one channel. So we are going to just write 0. So because channel starts from 0, 1, 2, so that's why I have written 0 here. The third parameter is the hist value. So in this case, our hist value is the ROI hist, which we have calculated. The next parameter is the ranges. So we will start from 0 to 180 as we are talking about the HSV color space, and the next value will be the scale. So let's say scale, for now we take 1 as the scale. So this is going to give you the back projected image, and then in the next step we are going to apply the mean shift to get the new location. So I'm going to just write ret comma track window. So I'm going to just say track window, which is this variable which we have already defined, and then we are going to just use cv dot mean shift, which is going to take few arguments. First is the image, which is the destination image which we got from the back project function, calc back project, and next argument will be our track image, which is the track window. So we have to define this term criteria. So I'm going to just write term CRIT for criteria, and then we have to define this outside this while loop. So I'm going to go here, and we are going to set up the termination criteria, either 10 iterations or move by at least 1 point. Okay, so we are going to define that criteria. So here in the curly brackets we are going to just say cv dot term criteria ESP or cv dot term criteria count. So because we want to either provide the termination criteria for either 10 iterations, so we just give 10, or we want to terminate by moving at least 1 point. This is the criteria for the mean shift, and we are providing these two track criteria. So once we have our track window for the car, we can draw a rectangle with the help of this track window, and this will be visible on our video. So we are going to draw that window. We are going to just say x comma y comma w comma h for xy width and height, and this will be our track window. And then we are going to just draw a rectangle. So I'm going to just say we have the final image, and then we are going to just write cv dot rectangle, which is going to take the frame and then the point for the first point of the rectangle and the second point of the rectangle, which are the coordinates of that point. So the first point coordinates will be x comma y, and the second point coordinate will be x plus width comma y plus height. Okay, and then the next value will be the color. Let's say we want to use 255 here, and the thickness, so thickness we want to take 3 here, for example. Now we can just show this final image using IamShow method. So till now we were just showing our original frame, so we can just say, let's say we want to show the final image here. Also, if you want to see the back projected image, you can just use this destination. So we can print this destination image also and see how does this back projected image looks like. So let's run this code, and you can see this car window is dragged, right? So as the car moves, this window also moves. Once this car goes out of the scope, it drags the other window. So this is how the mean shift algorithm works in OpenCV. Now, as I said, this mean shift has few disadvantages or limitations. The first limitation is the size of the target window does not change. So as we have seen, once this car is coming near to us, the size of this window is not changing, it remains always same. So this is one problem. The second problem is we have to give the initial position of our region of interest. So for example, if initial position of the region of interest is not known, then it will be really hard to apply mean shift method. So there are these two main limitations of this mean shift algorithm, and we are going to try to solve these limitations in the next video when we learn CAM shift, which stands for continuously adaptive mean shift.
In the last video, we have learned how to use mean shift algorithm to find and track objects in the video. In this video, we are going to learn CAM shift algorithm to track the object in the video. So if you have seen the last video, we have written this code. So we are going to use all this code which we have written in the mean shift video tutorial. And first of all, let me just run this mean shift code which we have written in the last video. And we have discussed about this problem of this rectangle which always remains the same even if the object is coming closer to the camera. So we need to adopt the window size with the size and rotation of the target. So once again, the solution came from OpenCV labs, and this time they introduced an algorithm which is called CAM shift, which stands for continuously adaptive mean shift. So this CAM shift algorithm applies mean shift first, and then once the mean shift converges, it updates the size of the window. In addition, it also calculates the orientation of the best fitting ellipse to it. Now let's talk about the implementation part of the CAM shift. So as I said, all the code which we have written in the last video will remain the same, except one thing, which is we have used this mean shift algorithm in the last video, and in this video we are going to use the CAM shift. So just write cv.cam shift, and all the parameters also will remain the same, which is destination, track window, and the termination criteria. So let's run this code once again, and let's see what result came out of this algorithm. So you can see this rectangle is changing its size according to the target. Now this result which we have seen can be better because the CAM shift function returns a rotated rectangle, that is our result, and also the box parameters which are used to be passed as the search window in the next iteration. So here when we see the result inside the RET variable, so let's print the result inside the RET variable. I'm going to just print it using the print function. Now let's run this code and let's see what this RET variable prints on the terminal. So let me just press escape. So what is this result? So here you will see the value of x and y, and also you will see these three values which are your width, height, and the value of rotation. So in CAM shift you can also rotate your rectangle according to your object size. So now we are going to use all these parameters which are there inside this RET variable, and we are going to try to draw the rectangle which might be rotating. So there will be a different approach other than this rectangle. We are going to use that approach to print those points which we got using the RET variable. So let's draw that rectangle. So here we are going to define a variable called PTS, and there is a function called cv.boxPoints. So we are going to use that function here, which is box points, and it takes a few arguments. We just need to pass our RET variable here. So we are going to just pass our RET. So let's see what values this is going to give us. So I'm going to just print this PTS value. So I'm going to just print the value of PTS now. Let's run this code once again. You won't see anything. and you will see these values, right? So it's going to give these floating point values, which we need to convert it into the integers, and the error was due to this because this is no longer defined, right? So for that, we are going to just convert these points PTS into the integer values. So I'm going to override this variable PTS, and then there is a function in Numpy which is called int 0, and here when you pass this PTS variable, it's going to convert those points into the integers. And now we can just draw our rectangle. But remember, this is a rotating rectangle, so we cannot use this normal rectangle function. So we need to use the other function for drawing those points. So I'm going to define this final image variable once again, and then I'm going to use cv.polylines. So there is this function called polylines, which you can use to draw those lines which you get using this points variable. So we are going to just pass the frame first of all. So we need to pass the frame as a first parameter. The second parameter will be our PTS value, and then the third parameter will be the closed or not closed. So when we pass true here, then this rectangle will be closed, right? Then we need to pass the color. So you can pass any color here, let's say 0, 255, 0, and then you can also pass the thickness. So let's say we just need to give the thickness of 2 here. Okay, so this is our final image, and now we are going to run this example once again, and let's see what happens. So you can see this rectangle is drawn, and it can rotate also with the object. So this is how camshift algorithm works with OpenCV. I hope you've enjoyed this video, and I will see you in the next video.